Yeah, perfect. Welcome, everyone. We're going to start 5 minutes late, so we're going to start 9:05 just to give people a chance to stream in. So 9:05 is when it starts. Oh, the clicker's right here. Perfect. Yes.
It'll be that one, but this will also be here for them.
Hi everyone. We're running a little bit late, so we're going to start at 9:05 instead of 9 a.m. But please, everybody, start to grab your seats, and we'll start in 5 minutes. Okay, can we put up the slides? Aha. Perfect.
I'm not connected to my.
I can see it over there. It's fine. Okay, we're about to get started. So if everybody could grab their seats, we'll get this show on the road. I see people are still streaming in. All right, so let's get started. So welcome everyone to the Science of Blockchain conference. This is the 6th SBC conference. I'm really happy that everyone came. Wonderful event, and I'm really looking forward to the program over the next 3 days. We have lots of wonderful talks planned. So just before I dive into the welcome remarks, just a few technical announcements. If you want to get on the Wi-Fi, the SSID is Stanford, and I wrote down the username and password here, so it should be pretty easy to get on to the Wi-Fi. If you want to, the conference is also live streamed, so if you happen to not be here but still watching us, the information on the live stream is available on the conference website. There are actually 2 ways to watch the live stream, either on YouTube or on livestream.com, and both links are on the conference website. And if you want to tweet about the conference, there's a hashtag there too. The conference is hosted by the Stanford Center for Blockchain Research in collaboration with IC3 and with Berkeley RDI. Thank you for our collaborators for helping set up the conference. All right, so this conference is actually supposed to be a very technical conference. Yeah, it's designed for engineers and for researchers. So we encourage all the speakers to give very technical talks. There's no marketing. This is about the technical aspects of blockchains. And so we're looking at the conference is going to explore kind of new research challenges, new research ideas in the blockchain space. And of course, it brings together sort of the research community along with engineers. So actually, I encourage all the speakers to talk about not just problems they know how to solve, but also problems that they would like help with. So open problems is something that gets everybody excited, and hopefully we can generate also some new ideas in the space over the next 3 days. Yeah, so again, it's intended to be a very technical conference focusing on blockchain technology, and that's primarily what this is about. Now, I have to say this is, if you look at the number of registrations, we've been running this now since 2015, I think, so it's been running for a while. If you look at the number of registrations in 2020, we had about 1,400. This was like, literally, if you remember, we ran this conference, I think, like a month before the lockdown or so. We just got it happen. It just happened before everything kind of shut down. In 2022, when we started it again, we had 4,000 registrations, and this year we had a similar amount, 3,500 registrations. So, what crypto winter? Everybody's, everything is up. People are, or at least in terms of people who come to the conference, lots of interest and lots of excitement in the space. So the community is, of course, alive and vibrant and doing quite well. So because of all the registrations, unfortunately, there's not. We couldn't get the football stadium is not available for this event, unfortunately. Because of this, I'm really sorry that not everybody could attend in person. But if this room fills up, there is overflow space on the other side of the building, so you can easily walk to the other side. Everything is going to be visible there, and you can watch the lectures from there. We're just not allowed to overflow this room. In particular, the aisles need to be kept clear. So please keep the aisles clear so as not to cause a fire hazard. All right, so that's kind of in terms of attendance. The program itself was set by the program committee. The program chairs are myself, Ari Jules, and Don Song. So thank you, Ari and Don, for helping set the program. I wanted to give you a few statistics about the submissions. So again, last year when we ran the conference, we had about 116 submissions. We accepted 25, so about a 20% acceptance rate. What do you think happened this year? More or less submissions? Well, I'll tell you. So amazingly, actually the number of submissions this year more than doubled, yeah, which is kind of amazing. The research community, again, in this space is very, very vibrant. We had a lot of submissions. We had to increase the program committee at the last moment because of all the submissions, but this is great. Please keep it coming. We hope to see the same number of submissions next year or maybe even more. As a result, though, the acceptance rates kind of dropped to 11%. So again, we apologize. Not all the submissions could be accepted, although there were lots of wonderful submissions that we would have loved to have in the program, but there was just not enough space. So please keep submitting, and next year we're looking forward to having as many submissions as well. And again, such a high quality program. So speaking of next year. The conference, again, is going to take place sometimes in August. I wrote down the URL for the submission site. So if you have a submission plan for next year, you can already go ahead and think about submitting, and this is where you'll submit. In fact, the big change next year is that the conference is going to start moving around. Yeah, so we've been holding it at Stanford now for many years, but next year we're actually going to hold it in New York. Yeah, so thank you, Ari, for being the general chair. Next year. Now, you might remember that I promised that this year was going to be in New York too, but we delayed it by a year. But next year, for sure, it'll be in New York. Yeah, and so wait for more announcements on that. And then it's going to start ping-ponging between the two coasts. So that's the plan for the coming SBCs. Okay, another important thing to remember is tomorrow there's going to be an open session for everyone. So there's a lightning talks session tomorrow. So if you have anything interesting you'd like to share with the community, please go ahead and prepare for a 2 to 3 minute talk. Anyone can come on stage and speak. What we'll do is we'll just line up along the walls there. Ben Fish is going to be the chair for the lightning talk session. We're going to line up along the walls. He's going to call you up, and you'll get to present for like 2 to 3 minutes. Ideally, just speaking, no slides. But if you're doing something exciting, interesting project, or have a wonderful research idea, come on stage, please, and share that with the community. Yeah, so just maybe start thinking about what it is you'd like to present at the lightning session tomorrow at noon. All right, so you can also try to find Ben if you'd like more information about what to do there. All right, so that's the lightning talks. Next, I want to thank a few people without whom this conference couldn't happen. So first of all, I want to thank the program committee. The program committee did a lot of work in reviewing all the submissions. Every submission was reviewed by at least three members of the committee. There were lots of reviews, lots of discussion taking place until we finally converged onto the program. So thank you to the program committee for all the hard work. Yeah, thanks everyone. Thanks to our sponsors. The only reason we're able to keep this conference free and open to everyone, you notice there's no registration fee. Everybody's welcome to attend, subject to the constraints of the room. The only reason we're able to keep this conference free is thanks to our sponsors. So a big thanks to all the sponsors who made this possible. Thank you so much, and we hope you'll come back and sponsor the conference next year too, so we can keep it as a free and open event. And finally, I want to especially thank Ruth Harris, who made this, who is responsible for all the local arrangements, the lunch, and everything that you see here. So thank you so much, Ruth. And actually, there are many volunteers from the Stanford Blockchain Club who also are helping with the name badges and welcoming everyone. And so again, thanks for all the volunteers. And with the registration, by the way, with so many registrations, we couldn't handle this. I couldn't handle this by myself. So Joachim and Nusret stepped in and helped with managing the registrations. So again, big thanks for making all this possible. Yeah, thank you all. Finally, since you're on campus, the Stanford campus is a really beautiful campus. It's kind of a shame to come to Stanford and just sit in a room for 3 days. So don't do that. Try to walk around the campus. There's really a lot to see on campus. And this is also a beautiful time. The weather is nice. You're not going to get run over by students on bicycles because the campus is not on session. So this is a really nice time to walk around the campus. So I thought I'd just point out a few places to see. So we are at the Alumni Center. You can see where we are right now. We're kind of on the left top side of the campus. If you're wondering, the computer science department is actually on the other side of campus. That's where we spend all of our time. But there's also lots of other things to see on campus. For example, you can walk over to the bookstore. It's kind of a nice bookstore with lots of, Stanford things there. That's kind of a part of a large student center, so that's kind of a nice place to visit. If you're into art, you can walk over to the Rodin Sculpture Garden, which is literally just across the way. So you just kind of walk along Rothway. From here, you'll hit the Sculpture Garden. It's a very, very pretty place to kind of maybe go have lunch if you want, if you have some time to kill, or just walk through the Sculpture Garden and look at the museum. Very, very pretty place to visit. And let's see, is there another place? Yeah, and that's it. So some places to see on campus. Before we start the program, I did want to mention a whole bunch of blockchain activities at Stanford, just so you know this is all available to you. So first of all, we run a seminar, a blockchain seminar. Everything is recorded, live streamed, anyone can join. If you just go to the CBR website and look at the seminar page, you can join the mailing list, you'll get announcements. I promise it's a very, very low volume mailing list. You'll just get announcements about blockchain events on campus. Everything is live streamed and you can watch the seminar talks remotely, ask questions, and participate. So this is a good activity to join. We also run a lot of blockchain courses. They're, again, on the CBR, the Center for Blockchain Research website. you can take our courses remotely. You don't have to be on campus to do it. It's open to the world. Yeah, take a look at this website. If there's a course, a blockchain course that's appealing to you, you can sign up and take it remotely. And finally, I want to give a shout out to the Blockchain Club, the Stanford Blockchain Club. These guys organize like many events. There are almost weekly events by various blockchain companies. Again, everything is live streamed, and you can follow their events on on this website. Yeah, so just a quick shout out to various events that you can join if you have a moment. So let's see. So the schedule for today for the conference is basically we're going to run from 9 to 5 p.m. Every day from Monday to Wednesday. On Thursday and Friday, we're going to run additional workshops. So I hope everybody can hang around for the workshops as well. The lunch is going to be at around 12:30. It's going to be served right outside, so everybody can grab a lunch box and just spread out around the building. We have the whole building for the entire conference, so feel free. It's a beautiful building. You can just hang out wherever, eat lunch, hang out, and talk to folks. Tonight we're going to be running a reception, so 5:20 to 7, I think. There'll be a reception right outside there with a good chance to meet fellow attendees and talk all about blockchains. Then actually the evening activities start. So on the conference website, you'll see that every night, tonight, tomorrow, and on Wednesday, there are a bunch of evening activities that begin when the conference ends. The only thing is, please sign up for these activities. They happen in downtown Palo Alto. And again, everybody's welcome to come to these activities. And as I mentioned, tomorrow we're going to have the lightning talks. So please prepare a talk if you'd like to share something with the community. All right. The main thing, of course, is have fun. I hope you really enjoy the conference, and I'm really, really looking forward to all the talks. Okay, so one last thing. Yeah, we talked about overflow seating on the other side of the building. I have to say that no smoking is allowed 25 feet within the building, and we also have hand sanitizers around the room and outside in case anybody wants to use the hand sanitizers. And with that, let's get started. So the first session chair is Dan Robinson. So Dan, the show is yours. Please take it away.
Hi, everyone. We'll be kicking off the first session on automated market making with a presentation from Jason Milionis. Jason burst onto the scene last year as the lead author on the paper introducing the seminal concept of loss versus rebalancing, or lever. And this is a paper that extends that concept on automated market making and arbitrage profits in the presence of fees. So welcome, Jason.
Are the slides working? Okay. I guess they're working now. Let's. Okay, yeah. Hi, everyone. Thanks, Dan, for the welcoming. So today, I will be talking to you about our joint work with Siamak and Tim on the economics of liquidity provision in automated market makers. So currently, we have about $4, $5, or $6 billion locked in on providing liquidity in automated market makers. And these liquidity providers who give capital to AMMs are clearly subject to some risk. But how much is that risk, actually? So last year at SBC, we introduced Lever, along with our co-author, Anthony, to precisely account for the arbitrage losses of liquidity providers in AMMs. Since then, there has been lots of discussion on the losses of liquidity providers, and Lever has become kind of the center of focus for a big part of it. So entire research spaces have actually been devoted to figuring out ways to mitigate Lever. But of course, one question remains, that is, what about fees? And so namely, lever was derived as the profit that is obtained by the arbitrageurs under the assumption that they can snipe prices without paying fees to the pool. Obviously, though, pools have fees, and so what we'd like to do is to actually refine our understanding given the presence of these fees. So I'm here to present to you the exciting follow-up work that we have on what happens to arbitrage profits when we introduce trading fees and discrete block times to the model. One of the main takeaways of this talk will be that the losses to the LPs that used to be lever are now going to be, well, what a surprise, lever again, multiplied by the probability of trade this time, which we'll see later in the talk what that stands for. And as a result of this, we saw that faster block times actually lead to our profits going down. But more than that, our work essentially shows that lever is still a very meaningful quantity in that it is precisely split into two components, one of which is the arbitrage profits that goes to the ARBs, and the rest of it that is returned to the LPs in the form of fees. So specifically, as fees increase, lever essentially gradually gets converted from arbitrage profits to fees that are being paid back to the AMM. So we'll first review the basic lever model, and then I'll show you what happens when we also introduce trading fees and discrete block times to this model. So we have a risky asset, X, for example, Ethereum, and a numeraire asset, Y, for example, USDC. And we have an external market for this risky asset. For example, you can imagine Binance, a centralized exchange, that has a market price for this asset that we denote by PT. And we assume that there is someone who essentially always knows this last up-to-date market price, PT. And these people are called arbitrageurs, or ARBs for short. And now we're going to have a probabilistic model for what the market price is. And essentially, this is the standard probabilistic model in quantitative finance that is known as the Black-Scholes model, which essentially, to those of you who might not be familiar with it, a 1-minute explanation is that the price oscillates all around the place, and over small time horizons, so over a tiny delta t, essentially the returns of this asset are going to be normally distributed with some mean that depends on a drift mu, and some volatility that's essentially this sigma that you see over there. So the price curve is essentially looking something like the one that you see on the slide. And so the way we're going to use the AMMs in this work is going to be through what we call demand curves. And so essentially, when we have the pool have a price P, then essentially we will say that the reserves that this pool holds are in the form of X of P for the risky asset and Y of P for the numeraire asset. And now if we have this definition, then we can define something that we call the rebalancing strategy, which essentially starts from the same reserves as the pool holds initially and tracks the risky asset exactly as it happens on the pool, except that it does so at market prices and not at pool prices. And so what is defined as lever is essentially the difference between the value of this portfolio of the rebalancing strategy and the value that we actually observe on the pool. And so the characterization that we gave at last year's SBC is essentially that this lever quantity is a stochastic process that's always increasing, and specifically it has an instantaneous rate which depends on the asset volatility sigma, it depends on the price P, and it depends on the marginal liquidity that the AMM provides at this price P, which is this Y prime of P that you see over there. So for example, if we imagine a constant product rule like Uniswap v2, then you might have seen by now the formula sigma squared over 8. What is that saying? That is saying that essentially, for example, with a 5% daily volatility for the asset, essentially the liquidity provider is going to lose a value of about 3 basis points daily of their portfolio value. So this corresponds to an annualized amount of about 11%. But of course, there is a key question, which is where does this money actually, is this money actually realized, right? Because all of this I showed you until now is a theoretical strategy. Well, it turns out that the people who actually implement the rebalancing strategy are exactly the arbitrageurs. And so whenever these arbitrageurs see that the AMM price is different than the pool price, then they will make trades on the pool to exploit that. And it turns out that under the assumptions in this model, namely that arbitrageurs are able to trade continuously and that they do not pay fees, the profits that the arbitrageurs are able to extract are going to be exactly that lever quantity that we saw previously. But of course, let's think about these assumptions a bit more carefully, right? First of all, you cannot continuously trade in a pool, but you can only trade when blocks are generated. And on the other hand, pools, as we've said already, have trading fees. So how do these two aspects actually affect the AMM? Let's try to relax these assumptions one at a time to make the model more realistic and see the effect that they have. So here, I'm showing you again the external market price in the red curve. And so when the arbitrageurs are able to rebalance continuously and without trading fees, then essentially what's going to happen is that the pool price is always going to match this external market price. And so in particular, the blue curve is going to be on top of the red curve. This is what we're going to observe. So now let's try to additionally add discrete block times. And so I want you to look at this particular graph over here. Let me first draw your attention to the red axis and the x-axis. These are the block generation times. So these are the times that you actually see blocks on chain. And these are the only times that the arbitrageurs can actually transact with the pool. Now, again, we do not have fees here. We only have these discrete block times. And so what will happen now is that there is periods of quiescence in between these block arrival times. And whenever a block arrives, there's a change that's being made to the pool price. And what is that change corresponding to? That change is corresponding to switching the AMM pool price back to the external market price at that moment. So this is the effect of just discrete block times. Now let's try to additionally add on top of that model trading fees as well. What is going to be the effect now to the pool price? Well, there's now going to be a no trade region, actually, around the current AMM pool price. And whenever the red curve is within this gray shaded region, that is the AMM pool price, we're essentially not going to see any trade, even if we could see a trade. So let's see these red points now. At these red points, you essentially do not have a trade, even though you were allowed to trade, because exactly the market price is within this not trade region, where not trade occurs. There are some moments when the external market price is outside of this no trade region, and if you were allowed to trade, you would have gotten a trade, but you were not allowed in some of these cases. In the green ones, as you see, the external market price is outside the no trade region, so an arbitrageur would be able to profitably trade with the pool, and this is actually what happens because they are allowed to trade at this moment. It is the moment that a block arrives. And so in particular, what the effect of this trade is going to be, as you can see here, is that the pool price does not go all the way up to the external market price in the first green X case, and it doesn't go all the way down to the external market price in the second green X case. There is essentially a suppression of moves in the pool price. And this happens because essentially the marginal profit of the arbitrageur has to be positive or 0 for them to transact with the pool. And what they're paying, which is their marginal cost, which is the fee of the pool, essentially has to be lower than what they gain, the marginal revenue. So essentially the price, the AMM pool price, does not go all the way up to the external market price. So that's going to be the effect of both of these aspects. And now let's see what is the model that you would expect given what I showed you? Well, we still have the price model as previously in a Brownian motion, essentially. And we have two additional characteristics. First of all, we have discrete block arrival times according to a Poisson process. That is also the standard process in quantitative finance, and it is what allows us actually to get analytical results in this work. And so in particular, this means that on average, every delta t, you're going to see a block on chain. And we also have uniform proportional fees. So this means that you have a gamma fraction of the trade size that is going to be given back to the pool in the form of fees. For example, you can imagine a Uniswap 30 basis points fee. Let's also introduce some additional notation to see what the actual formal is going to be. So we have the PT, as we said, the external market price. And now we also have PT tilde, which is the implied pool price. So this is the price that you see in the pool. And we define a quantity that we call the log mispricing that essentially captures the mismatch between the pool price and the external market price. So this mispricing, ZT, is going to be a random variable that is going to be 0 exactly when the pool price is exactly the same as the external market price. So large mispricing means that there is a high mismatch between the pool price and the external market price at this time instant. And small mispricing in absolute value means that there is good price match between the external market price and the pool price. So let's, the bottom picture here is the picture I showed you previously. So this is how the price of the AMM is affected when you have these specific block times. And the top price is actually where we're going to see what happens with the mispricing now. So the mispricing, as you see, it oscillates around the interval from minus gamma to plus gamma. And actually, the profitable case, the profitable trades, are only going to be outside of this no trade region. So the no trade region is now captured in this interval, minus gamma gamma. Whenever the mispricing is within this interval, even if you're allowed to trade, you will not trade. And if it's outside of this no trade interval, then a trade will actually occur. And so what we will actually see over there is that in these green cases, we have a jump of the mispricing process. How is this jump reflected? This jump is reflected back to the boundary of this no trade interval. And the reason for that is something that has to do again with the marginal profit that the ARB is able to obtain. So the marginal profit that the ARB is going to obtain is actually only going to be non-negative whenever they're able to obtain a marginal revenue that's more than their marginal cost, and their marginal cost is the fee that they pay, this gamma, right? So, so this means in order for their marginal revenue to be greater than gamma, the mispricing has to be more than gamma in absolute value. So this is exactly why we see these trades and these jumps. And so this is essentially stating whatever I said to you previously a bit more formally. Whenever you get a block, you will get an ARB trade only if the mispricing is outside of this not trade interval. And how will you see this trade? You will see that the mispricing will get pushed back to the boundary of that interval. Otherwise, this mispricing is going to follow a diffusion process, so it's going to have some drift and it's going to have some Brownian component with the asset volatility. Now, in this talk, I'm going to make the assumption that the drift cancels out, but feel free to check the paper for the general version that holds for any drift. So the first result of our work is essentially the steady state distribution of this mispricing random process. And in particular, it's going to look like it will be uniform in between the no trade interval. So from minus gamma to gamma, it's going to look like a uniform density. And it's going to have exponentially dropping tails outside of this interval. In particular, I think a corollary that's interesting from our work is that you can actually think about the fraction of blocks that you expect to see with an arbitrage trade. And in particular, this is quantified by this quantity that I told you before, the P trade, which amounts to 1 over 1 plus eta, where this eta captures essentially how wide the fee band is compared to the typical price movement in the return space that you're going to see over half of the block time. So in the geometric burn-in-motion model, this typical price movement over half of the block time is going to be sigma root of half of delta t. So this eta essentially captures how many blocks you're expecting to see until the typical price movement exceeds the not trade range, essentially. That's the intuitive explanation for that. And so, for example, if we have a daily asset volatility of about 5% and a 12-second block time, then we can see that the fraction of blocks that you expect to see an arbitrage trade ranges all the way from 4% to 81% for natural fees that we see on pools. So let's now talk about the arbitrage profits. That's the rather interesting case here. What we're going to do is, first of all, we're going to sum all of the arbitrage profits that we see over a time interval. Then we're going to take the time average of that, and we're going to translate that into an instantaneous rate that we see the arb profits. And the result of our work is that in the asymptotically fast block regime, so as the block time tends to 0, then essentially what you're going to have the arbitrage profit for the arbitrage profits is that you're going to have all of these colored boxes that you see over there. The first two ones that you see match the ones on lever for small fees. And so essentially you're going to have arbitrage profits that are effectively lever times this new quantity that we saw before, the probability of trade. So these are the arbitrage profits that we're actually expecting to see on-chain. Now, what is the relation of that with the block time? Well, as we saw a couple of slides ago, the probability of trade essentially scales down with the square root of the block time. And the arbitrage profits are effectively lever times this probability of trade. So these two facts translate to the fact that arbitrage profits are actually going to go down with the square root of the block time. And so this means that if you have faster blocks, then liquidity providers are going to suffer less losses due to arbitrage. But of course, faster block times have other considerations that are outside of our model. For example, decentralization considerations. And as an example here, we can see that if someone manages to drop the block time from 12 seconds all the way down to 3 seconds, then the arbitrage profits are effectively going to be reduced to about half of what they were previously. We can do an analogous procedure to examine the fees of the arbitrageurs, and I will not go too much into the details of that, but essentially what this says is that we have the interesting result that the fees that the arbs are going to send back to the liquidity providers in the pool is effectively going to be lever times 1 minus P trade. So this means essentially that the arbitrage fees that you're going to get are going to be the difference between lever and the arbitrage profits because of the result that we saw previously. And so in particular, I think what I want to highlight here is that lever is still a very meaningful quantity that essentially is being split when you have trading fees into two sub-quantities. One that is essentially the profits that are earned by the arbitrageurs, and a second one that is the fees that are being paid back to the LPs. What determines this split is exactly this probability of trade. And so in particular, the arb profits are going to be the lever times the probability of trade, and what's left of that is going to be go back as fees. I think the one more interesting thing and one innovation in this paper that might not be apparent at first sight is essentially the use of Poisson arrivals that allow us to get analytical results in this model. That same technique essentially can be applied to other fee structures as well that have been proposed, for example, to mitigate lever. And so I think I would be pretty excited to see what the community comes up with to take advantage of these tools that we developed. And so with that, I'd like to thank you very much.
All right, we have time for a couple questions, so people who want to ask questions can come line up in front of the two mics there and there. I have a first question, which is, I think what you call ARB in this paper is what most of the industry calls lever, and has adopted this term that you used last year to refer to this practical problem of reducing the actual losses by liquidity providers. But you're defining this new term, ARB, to describe that. Why don't you just redefine lever to apply to the no fee situation as well, or the positive fee situation as well?
Yeah, that is a great question. Actually, I believe that what lever captures is actually if you want, the money that is on the table. And so basically, lever is the total money that is on the table, and this money may go to several different paths.
Sorry, while you're talking, let him set up his computer.
Yeah. And so essentially, this lever can essentially go either to the arbitrageurs, it can go back to the liquidity providers, or it can go to block proposers. But it doesn't essentially matter where it goes to. The total amount that is on the table is still going to be lever. It's just that the split is going to be different. But it is true that the arbitrage profits are not going to be exactly levered this time, because the split is defined differently.
Hi. I think it's a really cool model. You've managed to encapsulate the fact that you have two groups, both of which are providing services to the AMM. The LPs are providing liquidity so that there's enough there to do trades, and the arbitrageurs are providing the price tracking with the external price. And the profits from that, or are getting distributed between the two camps, and that can be calibrated by the fee and by the block arrival time, I suppose. Mm-hmm. It'd be interesting to see a follow-up model where you consider from the perspective of a user of an AMM who's trying to place an order into the AMM, and their relative preferences for liquidity versus price tracking, and based on that economic model, what would be the correct fee structure to set up within that AMM, right? Mm-hmm. Yeah, I think that would be a cool follow-up.
Mm-hmm, mm-hmm. Yeah, I agree with what you said. I think though that we can't exactly determine what's the optimal fee structure. What we can rather do is compare a bunch of different fee structures. And I think this work gives you the tools to do that comparison. And I think the side from what you were mentioning is essentially the user's execution price, right? So what is the execution of the user? Is it a good execution, or is it a bad execution that they're getting? This has to do with both price discovery and fees, and I think it's something that's usually called the effective spread. So that's essentially what the user effectively sees, because the user sees both the mispricing of the pool, but they also see the fee that they're going to incur from their trade. Well, so these two might be in the same direction, or they might be in the opposite direction, and this affects how good the execution is of the trade.
Well, I think you probably could model it, right? Because you could probably construct some sort of utility function that balances between the liquidity present in the pool versus the spread, right, from the external price. And the user, the model user could to determine which one he values more relative to the other. And based on that, as the designer of the AMM marketplace, you could say, all right, I'm going to calibrate my fee to be this much, so not 30 beeps, but maybe 40 beeps or something, because that achieves something that is more desirable to a user with this kind of utility function, right?
Yeah, absolutely. If you don't have a specific utility function for the user, then yeah, you can get these sorts of results. Yeah.
Thank you.
Great. Thanks, Jason. Next up, Mahak Goyal from Stanford is going to be presenting on finding the right curve in his model for optimal design of constant function market makers.
Hello, Hello everyone, my name is Mohak Goyal. I'm a PhD student at Stanford University. I will present my work with my collaborators Jeff Ramseyer, Ashish Goyal, and David Maziers, who are all also at Stanford University. So this work is on the design of the constant function market makers, that is the trading function which the LPs want to use for the market making. So many of you would be familiar with the basics of market making, but I will still go over some of the basics. So market makers are the traders who are willing to take both the buy and the sell side in any pair of assets. And by doing so, they provide a liquidity to the market. In this business, they take a risk of ending up holding an asset whose price may decrease in the future. And in return for this risk, they earn a bid-ask spread or a fees on every trade that they facilitate. In traditional finance, market making is typically done by high-frequency trading firms. These firms have complicated inventory management and pricing algorithms. They look for new information and incorporate that in real time. By real time, I mean in the order of microseconds. And they keep their strategies and information privately, and that is their edge over the competitors. Now, in the new era of decentralized finance, we want to do market making on public blockchains. However, the blockchain infrastructure is not well suited for the traditional type of market making. For example, in the current state of the blockchains, there is high latency, low throughput, and high gas cost, and there are problems such as front running. Also, the traders' strategies have to be transparent, which removes their edge over the competitors. However, there are still billions of US dollars engaged in decentralized finance today. So how is this happening? So one innovation which has driven a lot of the progress in decentralized finance is constant function market makers. So this is a market making strategy which is intuitively very simple. That is, liquidity providers can deposit their tokens in a shared pool and define a simple function for computing the price that they want to offer for any trade request. So the trading function has to be quasi-concave, continuous, and non-decreasing in the asset amounts. The trading rule specified by the trading function is that any trade is acceptable as long as after the trade, the CFMM's trade function value is not decreasing. So this is the entire set of requirements that the LPs have to satisfy to set up a CFMM. But the question is that which CFMM should a liquidity provider use? So let us consider a simple example. We want to make a market between the euro and the US dollars or their crypto equivalents. The liquidity provider has many options. One canonical choice which has been very successful and popular in the initial days of DeFi was the constant product market maker. Informally, the constant product market maker will spread the liquidity to all the price points possible. However, an LP may feel that the price between the euro and the US dollar may not change in the near future, and the most efficient way of depositing their liquidity is to put it at one price point. Another possibility would be to spread the liquidity to a smaller price interval, and there can be an infinite number of such possibilities by taking interpolations of these curves. So before designing the curve that a liquidity provider may want to use, we first want to understand what are their sources of revenues and the losses. Their main source of revenue are the fees that they charge on each trade, which is equivalent to a bid-ask spread. However, they also have many losses. One important source of loss is the inventory cost. This is basically the loss that they have to face if the assets that they hold for market making diminish in price relative to a numeraire. This loss can be hedged partially by buying options, as shown in previous work. However, the more important part of their loss is the loss due to the arbitrage, which is captured very well in the Liver metric. So this happens when the asset's fundamental value changes on an external exchange. However, since the CFMM is a passive trading strategy, it continues to trade at a stale price unless an arbitrager comes along and they correct the CFMM's price. By doing so, they make a risk-free profit. And as shown by previous work, this loss is unavoidable. We can reduce it by choosing better trading strategies, but we cannot totally eliminate it. So these are the major considerations that an LP must have before deciding whether they want to enter the business of market making, and if yes, then with which trading function. So I would like to summarize our contributions on this slide. So we give a framework to find the optimal CFMM trading function, which is optimal in expectation for any given set of beliefs on the future prices of the underlying assets. Or they can also work with a price dynamics process, and they can use that dynamics process to condense that into a set of beliefs on the future prices. And our framework can consider different objectives, which can include efficiency. We define efficiency as the fraction of trades that the CFMM can satisfy within a maximum slippage amount. We can also consider the fees and the different types of losses. Our framework is also able to explain some folklore intuitions of CFMM designs which have been successful in practice. One important thing that I want to clarify is that in this model, we do not consider rebalancing. Our results basically apply to the interval between two subsequent rebalancing events. So this is very broadly put, our optimization problem will look something like this, that we want to maximize some objective function, which could be a combination of efficiency, loss, or whatever the LP is interested in. But their constraints are very specific to the CFMM's design principles. So first thing is that the LP will start with a limited total budget. This can be easily encoded as a linear constraint. We have a budget of $B, the price of X in the external market is PX, and the price of Y is PY. And we can buy any combination of these as long as it fits within our budget. Now, the next question is, how do we encode the quasi-concavity of the trading function as a constraint which is amenable to our optimization problem? So for this, we will go to another view of a CFMM trading function. We first define a spot price as the price offered for an infinitesimal trade. Then we can see that we can write the reserve amount X and Y in the pool as a function of the price that it is offering. That is the spot price that it is offering. And given any spot price P, we can define the liquidity at that spot price as dy over d log P. So basically, informally, what the liquidity is that the amount of Y in the pool which is available for market making when the price, the log of the price changes by a small amount around point P. I want to point out that this exact definition is not crucial for the results to hold. For example, we could have used dy over dp, or we could have used dx over dp, or something like that. The expressions would look different, but the core results will still hold. So coming back to our optimization problem, the quasi-concavity of the trading function can simply be encoded as non-negativity of the liquidity. So this introduces an infinite number of decision variables to our problem. That is, there is a decision variable, the liquidity at price point P for every positive price. The liquidity being non-negative implies that the level sets of the trading function are convex. Now we come to the next constraint, that is the amount of Y should not be negative. So to go about defining this constraint as a function of the liquidity, we first want to use the fact that the CFMM is a path-independent trading strategy. So we take a price process, assuming that the price continuously decreases from the initial price P0 and goes up to 0. In this case, the CFMM will sell all of the Y that it holds. So this case will give us the condition that the CFMM should not be able to sell more Y than it started with. So if we integrate LP over P over the price interval 0 to P0, then this exactly gives the amount of Y that the CFMM will sell. And we can see that this encodes the non-negativity of Y as a function of the liquidity of the CFMM pool. The next constraint is that the amount of X should not be negative. And for that, we take the other sort of price movement in which the price increases from P0 and goes all the way up to infinity. In this case, the CFMM will end up selling all of the X that it holds. And By integrating LP over P square from price P0 to infinity, we can encode the constraint that the CFMM should not be able to sell more X than it started with. I want to point out that there is a bit of difference between these two expressions. In the first expression, we are integrating LP over P, and the other we are integrating LP over P square. This is just an artifact of the, this is just because we define the liquidity in terms of Y and not in terms of X. So it's actually the same thing. Now we come to the next important thing, that what is the objective function? For defining the objective function, we need a model of the trades that happen on the CFMM. So this is our trade model. We first assume that there exists a common knowledge true price of X and Y, or let us say the price of X in terms of Y, which we denote by P. And we assume that there are two types of trades. One are the arbitrage trades, which correct the price on the CFMM, and the other are regular trades, which may be done for intrinsic reasons for the traders. We define a trade success such that a trade buying X with a maximum slippage epsilon and price P succeeds if the CFMM can offer a price P prime at most 1 plus epsilon times P. An equivalent definition can be given for trades selling X. We assume in this work that all regular trades have the same maximum slippage epsilon. This assumption is just to make the analysis a little bit easier. We also assume that the regular trades for buying versus selling X are balanced in expectation. That is, apart from the arbitrage trades, the regular traders do not in net accumulate a position in X or Y. So with this trade model, this model may not be perfect, but it captures important insights, and this will give us a lot of insight into the results as well. So one important metric that we want to capture is the rate of the trades that can be successfully fulfilled by the CFMM. Intuitively, we can think that higher liquidity at a price point would ensure that more trades would go through. By trade failure, I mean a trade is failing if the slippage offered is more than epsilon. So we have a theorem that for balanced trade patterns, that is when the amount of X and Y, the amount of X bought versus sold is balanced. And for small trades of size K, the trades have to be small with respect to the size of the pool. At a price P, the probability of the trade failure is approximately K over 2 times log 1 plus epsilon times LP. So the probability that a trade fails increases with the size of the trade, which is what we would expect. And the probability of a trade failure decreases with the slippage that the trader is willing to accept. Also, the probability of trade failure decreases with the liquidity at the price point. The proof of this theorem is based on the stationary distribution of the CFMM state when it reaches the price P. The important takeaway from this result is that the trade failure rate is a convex function of the liquidity at each price point. Now, using the results from the trade failure rate, we can define the trading fees that is collected by the CFMM. So the CFMM naturally collects fees on the trades that succeed. Let us say the rate of trade arrivals of unit size trades is R of P. So there is an assumption hidden here. We assume that the rate of trade arrivals is independent of the liquidity, which may not be the best assumption, but in this framework we can also take rates which increase with the liquidity, but they have to be concave and slowly increasing for this framework to work. For simplicity of presentation, I'm assuming that the rate is independent of the liquidity. The fees per unit is gamma, and the rate of fees collection is given by this expression, gamma R times the probability of trade succeeding. The important takeaway from this slide is that the revenue is a concave function of liquidity at each price. And we would like to maximize the revenue, and maximizing concave functions is easy. Now comes another important ingredient in our framework, which is CFMM's loss. So the instantaneous LVR is defined as the volatility of the price pair, the price in the asset pair, times P square times dx over dp. So by simple algebraic computation, we can see that negative of p square dx over dp is exactly LP as we defined it before. So the instantaneous LVR is sigma square LP. The total LVR is computed by integrating the instantaneous LVR over a period of time. So we can use our definition of liquidity in that expression. Another important metric is the divergence loss. For the divergence loss, we want to define a final price when the liquidity provider liquidates their position. Let us say that price is Px and Py, and P hat is the ratio. The value of the pool at this point is Px times the amount of X that the pool holds, plus Py times the amount of Y that the pool holds. We can write this expression also in terms of the liquidity, and it is given by this expression above. So while defining the constraints, we saw how the amount of X in the pool can be given as an integration of the liquidity from a given price up to infinity, and the amount of Y in the pool can be given as an integration from price 0 to P hat. The divergence loss is simply the final value of the pool minus the initial value of the pool. So in this case, this is V minus B, and B is the amount of dollars that the liquidity provider invested. So the important takeaway is that both the LVR and the divergence loss are linear in the liquidity at each price. Now, what objective should we choose? So we do not answer that question, what is the best objective to choose. We give an optimization framework, and the liquidity provider can choose their own objective function, which could be linear combinations of the expected fees revenue, or the efficiency, or the expected cost. And all of these natural objective functions become combinations of LP and 1 over LP. Now, the next important question in our framework is that what is this expectation that we are taking over? For that, we need to assume that the liquidity provider has some model for the price movements of the underlying assets relative to a numeraire. This model of price movements will induce, at a given future point of time, a joint distribution on the prices of X and Y. However, a liquidity provider will not make a market at a single point of time in the future. They will want to take an integration over the entire time duration in which they are entering the LP position. So for this, we again take advantage of the fact that CFMs are path independent, and we can easily integrate over the price that is going to be realized in the future. And the expectation over a time horizon is equivalent to a different joint distribution. So for deriving this sort of a belief function, I take the example of the Black-Scholes model. Let us say an LP wants to use a curve for time is equal to time 0 to capital T, and they assume that the prices of X and Y will independently follow a geometric Brownian motion. The variances in the prices will be sigma X and sigma Y, and the drifts may be mu X and mu Y. The rate of time discounting is lambda. By linearity of expectation, the LP can collapse the entire price dynamics into one single prior function. So they can take the integration from time t is equal to 0 to capital T with time discounting. They can take the priors on each time in the future, and they can find the belief function that they are going to use in the optimization framework. So now, coming back, now plugging everything together, let's say we take an example of maximizing the net profit. The objective function will look like something like the expected fees that is collected minus the loss. I'm omitting the expression for the loss here because it will be too cumbersome to parse, but it is linear in LP as we saw earlier. The interesting thing is that now this program is a convex program, and we have a decision variable LP for all real P. That is, we have an infinite number of decision variables, but thankfully we can handle that analytically. The constraints are linear in LP, and the objective is the maximization of a concave program. Now, from convex optimization theory, we can see that the KKT conditions often reveal important things about the problem itself. In our problem as well, the KKT conditions are analytically tractable, and they give a closed form map from the choice of trading function to the joint distributions that give the belief of the liquidity provider. So this can help us understand what people are doing in practice. So one canonical choice of the trading function is the constant product CFMM, which was used, for example, by Uniswap v2. If maximizing the fee's revenue without accounting for the loss, and if the prices of X and Y are thought to be independent and uniformly distributed on a unit square, then the constant product CFMM is the optimal choice. So this is informally like a one-size-fits-all CFMM. We can take a few more examples. So if the LP believes that, for balancer, let us say if the LP believes that X is going to be more valuable in the future than Y, then they will choose a value of alpha greater than 1. And the balancer CFMM is actually the optimal choice for them. If the LP believes that the price of X and Y are more likely to be similar to each other rather than independent, then the CFMM implied by the LMSR rule would be optimal for them. So I would like to summarize that in this work, we provide a framework for potential liquidity providers to decide which CFMM, if any, is going to be the best choice for them for the market making. And this framework also explains some of the intuitions behind the widely used CFMM trading functions. Thank you so much.
The questions, you can line up at the microphones here and here. I want to ask about the practical implications, and maybe taking a specific example. You mentioned, so if you go back to the slide, oh, actually, you're on the computer. The slide with the LMSR. So you're saying LMSR is a good fit if the expectation is that the prices of, say, like a yes and a no share traded against each other are going to be similar?
Yeah.
I guess, so usually if LMSR is used for prediction markets, I think like the one thing we know about prediction markets generally is actually that they're going to resolve to one being worth the price of 1 and one being worth the price of 0. In a lot of cases, I think prediction markets tend, at the end of their lives, to actually go toward one of those prices. So why would LMSR be a good fit for prediction markets if that's the belief function?
Yeah, that's a good question, and I'm not entirely sure about this. Yeah.
Sure. Yeah, Alex.
I wasn't sure what assumption you make about the fees in this model. So do arbitrageurs pay fees or do they not? Because if they don't pay fees, then basically LPs cannot capture any value from the uninformed flow. If there's an uninformed transaction, it pushes the price somewhere, and then arbitrageurs will kind of backrun it, and get the full profit. And so LPs don't get anything. But then,
Yeah, thank you. So in this work, we assume that the bulk of the trading volume is going to be from uninformed traders. So for the fees, we only capture for the expression of the fees, we only capture that part of the fees. And for the fees that is coming from the arbitrages, that we omit here, but I agree with you that that's also an important thing to capture.
yes, I think it would be great if you could charge a different fee to the two different flows, right, to arbitrageurs. But I'm not sure that we know enough about how to do it. And then another thing that I just want to point out quickly is that in the previous paper that we saw today, there is a result saying that the loss depends on the liquidity that is available sort of on the margin, but the shape doesn't actually matter that much. If I read it correctly, I don't want to misrepresent what the paper is saying. So when you take fees into account, I wonder if the results will eventually, the shape is going to matter as much as it does in the current setup where the fees are symmetric. But I guess it's a topic for future research.
Yeah, so these two models are kind of incomparable in that sense. So we assume here that the arbitrageurs can exactly correct the price of the CFMM. We do not have that no trade region in this model where the arbitrageurs will have no incentive to trade. So yeah, that's an interesting thing for an extension of this work. Thank you.
Thanks, Mahag. Is Joseph Poon here? Joseph Poon is here. Hello. What's that? Yes. All right. So next up, we will give your computer. The slides. They've got the slides. Yeah. So next up, we will have Joseph Foon and Chris Jeffries. So Joseph is one of the creators of both Lightning and Plasma, and this is the first time that they are presenting publicly Warp, an algorithm, or what is it?
It's
A decentralized exchange, efficient decentralized exchange algorithm.
Yeah, awesome. You got to look out. Hi, everyone. We're here to present an on-chain matching engine, and there's been no method in the blockchain to directly match buyers and sellers completely on-chain without capital-efficient liquidity pools with high price precision. And we needed this for an on-chain matching engine in order to make a decentralized cross-chain wrapping system for UTXO assets. That's not what we're presenting here today, but it's, I think the need in this space for a direct matching engine on-chain that supports things like the EVM to be critical in this space. And we think there's a broad applicability, and there are, in our construction has gas cost comparable with AMMs on the EVM. So I think it's important to go through what we're talking about through the historical narrative, because I think that'll inform what we're trying to solve, and also hopefully it gives some intuitions when we sort of present the solution, and maybe it's sort of like directionally as we explain the history, you can sort of see directionally where we're headed anyway. Now, there's in a normal centralized exchange, equities markets, whatever it may be, you're going to have these things called order books, and if you wanted to, let's say, buy 18 bags of apples, we all could see what should happen, right? You go to Wally, you fill his availability, and then you fill at 11 partially, right? That's easy to see for us, but there's actually not an easy algorithm to do this on-chain because of gas constraints. Because imagine if instead of a single order, sell order at $10, imagine if there's hundreds of these at hundreds of prices, like $10.01, $10.02. You're now doing read records on hundreds and hundreds of orders potentially at different prices, at different price levels, and at different price individually, all the way up to $11. It could be like hundreds or even thousands, right? And on the blockchain, you need constraints, capacity constraints. Otherwise, there's denial of service attacks. And that creates significant issues. So this gas limit problem is fundamental to what we're going to be looking at. So what are some early approaches? EtherDelta, they traded off price-time priority. And price-time priority means if you put in an order at a higher price, you get filled first. If you put in an order later than someone else, you're going to get filled later than them. EtherDelta was it's sort of like Craigslist or Facebook Marketplace. You throw the orders out there, it sort of goes, and then who knows what you're getting kind of thing in terms of who's getting it and in what order. And then there was a way to sort of abstract that complexity, that linear complexity away by running a central server. Now you are trusting the central server for matching, who knows what they're doing, but the general idea is that there's some centralized point of trust on the matching itself. Now you're not giving custody to them, but there is this process of that, and to this day, today you sort of see this in the RFQ constructs. And what we think is very clever was the Gnosis Dutch auction. The Dutch auction construction was, there was a time decay, and if you fill it earlier, you pay a higher price, or a higher price gets set. The trade-off is, to do price discovery along something granular, it's probably going to take, maybe potentially days or weeks in order to do price discovery. But it is fully on-chain, and it is a way to do an auction system. So AMMs. Now, I'm sure most of us are familiar with AMMs, but I think what we want to point out here is that the kernel of AMMs is that you're providing a single price. By aggregating your orders together into a single liquidity provider, this problem that we had with these many different orders, well, you're just dealing with one guy, one record on chain. And you only need to fill one price. The trade-off, as we know, there's high capital requirements, and you put in a lot of money, there's impermanent loss. Concentrated liquidity, adjusting the curve definitely helps significantly with that. But it doesn't eliminate the problem space. You still need to be supplying, $1,000 of X and $1,000 of Y to do these LP constructions. And auctions are very challenging, and auctions are necessary in order to do decentralized, fully decentralized oracles without, validators and trusted counterparties for crypto assets. And it'll continue to be useful and superior for certain applications, but we're strictly looking at, an order matching type of DEX problem here. What do we have today? So today, in terms of if you want to do, tight prices in DeFi, you have RFQs. You're essentially trusting some RFQ server to do this matching, and they're not really doing matching, they're more doing quotations, but it's the same general idea. They give you a price, you execute on it. If you choose to, you broadcast it on chain. People deliver prices to the RFQs. So there's some issues here with RFQs. It's a trusted intermediary. A sizable proportion of DeFi is now becoming RFQs. You give it a couple more years at the current trajectory, they're going to dominate, right? Like they just have the tightest spreads compared to other things on chain right now. Because they don't have to deal with these fee constructions and these other things, they're able to do it, right? And you have basically what amounts to be black box, centralized, opaque providers. And to give you a color on what we're talking about here, some RFQ providers in their docs, this is publicly disclosed, tell you that if you are supplying liquidity on RFQs, you can differentiate your users based on what website they're using. So if you go to an RFQ and get a quotation from website A, you can give them a different price than if they went to you on website B. So it's already self-selective and not an open market. But we think there's an opportunity here. I think the landscape has changed for on-chain matching. We now have smart contract L2s where we didn't before. Capacity has ballooned. There's so many L1s and L2s where we're only using maybe 1% of the available capacity, maybe less. And with more engineering, more work that everyone in this audience is participating in, or many of us, that I think capacity is going to increase even more with these roll-ups and ZK constructions and everything in the future. And I think we have sufficiently fast block times to start working on matching engines. And I think there's a lot of cool continued innovations ahead. So our contribution that we're presenting today is about a logarithmic matching engine. And it's important to find the problem of what we're looking at here, because I think when you see the problem, you can start to see where the solutions lie, right? The problem is fundamentally that you are filling many different prices, and that's a linear complexity problem. There could be thousands of orders with very, very small orders, because we're doing things on chain and we're dealing with an adversarial setting. Someone could fill, anywhere from, you want to fill from $10 to $11, there could be thousands of prices in there. So you could trade that off with precision, right? So you could say, okay, we've got an order book, we only have 10 different prices, maybe, and we only allow a certain amount of orders. Yeah, you could solve the problem that way, but that's not the experience that you have with traditional exchanges. That's not what people expect, and that's not a true matching engine at that point. So we constructed an EVM optimized radix tree data structure compatible with the EVM. The EVM has incredible constraints. 32 byte keys, 32 byte values. Fitting everything in 32 byte values is not easy, and fitting the data structure in which minimizes reads and writes is highly complex. Intermediate nodes, and here's the other insight, which is intermediate nodes, which JJ will be getting into soon, is they're going to contain both the child node's values and quantities. And that allows for true limit order books, auctions, and et cetera on chain, where all the executions happen inside the smart contract, all the matching happens inside the smart contract, and all the storage is in the smart contract. There are no validators, there's no cranks, it's happening on chain. The person that deployed the contract can walk away, shut off all their computers, it runs. It does its thing. We're talking about extremely high price precision. And this is the important point, because price precision is the problem that is being solved. You can abstract it away with low precision. But if you want 1/10 of a basis points, that's a much bigger challenge, and that's sort of what people use in the Forex market. This is the standard. And we have a construction which is fully time-bound in the worst case at several 100,000 gas. It's very efficient, usually less than 200,000 gas. The worst case should never happen. We're talking about potentially trillions of orders or billions of orders that persist over many years that never get filled. It should never happen. But in the average realistic case, we're looking at below 200,000 gas. It's comparable to AMMs. Most popular AMMs are around 150 to 200. Some do a little bit lower, but it's somewhere in that range. We have an implementation in both Solidity Assembly and coming with C, which should be WASM capable.
Okay, so I'd like to quickly go over the problem. So the problem, as Joseph mentioned, is there's a lot of linear complexity going on in order books and matching engines. So problem, many orders can be placed at the same price, and one order may potentially fill an infinite number of orders or prices. And linear complexity in a decentralized system where n is unbounded is absolutely unacceptable. You can't do that on a blockchain. So the most well-known matching engines, at least the public ones, don't attempt to even address this problem. So our basic approach is to decouple matching and execution. And historically, these were considered the same thing. Matching and execution would happen at the same time. But by doing this, we can have synchronous matching and asynchronous execution. I'm going to explain what that means later. But this means that we can have log n matching. But first, I'm going to go over some of the traditional data structures that are usually used for order books and matching engines. So typically, the most traditional design that we could find, there's actually very little literature on this subject. A lot of these matching engines are trade secrets from centralized exchanges and whatnot. So, but the most traditional design is you use a self-balancing binary search tree or a radix tree. And the nodes are prices. And in each node, you have a linked list of orders. So like it has some decent properties, right? You have log n insertion, and you can optimize this and have O1 insertion if price already exists. You have O1 cancel, price lookup. But the big problem is like you have ON matching complexity. So this design first reached a wide audience as the result of now a frequently referenced blog post from 2011. It's like if you search Stack Overflow, if you search Google, like how do I write an order book, everybody references this blog post, which uses this design, which basically looks like this. So you have a tree, and each node in the tree is a price. And they point to within each node is a linked list of orders. A doubly linked list, right? So you get O1 insertion, O1 removal. But the problem is if you try to match, right? You have to iterate down this tree, iterate through these linked lists, go through every order and every price that the order satisfies. So you have this crazy complexity all over the place. And this is why this cannot be used on a decentralized system. So the other approach, which came around the same time, was the QuantCup approach. And around the same time, there was what was called the QuantCup.org contest, which was a contest to see who could write the fastest matching engine in C. And this was a minor improvement over the tree-based approach because it utilized a pre-allocated array of price points. So that's a little bit better than a tree because you get better caching properties, right? Because you're not chasing pointers all around this tree. You always have O1 insertion because you're always just going directly to a price bucket, which has a doubly linked list. But again, the problem is you have ON matching complexity. You have OM space complexity, where M is the number of prices. You have to pre-allocate this giant array. And there's a lot of limitations there. But it won the QuantCup.org contest, so this is another frequently cited design. And basically looks like this. So it's very similar, except that top row is an array. And each item there is a bucket in an array, which points to a linked list of orders. So it looks very similar to what we saw before. So our approach is a little bit different. I'm going to be showing you an example of our tree. In reality, we use a base 2 radix tree. But for simplicity's sake, I'm going to make it a base 10 tree so that's more understandable for everyone here. So the idea is you utilize a radix tree of prices and orders. So everything is the same thing, basically. So we have a decrementing, so we have a price. When you insert an order, you have a price. And we have a decrementing counter, which creates a decremented nonce. And you append that nonce to the price to create a path down the tree for insertion. And that's basically how you insert into this radix tree. That's what the path is. The idea for the decrementing nonce is you obviously want it to be higher for earlier orders to maintain price time priority, because you want earlier orders to go on the right side of the tree, because as you'll see, we're always going to be matching from the right. So like Joseph mentioned a little bit, so leaf nodes maintain 2 extra fields, quantity and value. Okay, so I'm going to need to define some things. So like quantity is so we have an ETH USD pair. Quantity is the left-hand side of the pair, or the base in quote, right? That's probably what a lot of people are familiar with. I'm going to say left-hand side, right-hand side, because I find it more understandable. So we have quantity, which is left-hand side of the pair, ETH, and price, which is the right-hand side of the pair, USD, and value, which is price times quantity, and the result is in USD. So internal nodes maintain some quantity and some value, where each of those fields are the sums of their children's respective values, right? So this tree basically has O log n for every operation, including matching. And execution is decoupled from matching. So execution is offloaded onto the traders themselves. And I'll maybe explain more of that later. But now I'm going to go through what an insertion into this tree looks like. Bear with me because these slides can get a little bit complicated. Okay, so we have an ETH USD pair. We want to insert a bid for 1 ETH at $17.99. That's our root. So we have a counter, which decrements. We append it to the price, so we have 1799:9. That's our root. So our path is 1799:9. Our quantity is 1 ETH, and our value is 1799 because obviously 1 times 1799 is 1799. So what happens when we insert again? New bid comes in. Oh, also, sorry. Assume that the ask tree, this is a bid tree. Assume that the ask tree is empty. Because these trees, when these orders comes in, they sort of like eat away at the opposite tree. But right now we're assuming that the ask tree is completely empty and there's only bids coming into the order book. So we insert another bid, 0.5 ETH at 1800. So there's a collision here, right? They both start with a 1 digit, so there's a split that happens. And now our root node has a prefix digit of 1. And the new bid that came in has a higher price. The nonce doesn't really matter right now, so it goes on the right. I'm sure you're all familiar with radix trees. The only big difference here is everything is getting summed up. All these quantities and values are getting summed up. And you can see the rightmost leaf has quantity of 0.5 ETH, value of $900 because the price is $1,800. So insert again, same thing, counter decrements. This goes on the left, it's a low price. Insert again. So what we're doing is we're building a tree so we can match against it, right? So we insert again. Again, all the sums still apply. We go down the right side this time. It's a high price. Everything gets summed up to the root. We insert again. So this one's interesting, right? Because we go left, right, left. There's a split that happens, an internal node that's created. Because now there's 2 orders at the same price, right? So if you look at the bottom left green node, which is a leaf, 1799:5 next to 1799:9, right? The :9, that nonce makes it go on the right side of the tree. Remember, we're always going to be matching from the right. So because the order to the right of the green leaf came in first, it gets a higher nonce, so it's going to get matched first, even though they're at the same price. And same thing here, right? So new node comes in, 2.5 ETH at 1802. And there's already an order at there's already a bid at 1802, but this one has a lower nonce, so it's going to get matched. It's going to get matched later, depending on what happens. So this is the final state of the tree, and now we're going to start inserting asks, and this is where the magic happens. This is where we're going to see the logarithmic behavior of our algorithm. Ask comes in for 4.2 ETH at $1,800. Now remember, we're always going to go right down this tree. So we go right, and then we hit the red node. And we notice that the red node, its path, not its price, its path, is higher than the asking price, right? So this entire subtree can satisfy this order. There may be 1 million orders, 1 million nodes underneath the red node, and we do not need to traverse them at all. All we need to do is delete that subtree and promote the left node. So we just technically matched. In this example, obviously, there's 2 orders there. There's 2 leaves. But pretend there were 1 million. We can match 1 million orders just by deleting that node. And then we tally up the value in an accumulator, the sum value, and then we sort of decrement the quantity that we're matching against. So this is what's going to happen. So the blue node gets promoted, and it takes that old internal node's place. We deleted the subtree in red, okay? So we didn't have to traverse either of the nodes under the red node. So once we promote this node, what happens is it's a partial fill. There's 0.3 ETH left over as a result of this order. Okay, so let's run through another ask again. And again, these slides take a while to grok, but I think you'll get it if you stick with me here. So another ask comes in. Again, we go right. This ask is for 1788 and a quantity of 4.55 ETH. We go right, we hit a leaf. We see that it's $1,800, so it's greater than the asking price, so it satisfies the ask. Again, we're going to promote the left node, so it looks like this. So we're promoting, blue node becomes the root, then we start going down the blue node again. Again, we're always going right. And this is what happens. So we go right again, we hit the right node, and we notice that the prefix digits 179 are greater than 178. So again, this entire subtree can just be deleted. And we can take the sum quantity and the sum value and tally them up. And then again, we promote the left node, and this is what we're left with. A partial fill, that's our root. That's the final state of the tree. Okay, so what's happening here? So the idea is that the seller's order is consuming as much as possible of the bid tree. And now the protocol knows exactly how much USD the seller gets and how much ETH they need to spend to get it. Any leftover ETH is going to go on the other side of the book. It's going to go into the ask tree as a resting order. So, and the ask tree is basically the inversion of the bid tree, right? It's the same exact behavior, it's just flipped. So now traders, like I said, there's asynchronous execution, right? So all we do is the matching. The traders actually need to execute their orders by claiming it. And the idea is they can go to claim their order, and you might be asking, well, how could they claim their order if it's deleted from the tree? And the idea is they have an ID for the order, which is the path down the tree, right? It's the price and the nonce and the side of the book, sort of. So what they can do is they can hit the contract and say, by the way, this contract basically only has 2 functions. It has order and cancel and claim are basically the same operation. So the idea is I want to claim my filled order. So what it does is it hits a separate storage record to make sure that order exists, and then it traverses down the tree. If the order is not present in the tree, that order is completely filled. If it is present in the tree, it's either partially filled or just not filled at all. It just like went on the book. and then they get whatever value was in there, and that would be a cancel, right? So claim and cancel are the exact same operation. So it's a very elegant system in that you only need 2 operations. You only need order and cancel. That's it. It's 2 operations. So like I said, our implementation on the EVM differs a lot from the examples I showed you. It's not base 10, it's base 2. Just because base 2 radix trees have a lot of nice properties. It's a lot easier to work with base 2 radix trees on the EVM because of all of the EVM's constraints. You know, you wouldn't want to use like some like base 16 radix tree, or just, and also we were writing this in Yule, which is how we got it so highly gas optimized. So the idea with our EVM implementation is that we have a 24-bit price, 40-bit nonce. So that gives you 2 to the 24 different prices, and that gives you about 1 trillion orders that can exist in one pair. It's so high, you'll probably never hit it. In our randomized benchmarks, the median gas usage for placing a limit order is around 120K. But if we exclude orders that fill immediately, and we only include orders which hit both sides of the book, the median gas usage jumps up to about 150K. Claims and cancels can be batched. So a cancel is normally around like, a claim or cancel is normally around like 70K gas. But if you batch them, and again, it depends on like the batch size. Like if you're, obviously if you're batching like 100 orders, the median gas usage drops down to like 25K gas per order cancel. And the reason for this is like when you're getting like sort of like a slight gas refund by deleting stuff, and also like you're also hitting, you're repeatedly hitting like the same storage slots in the contract. So those are all hot. So it's like batching cancels can be very efficient. And to our knowledge, this is the first on-chain data structure which resolved a linear complexity problem, right? So this is the first truly logarithmic matching engine that can actually be used in a decentralized system, to our knowledge. So you might be wondering, you might be thinking, well, this is a radix tree. Eventually, it'll get fully saturated, right? And it'll have to do all these traversals just to get down all the price digits, and it'll have to do all this summing back up the tree when it inserts, and it'll have to reduce the sums when it matches, and so there's a possible optimization here that we're working on, and the idea is that the rightmost branch of the tree doesn't include its right node's sums. So the idea is that most often in an order book, people are placing orders near the top of the book, right? So that means they're always going to go on the right side of the tree. So if we exploit this fact, and we make it so that in the rightmost branch, the nodes don't include the sums of their right children, we can avoid all that summing during insertion and matching. And we believe, we don't have this optimization working quite yet, but we believe in the most typical case, the most typical orders could get around 100K gas usage, maybe even less than that. And Joseph, you take it from here.
Yeah. So like we are doing a high-level explanation. Like we said, like there's some changes with regards to how the radix tree is, like technically it's the 2 childs that are green, but it is what it is. So in terms of implications, we think it's useful for a wide range of DeFi applications, not just decentralized exchange. We need it as an auction scheme as well. An auction scheme is very interesting because like think about the normal DeFi, a common DeFi use case of, some liquidation of some underlying asset, and normally they use some oracle and then they sell it on the pricing mechanism in order to do that distribution. That oracle can get manipulated, as we saw with Mango. Instead, in order to reduce the potential for manipulation, what you could do is this thing that's getting liquidated, you throw it into an auction, people bid on it, people can arbitrage it out with other exchanges, and that's a lot harder to manipulate because if you put in a low price, someone's going to put in a higher price, right? Like, it's very hard to do right now to do an auction scheme of like a large asset with many different bidders with small amounts because functionally you need an order book. You need an on-chain order book. And I think it can provide, as a result, an alternative to the composability design pattern. And composability, oftentimes you're hitting other contracts in order to fulfill whatever you're looking to do. And maybe you could just auction whatever it is that you need, and that you leave it up to market makers to do this composability functionality. AMMs inherently, due to impermanent loss, have some percentage costs. And they need to account for impermanent loss. We think that market makers basically are capturing the bid-ask spread under this construction, and maybe that can tighten the competitiveness in this space with regards to centralized exchanges, RFQs, and things like that. So what are the opportunities here? I think it brings about when you can do an on-chain order book. I think we can do a new round of L2 innovation where, if you think about it, with a lot of these roll-up constructions, the primary cost being borne is the cost of the data availability on the L1. So you take a transaction, you broadcast the call data on L1, or it gets bucketed together and broadcasted on L1. And that would likely require, but maybe instead, you flash the orders on the L2, and it's only when it matches, when an order gets filled or partially filled, that you even need to prove data availability. Because if an order gets issued and canceled on an L2, why do you really need to prove anything? Like, no money has really changed hands. And that allows you to really reach scale where you can issue maybe like an incredible amount of orders per second, and a certain percentage gets filled, and those get committed on L1s. Now, this probably requires some opcodes and changes on the L2s, but it's theoretically possible, right? I think you could, because you could do commit reveal schemes, you could commit to something and then say, okay, I actually did the order at this price and do it at a later date. I think it becomes interesting and necessary for these types of things. What I think is really promising with this is because we have bounded complexity, specifically it's a tree that has a depth of 64, all the other order matching algorithms out there that are published have linear complexity, i.e. infinite, basically, complexity, where, near infinite, where at each price you can fill each possible price. And that's a lot of possible different prices. How are you gonna unroll that loop, right? With this, you could have a 64 deep loop, you unroll it, and then you may be able to do interesting things like ZK constructions off of this to build a true central limit order book with a ZK construction. So I think, when we think about we're building, if we have an on-chain order book, if us as a community, if we have this as an algorithm, we could just broadcast an order. It hits a full node that either you run, at home or, in some data center, and you're doing the execution on your computer, or a computer that you authorize. You're doing the matching on your computer. You're doing all the data is on your computer. All the data gets broadcast everywhere together. That's very different than centralized exchanges, equities, like the New York Stock Exchange, NASDAQ. You're hitting some server. And this is a construction where you have everybody computing everything together. And I think that gives us an opportunity to explore new avenues and gives us the ability possibly to see, to show traditional markets what the opportunities are. So we have an EVM Solidity assembly version, also known as Yule. We're releasing around mid to late September 2023 in order to maybe see if the optimization is possible and also do some code review. Yeah, we're definitely looking for code and technical comment on this. Yeah, and we'd be honored to have your review on this. Yeah, thank you so much.
Thank you.
I have a couple questions if people want to line up at that mic and that mic over there. So I think it's very impressive what you've done to reduce the cost of execution, but if you still have the cost of placing orders and canceling orders and claiming orders linear, the whole system is still linear in the linear gas costs and the number of orders, right?
Yes. So the problem is not necessarily the gas costs in terms of the fact that, well, there are concerns with regards to that, but the order issuance in order to insert an order is bounded by because there is that depth. So functionally, like if it costs some n amount of gas, let's say it's like 120K in order to do an insert, that's not infinity, right? The problem is principally with batching, which is infinity.
But it is still proportional to the number of orders that are being placed.
Oh, definitely.
Yeah,
We don't have a
execution.
magic system where you can insert an order.
matching is log n.
So you can't insert 1 billion orders and it all fits in a block. That's not possible. Yeah.
On an AMM, because orders automatically flip when they're crossed, and because you can place orders across a whole range, you don't have costs that are proportional to either the number of prices you're placing orders at or the number of times you get crossed.
That
So
is
there's still sort of a different complexity class in that.
Yes. But we're presuming that the cost of insertion is going to be comparable. And additionally, there is this question of, okay, if you have a lot of insertions and cancels on this book, what does that mean? And that's a matter of the spread, right? But in addition, we think with L2s and these new constructions, you could perhaps issue an order on L2, do a cancellation, and it doesn't really bear any real world, well, not significant real world costs.
First of all, thank you very much, guys. Brilliant presentation. I have good news, I have bad news. Good news, I can confirm it does work in practice in the real exchange. The bad news, we run the similar model for about a year now. At ZKX, we separate the execution from batching and matching. The only massive issue in the real exchange is when you have mass automated trading strategies, the cost of order placement goes by order of magnitude. So in your optimization, you've proposed optimization within the one network. What we've seen so far, that in order to keep the cost down for the automated trading strategies, you have to separate execution and keep it, let's say, in our case, it's starting at L2, while matching and batching happens at L3. So maybe consider separation and isolation not in the way of just batching and matching and then execution, but in a different network as well. Because for us, it was the biggest issue with, we only charge fees for the orders that have been matched, but the mass value of orders are withdrawn before they're matched by the automated strategies. So for us, the answer was to just separate between L2 and L3. Maybe,
Yeah, I think the separation when it comes to L2 is relevant. What we're specifically talking about is a radix tree construction where the sum value is included.
Right, we're not claiming to have invented separating out matching and execution. Like, we are aware that that has been a thing, like that's a basic, and that's a basic pattern in a lot of smart contracts. Like, that whole claim pattern, right? You don't want the contract just automatically like sending things out. So, I mean.
And there is a follow-up for that. In your randomized strategy, you've tested 20,000 transactions. In our case, for some reason, which we're still trying to explore, when it goes about 150,000, it goes exponentially in terms of the cost.
That's what we're solving. That's specifically
That's the optimization we discussed? Yes.
Like we didn't put our contribution today as the separation of claims. This UTXO pattern of an output that you claim at a later time is a pattern that occurs, is a logical pattern for this type of stuff, and definitely we do believe other people have implemented that. It's specifically the radix construct, the keeping everything within 32 bytes, and the sum value that makes it logarithmic.
The matching algorithm.
But it's definitely working, so congrats.
Thank you.
Thank you.
Thank you.
One more question?
So I believe you developed this design with the sort of EVM model where all the computation is going on chain and all the traversals to find the match happen on chain. Other chains, they allow you to do all of that kind of computation to navigate through the tree and stuff in off-chain code without incurring any cost.
Right.
But then for the on-chain validators, you need to prove that wherever you ended up and whatever paths you kind of collected are the valid ones, and you're not kind of, you're not in the wrong part of the tree or whatever, right? How would your design change if you kind of were to lift your constraints in this way, right?
So we have these aggressive constraints because when you offload it to a centralized server, they could do things like censorship. They could preferentially execute with their friends.
Oh, sorry, I wasn't clear. What I meant was, I don't mean that you are trusting someone to do the navigation. What I mean is that the validators, all they care about is that, like in the UTXO model, right? You can say, I'm consuming this UTXO, that UTXO, that UTXO, which is great. It limits you from being able to traverse the entire global data structure because you're limited in the amount of information that you can provide to the transaction, right? But if your data structures in the UTXO model are constructed in a way where you can prove them, oh, I'm actually in the right side of the tree right now, and I'm consuming from it, right? Then you can, all you have to do is show that. You don't have to traverse the whole thing in the on-chain code, right? So how would your design change if you have the ability to just prove that you're in a particular side of your tree without having to traverse the tree in the on-chain kind of execution environment?
So we have this constraint for a reason. We have this constraint because you can, on that off-chain thing, manipulate things in terms of who gets into the tree itself. But if you relaxed it, obviously, you don't have this problem of, block size constraints. So,
Right.
the recommendation would be use more traditional methods.
Okay.
All right. Thanks very much, Joseph and JJ.
Thank you so much.
Thank you. This, now coming to the first break. Pick up again in 20 minutes with a session on mempool attack and defenses.
should talk with Aviv Zohar. So there are two Avivs, Aviv Yaish and Aviv Zohar.
Oh,
and
yeah.
they have recent attacks also on the mempool.
I see.
So I think it'd be good if you can talk with them.
Censorship.
Yeah.
Cool. Yeah, definitely.
Vitalik mentioned your deter papers.
Oh, cool. Yeah, definitely. Yeah, I will find him.
Funny because he said the gas code is a mess. And then
All right, everyone. We're about to start the next session, the second session, which will be on mempool security and denial of service attacks on the mempool. Please, take your seat. If you want to have conversations, please, move them to the hallway so that we can start the session. I'll wait 30 seconds. All right, welcome to the second session. My name is Joachim Neu. I'm a PhD student here at Stanford, and I'll be guiding you through the session. Our first speaker today is Yizhe Tang. Please come up on stage. Yizhe got his PhD from Georgia Tech and is now a professor at Syracuse University. And we're very excited to hear him talk about actually work in progress work, which is about comprehensive understanding of Ethereum mempool denial of service security. And the rules of the game are as usual. We have 25-minute talk and then 5 minutes for Q&A. If you have a question, please line up at the mic and then we'll call upon you. Have fun.
Yeah. Thank you, Johas, for the introduction. Good morning, everyone. A great pleasure to talk about Ethereum memory pool security. My name, as introduced, is Yizhe Tang. I'm an associate professor from Syracuse University. So this is joint work with my students, Yibo Wang, Kai Li, and Wang Ningding. So let me start with giving a quick recap on how transactions are handled in Ethereum blockchain. Let's say a Web3 client who want to send out the transaction to Ethereum blockchain. So the client will send the transaction to a blockchain P2P node. And nowadays, we know of the upgrade, Ethereum works on two different levels, execution layer and consensus layer. On the execution layer, the node will use a buffer buffer the transaction in a data structure called memory pool, and then it will propagate the transaction to reach the entire P2P network. Okay. And on the consensus layer, the node will retrieve transactions buffered in the memory pool to build and propose block. So once a new block, including the transaction, is proposed, it will be further propagated, validated, and then appended to the blockchain. So you can imagine in this pipeline, memory pool is a critical data structure. Okay? The denial of memory pool service will cause a global damage. So first, a block validator, given a denied memory pool service, a block validator will not be happy. because it will not be able to retrieve legitimate transactions from the memory pool, and it will be forced to produce empty blocks. In the long run, the block validators will lose the revenue from legitimate transaction fees, and they will probably lose the incentive in participating mining or block validation. There is an incident that occurred like 2 years ago. The memory pool service in Ethereum testnet was denied. And in this screenshot that we take from Etherscan, you can see the timeline goes like upwards. There are multiple blocks produced. So below the first red dotted line, we are looking at the 3 blocks produced prior to the attack. You can see prior to the attack, the blocks include 51 transactions, 46 transactions, 77 transactions per block. So that's the regular, like a block utilization. And once the attack is mounted, the next 4 blocks, you can see there is only 1 transaction per block, 1 transaction per block, 0 transaction per block, and 1 transaction per block. After the attack ends, the utilization per block is resumed back to normal. So if we look at how much revenue the block validators receive, at the time it was miners receive. So during the attack, miner revenue decreased by 99%. So this is definitely something that block validators will not be happy about. On the other end, Web3 clients will not be happy about a denied memory pool service because they will not be able to transact. Their transactions, although sent out, will not be able to be included in the next blocks. So whatever DApp they participated in will fail. So based on this risk, we formulated the following threat, what we call asymmetric denial of Ethereum memory pool service. So in this threat model, attack client sends crafted transaction to a remote victim node's memory pool. Meanwhile, that victim node receive regular transactions sent out by the like a benign Web3 client. Okay? So the goal of the attacker is to make the memory pool under attack unable to buffer unconfirmed benign transactions from regular users or Web3 clients. Is this threat realistic or how practical this attack is? In order to do the memory pool denial of service, a baseline design is send transaction, spend transactions. So because in most Ethereum clients, memory pool admit transaction based on fee. The higher the fee is, the high priority transaction will be admitted to the memory pool. So an adversary, let's say a naive adversary, will just send a bunch of spend transactions at a high fee. The fees are higher than the fee of normal transactions. So normal transaction will be evicted. But this baseline design will not be very friendly to the attacker. It will cost quite a fortune for the attacker. And to some degree, it may not be as practical. A more realistic threat is what we call asymmetric memory pool DOS. In this case, we formulated that the attacker cost should be much lower than the damage on the victim side. More specifically, the fees of adversarial transactions will be lower than the fees of normal transactions. So today, the only known asymmetric DOS is the detail attack, which the result was published 2 years ago in Cybersecurity Conference CCS. And recently I come to notice there's another similar attack in the space. The detail attack follows a quite simple pattern in which the attacker sends out a bunch of invalid transactions, such as a future transaction in Ethereum, to evict normal transaction, pending transactions in the memory pool. Because it is the invalid transactions that are sent by the attacker, which are not included in the blockchain, so it doesn't cost the attacker anything, like a 0 Ether. But this pattern is quite easy to detect, and actually it is already fixed in the latest Ethereum clients, most leading Ethereum clients, as far as we know. So given this status quo, we pose the following like an open research problem. Are there any new and stealthy asymmetric memory pool DOS attack other than Dieter and other existing ones that can evade the existing defenses adopted in today's Ethereum clients? In this work, we approach this research problem from 2 different angles: automatic vulnerability discovery and security verification. So given an Ethereum client, we want to be able to find if this client is free of asymmetric DOS attack or not. If it is, we want to present a formal certification over that. If it is not, we want to be able to find a concrete functional counterexample. In other words, functional attack against the tested Ethereum client. So this is a work in progress, and in terms of approach, our motivating observation is the following. Finding asymmetric memory pool DOS is a safety checking problem. First, we formulate memory pool eviction safety property, among other things. Basically, the idea is if a memory pool is safe, then it means that the transaction fee in any reachable memory pool state should be lower bounded. If such a lower bound does not exist, it can be easily exploited. On top of that, we build a memory pool model. We build an explicit model of explicit memory pool state. And on top of that, we implement state transition rules by non-admission policies. This process currently is done manually. Okay? For instance, in our model, we build admission policy based on transaction fee. As I mentioned before, the higher the transaction fee is, the high priority transaction will be admitted. Also, we implement the defensive policies adopted in today's Ethereum clients that is intended to mitigate the detail attack. For instance, such a policy will prevent the eviction of valid transaction in the memory pool by any invalid transaction. So we implement the model and the safety property in TOA+, and we run the TLC model checker with the bounded iterations to find either violations or present a formal certification of system security, safety. So if a violation is found, we extend the model level error trace into concrete attacks, and then we validate the concrete attacks on real Ethereum clients. So using our automatic tool, we are able to rediscover deter attacks on older version of Ethereum clients. On top of that, we also are able to find 12 new memory pool DOS-related bugs. So on the table here, you can see so we report all the bugs to the Ethereum Foundation, which governs the development of different Ethereum clients, including Geth, Nethermind, Aragon, and others. So most of them get confirmed, and some of them get fixed. So today I'm going to talk about one specific example of the new memory pool DOS attack or bug that we discovered and recently get fixed in Ethereum client. So in this attack belongs to the category that we call turning-based eviction attack, and it belongs to the class of more stealthy attacks, in which the transactions are the adversarial transactions. In the beginning, it does not appear as an invalid transaction. It is a valid transaction, and then once it is admitted to the memory pool, it will be turned into invalid transactions. And such stealthy transactions can bypass the rule Ethereum clients use to propagate the transaction to other nodes. Okay, so in this sort of toy example, we are looking at two polys. On the left-hand side, we are looking at attack client. Right-hand side, we are looking at a toy memory pool, a victim memory pool of 2 slots. There are 2 accounts, Bob, the victim account, and Malloy, the adversarial account. In the beginning, the Malloy has 5 Ether in his account. For Ethereum, a transaction is essentially a droplet, a quadruplet. It consists of 4 fields: sender, nonce, price or fee, and value, the amount of Ether being transferred. So in this work, we don't consider the data field or the field related to smart contract execution. And in this initial state, we are looking at the 2 transactions sent out by Bob. So transaction 1 has nonce 1, and the transaction 2 has nonce 2. So they are consecutive transactions. Both are valid pending transactions. Price-wise, they are with 3 GWei, and the value are both 1 Ether being transferred. So this is Bob's benign transactions. And attacker node's goal is to evict these 2 transactions at no cost, or very low cost. So what attacker do is 2-step. First, the attacker sends out the 2 transactions, TX3 and 4. They are both sent by Malloy, the account controlled by the attacker. Again, the nonce-wise 1 and 2, the fee of Malloy's transactions are 4, slightly higher than Bob's transaction 3. And both transactions have Ether value 1. So if that transaction, these 2 transactions are sent to the memory pool, TX3 and 4 will be admitted to the memory pool because 4 is higher than 3. So if we take a pause at this sort of snapshot and look at how the attack goes, at this point, the DOS attack has caused the full damage to the victim transactions because Bob's 2 transactions, TX1 and 2, have already been evicted from the memory pool. Okay? So in other words, the damage caused by attack is 6, 3 plus 3. But in terms of the cost by the attacker, it is 8, because at this point, these 2 transactions are both valid transactions, and they will be included into the next block. So 4 plus 4, 8 is larger than 6. So this is like a successful attack, but it's not a successful asymmetric attack. So what the attack wants to do is to lower down his cost. And this comes to the second step, in which attacker send TX5, a transaction that we call a turning transaction. TX5 has the same nonce with TX3, but the price-wise is higher. So it's a 5 GWei, higher than 4 GWei. value is 5 Ether instead of 1 Ether. Okay? So the memory pool will admit this transaction because of two reasons. One, it has a higher transaction fee, 5 larger than 4. Second, this is a valid transaction because 5, this is, does not go beyond the balance that Molloy has. Okay? So if we forget about the transaction fee a little bit. Okay? So this transaction will be admitted to the memory pool. Before the admission, transaction 3 and 4 are both valid transactions. I use this green arrow to indicate both transaction fees will be charged by the blockchain. But once TX5 is admitted to the memory pool, replacing transaction 3, this is what the memory pool looks like. TX5 is still a valid transaction, but admission of TX5 will turn TX4 from a valid transaction to an overdraft transaction. And TX4 will become an invalid transaction if the block validator is going to select retrieve transaction from the memory pool at this point. It will not be able to validate the transaction or include it to the next block. So it decreased the attack cost from 8 to 5. So 5 is smaller, lower than 6. So this constituted a successful asymmetric DOS attack. So this is how things work at a high level in this Toy Story. We also validated this attack by running the attack against the real Ethereum clients. We run 3 nodes in a local network. Attack node sending adversarial transactions, victim validator node reading transaction from its own memory pool and validating the next block, and workload node that generate benign transactions. And so from this figure, you can see once the attack, so x-axis looks at the essentially timeline, y-axis looks at the cost of different transactions. Once the attack starts, blue lines and red lines drops immediately to 0. What that means is a blue line represents the cost of benign transactions in the memory pool under attack. And the red line represents the cost of adversarial transactions. Both lines are close to 0, which means the damage is maximized. Almost 100% of memory pool's content normal transactions are evicted, and the cost of adversarial transactions also becomes 0. Okay? We compare this attack with the case where things goes well without any attack in the green line. So you can see without attack, green line, the benign transaction fee do not drop. Okay? We also compare it with the baseline span transaction attack. So you can see in terms of cost is more than 3 orders of magnitude lower than the baseline high cost span transaction attack. So overall, we measure our result by 2 metrics, more than 99% of success rate and also very low ether cost per block. So we have reported this bug to Ethereum Foundation, and we also developed a security patch. Actually, in April this year, this what we call turning by eviction replacement bug are fixed in Geth security release version 1.11.4. Okay? We are working in progress for other asymmetric DOS vulnerabilities in Ethereum clients. We are grateful for the support and the collaboration with the Ethereum Foundation team in terms of bug bounty and also academic grant program. So in this talk, I introduced the problem of or the security attack asymmetric denial of memory pool service. Also talk about the open research problem in the space, given the defense that is already taken. Formulate the problem by safety checking problem, and also present discovered attacks with both toy examples and also how it works in practice. With that, thank you for your time, and I'm happy to take questions.
Okay, great. Yeah, if you have questions, please use one of the two mics that are in the room. I'm going to ask a question myself, which is, you know, you say this is work in progress, right, towards comprehensive understanding of DOS, you know, security and issues of the mempool. Where are we in this, you know, process of getting a comprehensive understanding? Where do you, you know, what are open problems? What are things that people should think about? What's your sentiment in terms of, you know, can we actually get this, like, you know, provably secure, or will this always remain at the level of heuristics, etc.?
Thank you for the question. This is also the question we have been actively working on, which means it is a hard problem. Is there an end in this arms race between attacker and the defense? For that, I want to say we envision this can be closed to some degree, but the fundamental challenge in this place is, in this problem space, is the trade-off between, let's say, validators' revenue optimization and the DOS security. So imagine if you don't care about the revenue at all, then you can implement a very simple FIFO queue, right? So I just, everything that is admitted into memory pool, I'm not going to allow any eviction or dropping of the transaction. It's like a locked over there. But that will not be very a good design if, if you want to optimize the revenue by the block validators. And once the eviction or other optimization, revenue optimization scheme is allowed, that will simultaneously create the risk of a DOS attack. So how things work out between these two ends, revenue optimization and the DOS attack, yeah, that's something we have been working on, and I think that's a sort of open problem in this space.
Okay, so it sounds like that it's only economically feasible if the attacker spends a lot of gas for these types of transactions. And then as like a follow-up question, it also means that in order to perform these attacks, you need to have searchers or nodes that understand the full state of the mempool, so you know what the ceiling is in terms of how much gas you should spend to evict certain other transactions, right?
Is it comment or question? Sorry.
My question is, you have to know what all the other transaction costs are in order to perform this attack economically, right?
Yeah, to some degree, yes. This is so. In the current design, at least in Ethereum, is memory pool content is publicly accessible. So it's an open membership network. So you just join the network, and you will the memory pool of your node will be populated. From there, you can sort of get a sense what the memory pool of other nodes in the network looks like. So yes, to your question, it's better you know what the content the memory pool holds before you send in an attack. I know there is like a private transaction in the space as well. So for that, this work does not apply to the private transactions.
Okay, thank you.
Thank you.
You talked about the trade-off between DOS security and revenue. Do you see that as like a fundamental trade-off? And if so, like what is the intuition behind that trade-off?
Yeah, thanks for the question. Yes, so to me, I do think that this is a fundamental trade-off because of the fundamental in the sense that the transaction model by Ethereum or other account-based blockchains. For instance, in this toy example, if you look at it, one of the vulnerability comes, the cause of the vulnerability comes from how the transactions are designed in Ethereum. Unlike the UTXO, where any account balance needs to be atomically spent in Ethereum, you don't have to atomically spend it. So you can split it into arbitrary number of pieces, and that's why we can send 2 transactions to spend this this account, and that's why we can do this to create this overdraft situation. So let's say in Bitcoin, I think this specific attack will not be applicable. So if you want to change, so that's one way you can change, and I think that's fundamental in terms of how Ethereum is designed, account-based blockchains. And also there are other things that pose challenges. If you think, so because of memory pool, you have to make a decision online. You cannot wait after you buffer it and then do the optimization or admission in the offline manner. So you don't know what happens in the future, right? So whether or not to admit this transaction, you can only rely on the past history. The thing in Ethereum is that different transactions, they can have inter-transaction dependency. The transaction that arrives later can turn the transaction that admitted earlier into invalid transaction. So that's, yeah, that's something that needs to be looked at if we want to fix this problem altogether.
Great.
Thank you.
Let's thank our speaker one more time.
Thank you.
Then we have our second speaker of the session set up. Okay, our second speaker of this session is Kai-Hua Chin, who is a final year PhD student at Imperial College London, advised by Arthur Gervais. And he works on blockchain security with an emphasis on DeFi security, and today he'll be talking about the blockchain imitation game.
Thanks for the introduction. Yeah, my name is Kai-Hua. I'm going to talk about the blockchain imitation game. This is a joint work with Stefanos, Lee, Benjamin, Don, and Arthur. So it's not a secret that millions and billions of US dollars are extracted from the blockchain and the decentralized finance ecosystem from different sources like arbitrage, liquidation, and different kinds of DeFi attacks. This is also known as MEV. The entities who go on hunt for these MEV opportunities are called MEV searchers. Now, to become a MEV searcher is not an easy job. Thinking of if you are an arbitrager, and what you need to do is you need to monitor the financial market 24/7, try to identify the price difference across different financial markets, and once you identify an arbitrage opportunity, you need to issue an MEV transaction swiftly to be the first one taking this opportunity. Because, you know, these profitable opportunities are typically one time. And also, as a searcher, you typically need a contract. Here we have example, we have MEV contract, we have arbitrage function, and there are in total 3 financial actions. First, we swap Ether to USDC, and swap back USDC to Ether, and finally sends back the profit to the transaction sender. And the purpose of such a customized smart contract is to ensure that these financial actions are atomic, meaning all the actions should succeed or fail altogether. Because you know you don't want your arbitrage to be interrupted by other blockchain transactions. Now, thinking of you are a lazy MEV searcher, you don't really want to monitor the financial market 24/7. You don't want to understand the complex trading rules of different DeFi protocols. You don't want to figure out how every smart contract works for these different DeFi protocols that are emerging every day. But you still are dreaming about making money out of this system. What would you do? Well, possible solution is you can become a copycat. You can literally copy the strategies from the others without thinking of your own strategy, right? And in our work, we call such a strategy the blockchain imitation game. So to understand what imitation is, let's dive into the life cycle of an MEV transaction. So first, the MEV searcher identifies the MEV opportunity and issues MEV transaction. This transaction is propagated through the public peer-to-peer network or other private channels to be observed by blockchain miners, builders, validators, who are responsible for creating the next block. And this transaction is eventually executed and mined or included in the blockchain. So you might notice that from the observation phase to the execution phase, there is a small gap. This time window typically lasts a few seconds, actually opens up the possibility that an imitation player can observe a profitable transaction, copy-paste, and then front-run original one. So in summary, the imitation game boils down a strategy of observing, copy-pasting, and front-running. You probably know how front-running works in a blockchain system. Now the question is, how can we copy-paste? How can we generate an imitation transaction? So one very basic form of imitation strategy that we introduced in an academic paper last year is called naive imitation. So to create a naive imitation transaction, an attacker basically blindly duplicates the potentially profitable transaction and performs some simple string replacements in the transaction data. Once the naive imitation transaction is generated, the attacker can simply verify the profitability by executing this naive imitation transaction locally. And if it turns out to be profitable, the attacker can then proceed with the front-running game. So let's look at a concrete example. We have a MEV contract with an up function. And you might notice that actually anyone who invokes this upcharge function can perform these upcharge actions, right? First swap Ether to USDC, then USDC back to Ether, and finally sends back the profit to the transaction sender. That basically means as long as the imitation attacker can front-run the original profitable transaction, the upcharge profit will be sent back to the adversary account instead of the original transaction sender, right? This is a very simple strategy that you can copy-paste any profitable transaction. Although it's very simple, but we find that it's rather effective. So we found that from December 2018 to August 2021, on Ethereum, the naive imitation strategy could have generated more than $35 million. That's not a small number, right? But fortunately, the naive imitation is quite easy to prevent. So the searcher can basically add one line of code in his or her MEV smart contract, checking whether the transaction sender address matches a specific value. Then in this case, if the naive imitation transaction is sent to this MEV contract, the execution will be immediately reverted, right? Because you cannot use the send account as the original transaction sender. So sounds great. Are we all safe? Is imitation still a problem? Well, apparently yes, right? That's why I'm here. It's still a huge problem. So if you look at this MEV contract and upcharge function again, you might realize what a smarter attacker can do is the attacker can create another MEV contract while bypassing the address validation, right? Because what is essentially for this upcharge transaction is the last 3 steps. Well, you only want to swap the asset and send back the profit. You don't want to really execute the address check in this smart contract. Well, this sounds very straightforward. I mean, if you can look at the smart contract, you can just copy the contract partially, and great, you can steal the money. But it's not that easy. There are still some challenges. Because what is executed in the Ethereum virtual machine is the so-called bytecode. It's not human readable, and the imitation protection mechanism can be anywhere in the smart contract. There can be even multiple smart contracts in one single transaction. So it's not that easy. So that's basically what we do in our paper. We propose a generalized imitation method. We call it APE, and APE allows you to automatically generate MEV transaction, but you can bypass all the imitation protections. So how it works? This is the overview of APE. I will discuss some of the technical details in my later slides. But on high level, the input is any pending transaction, and the output is the imitation transaction that includes all the contract deployment, also the imitation execution. So in total, we have 6 steps. In the first step, we executed the pending transaction locally. We build up the dynamic control flow graph. So for those who are not familiar with this concept, it's just some graphic representation of the transaction and the contract execution, showing how the different codes jump to each other among these code blocks. And then in the second step, we try to analyze the probability of this pending transaction. We try to identify the so-called beneficiary account who are receiving revenue in this pending transaction. Those accounts are the accounts that we aim to capture in our imitation transaction. Now, in the third step, we executed naive imitation transaction I mentioned earlier locally again, and we performed some dynamic intent analysis. And the purpose of this step is to identify all the code of imitation protection automatically across different smart contracts. And then the step 4 is the patch identifier, where we're trying to figure out all the smart contracts that we need to replace and synthesize in the imitation transaction. And then we synthesize these contracts. And then in the step 6, we validate the imitation adversary contract deployment and imitation execution locally again. And similarly, if it turns out to be profitable, the attacker can use the imitation transaction to front-run the original profitable one. So let's dive into a bit into the details. So first is the dynamic intent analysis. So when you look at the contract with imitation protection, so why does the naive imitation fail from a bytecode perspective? Well, it starts with actually some small differences, right? So in this case, we have a different transaction sender, and such a difference propagates through the execution and finally reaches a so-called conditional jump in the bytecode. So specifically, it's called jump I. And from this conditional jump, the execution of the imitation transaction will jump to another branch. As a result, the original transaction will continue with the upcharge operations, while the naive imitation transaction will be reverted, right? So the purpose of dynamic intent analysis is just to track the operation code that may introduce a difference in execution, and trying to find where the code start to go into a different branch. So in this way, we are trying to figure out all imitation protection mechanisms in the MEV contracts, in this case. So the next is the patch identifier. So to understand what patch identifier does, let's assume the following scenario. So in this case, the MEV contract is not invoked directly by the transaction sender, while it's invoked by another contract, let's say contract A, and we have a function E that calls MEV.up xy, right? So in this case, let's assume we can successfully identify the MEV protection in the MEV contract, imitation protection in the MEV contract, and we successfully synthesize an adversary contract that bypasses this protection, and we deploy it. But the imitation execution may still fail, right? Because as you know, as you can see, the address of the MEV contract is hard-coded in contract A. So now when the adversary sender is trying to invoke the contract A, the contract A will still call the original MEV contract instead of the new one that we just deployed. So what we need to do here is we need to deploy another contract, A prime, and we should invoke the MEV prime properly in this case. So patch identifier is basically such a recursive process that we are trying to identify all the smart contracts that we need to replace and synthesize in this MEV game. Okay, so finally, we have the contract synthesize. So as we just discussed, we are trying to follow the execution of the original profitable transaction, right? But there is some differences that leading to, in some scenarios, the jump high condition might lead to a different branch. So in the contract synthesize, we need to take care of such differences and try to force the jump high to follow the original path. So what we need to do is we need to just simply delete the conditional jump in the smart contract, and we replaced with unconditional jump. We call jump in the EVM bytecode. And in this way, we just force the jump to follow the original path. We call it the jump high forcing in our paper. And also, we need to take care of some other components when we are trying to synthesize the contract. For instance, we need to, as I just discussed, we need to make sure that every synthesized smart contract should be invoked properly. And also, every newly deployed smart contract has an empty storage, so we need to recover the storage properly in the synthesized smart contract if necessary. And also, in some scenarios, the MEV searcher may leave the money or the profit in one of the smart contract. But when we synthesize a new smart contract, we actually have no way to withdraw the profit later on because that part of the code is not touched, and we didn't include any such of logic into our newly deployed adversary smart contract. So in this case, in the imitation, we are trying to involve so-called asset transfer redirection and send back all the profit immediately to the adversary sender within the imitation transaction. All right, so to understand the effectiveness of APE, we performed a comprehensive evaluation by executing APE on every past transaction from August 2021 to July 2022 on both Ethereum and the BNB Smart Chain. And it turned out APE could have generated more than $148 million on Ethereum and more than $42 million on BSC. And we also performed some real-time evaluation by injecting the APE logic into a running mainnet full node without actually sending out the imitation transaction from ethical consideration. And the performance of APE is great. As you can see, on average, every imitation execution only takes 0.07 seconds, which is way below the block interval of Ethereum and BSC. Okay, so now if you look at the accumulative profit diagrams I put in the slides, you might notice that there are some spikes along with the line, right? For instance, in December 2021 and on Ethereum and April 2022 on BSC. So to understand where the revenue comes from in these high reward transactions, we did some manual investigation. And it turns out many of these high reward transactions are actually these DeFi attacks, where attacker basically exploit some vulnerabilities in smart contracts or DeFi protocols, trying to profit by stealing money from other benign victim DeFi users. So such insights actually leads to an interesting proposition. Can imitation attack be repurposed as a defensive mechanism? Well, the answer is perhaps yes, right? So imagine that you are a miner or you are a validator. When receiving a DeFi attack transaction, instead of including this transaction in the block immediately, you can generate a counter attack by using our imitation strategy and then front run this DeFi attack transaction. And then later on, you can deviate the money into your own pocket, and later on, you can just return the profit to the victim DeFi users, right? Acting as a white hat. So in our evaluation, we find that on Ethereum, it could have prevented 29 attack transactions, corresponding to more than $73 million of users' loss. And on BSC, the preventable attack transactions reaches 40, and the user's loss reaches more than $22 million. So I have also listed several examples for you to reference in the slides. So with that, I'm going to wrap up my talk, and I hope you find it interesting, and I'm happy to take questions.
I'm sure people will have some questions. If you want to ask a question, please line up at the mic. I'm curious, I'm sure these kind of attacks are already in maybe some more primitive form happening in the wild. Can you maybe speak to, in your experience, based on what you've seen on chain, how sophisticated are these kind of copycats at the moment, and what techniques do they employ?
You mean the wild, right?
Yeah.
We haven't observed any one is using our strategies by synthesizing smart contract on the fly and trying to merge everything into one transaction. But we do observe some MU researchers trying to play this imitation game beyond the naive solution. What they do is typically sometimes they trying to extract some effective actions, financial actions, trying to include in one MEV transaction and try to front run the others. So, in summary, all the transaction execution is public. And there can be many ways that how you can copy a transaction. So I'm pretty sure there are many solutions, but some I'm just not aware of.
Yeah. First of all, thanks for the great talk. Starting from the intuition of using this imitation game as a defense technique against DeFi attacks. Mm-hmm. First question, can you give us a sense about how many attacks, percentage-wise, can be intercepted out of the DeFi attacks that you have analyzed using your technique? Mm-hmm. And the second question is, how easy or hard is it for an attacker to bypass your defense technique then? Mm-hmm. If I know how your imitation pipeline works, I guess I can shape the contract in a way that it does not get detected. So can you give us a sense on that?
So first question is about percentage. So I would say theoretically all the single transaction attack could be potentially prevented by imitation. This is just because all executions are public. And so attackers basically use a sequence of DeFi actions to exploit some money from the users. So I don't have the concrete number about the coverage of our solution against all the DeFi attacks, and our implementation might have some bugs, might miss several transactions in our evaluation. But I would say theoretically we can prevent every single transaction DeFi attack use this solution. And then regarding multiple ones, there can also be solution that you can imitate multiple transactions, but we are working on it, basically. What's your second question?
How hard is it for an attacker to bypass your technique once the attacker knows how your pipeline internally works? Can the attacker simply craft a contract that is shaped in a particular way that is not intercepted by your technique?
Yeah, I mean, this is a cat and mouse game, right? So attackers, for sure, we are trying to obfuscate their attacks, for instance. So, I mean, we're trying to find out some obfuscation solutions to prevent our imitation strategy. But as I just discussed, right, everything is public. So what you need to do is just to copy the effective actions of what the attack is doing and try to create a counterattack. So I always say it will be hard, but it's not impossible, but I don't have a solution at the moment in my mind.
Thank you.
I had just one question. It's a great talk you gave. Can you please go back to a few slides behind? I want to show the two codes, 0x12. Go further behind, please. One more.
Which
maybe.
one?
Yeah. Yeah, this one. I think, no, it was the previous one. One more, I think. Yeah, this one, yes. So how did you know that if you inserted the 0x12, this is a vulnerable function that you decided to work on this? Did you use some tools and scan some other applications to come to a conclusion that this is one possible function that could result in the problem? That's one part. And the second part is, can we always say that a kind of a fix to this is to replace this jump I and push with a jump I and a pop and a swap and a push and a jump? And that will fix this problem. Can we generalize it for this kind of bytecode?
I'm not sure what do you mean by generalized bytecode.
Okay. No, I was looking for a general solution. Can we replace, if we use this, so we can go 2 slides later in the front.
I mean the...
yeah, this one. Yeah, this one.
Part. Okay.
So this is the fix, isn't it? Isn't this the...
Yeah, so basically, because we only have 2 scenarios to take care of, so jump I only has either jump or not jump. So here I give you an example how we can force it to jump, and in the paper we have another scenario that how we can force it not to jump, right? So in this case, it just delete the jump, and it can just continue to execute.
Yeah. Thank you.
Great. So this concludes the second session. We have a break now. I think you can find lunch outside. Thank you.
1, 2, 3. Okay, we're going to start in 8 minutes. So if people can start helping me close doors and shout, come in, come in, come in, then we can start the session. We are going to start in 3 minutes, so if people could take their seats and close the doors over on this side. All right, 2 minutes. Please take your seats. Close the doors to the conference hall. We're going to start in 2 minutes. All right, we're going to get started. Welcome to the Proof of Stake Consensus session of SBC. And we have an amazing lineup of presentations. The first one, everybody heard the phrase, time is money, right? But what that usually means in the traditional financial world is if you can rush fastest to the market infrastructure authority, then you win. And high frequency trading and all of this is all about getting faster. In the first talk, we'll actually talk about how being slower might benefit you. So please, Casper, come to stage and present.
Thank you. Thank you for this time is money introduction. I'll be talking about our paper, Time is Money, Strategic Timing Games in Proof-of-Stake Protocols. And this is joint work with Professor Fahad Saleh from Wake Forest University and Thomas and Barnaby from my colleagues from the Ethereum Foundation, as well as Jennifer and Niha from Jump Crypto. Before jumping into the specifics of timing games, I kind of quickly want to motivate why we should care about them. Consensus protocols are typically evaluated based on their ability to maintain liveness and safety. Liveness being the regular addition of new transactions to the output ledger in a somewhat timely manner, and then safety being the security of those confirmed transactions the security of the transactions remaining in these positions in their respective positions in the ledger. And the thing is, in real-world blockchain protocols, we do also care about something else, namely fairness of economic outcomes amongst consensus participants, because in order to preserve decentralization, essentially. And more specifically, a protocol should be designed to maximize profitability of honest participation. So basically, honest participants should not have any incentives to deviate from the honest protocol. Otherwise, a deviating participant may outcompete the honest peers and then leading to centralization of the validator set slowly over time. And so the problem is that MEV, maximal extractable value, which I will define shortly, frustrates such fairness goals. Maximal extractable value, which I will refer to as MEV going forward, is the value of that consensus participants in their duties as block proposers accrue by selectively including, excluding, and ordering user transactions. So to just give a simple example, If Alice submits a transactions to the public mempool to buy some amount of ETH on a decentralized exchange, Bob may then try an arbitrage to create the same price on a second decentralized exchange in order to recoup that arbitrage profit. And what becomes obvious here is that the order of transactions matters. So if Alice does this trade, Bob really wants to be right after that transaction in order to be able to do that arbitrage to ensure that no one else arbitraged before Bob. And so the order of transaction is of fundamental importance here. And MEV has security implications for consensus protocols and has been studied in the literature in various forms. I'm not going to go into much details, but essentially what I want to get to is actually a different notion of how MEV can impact consensus protocols. And so potential MEV accrues over time as users submit transactions. And the value of the set of these pending transactions therefore increases over time for block proposals. And so the important takeaway here is that as a consequence, time is valuable to consensus participants, which is usually sort of obviated by the assumption of honest versus and honest of an honesty assumption in typical models of consensus. So usually we operate in this honest Byzantine paradigm. And here we're basically, we argue that a model grounded in rational consensus participation provides a more accurate portrayal of behavior in these economically incentivized systems, such as blockchain protocols. And now I want to build some intuition for these timing games. I'm going to be using Ethereum as an example, but we argue in the paper that without loss of generality for proposed vote type of proof-of-stake protocols, that these dynamics hold. And so time in Ethereum really just moves forward in these rounds that we call slots. Each slot is 12 seconds long. And then these slots, each slot you have a block, and basically the chain just chugs along. Maybe just a quick side note here that in proof-of-stake systems, we have this sort of quote-unquote deterministic nature of time where, as opposed to proof-of-work, where we have randomness sort of exogenously fed into the system, here we make, the blockchain makes progress in rounds. That is either of a fixed interval of time, like in Ethereum, or has some notion of timeouts. But these dynamics of what is referred to as deterministic time remain across these proof-of-stake protocols. And so in a slot, you have typically some duties. And here in Ethereum's case, just to use this as an example, again, without loss of generality, we have at the beginning a block proposal that is supposed to be released at the beginning of the slot, so 0 seconds into the slot. This is taken from the Ethereum protocol specifications. And then we have a committee of attesters voting on these blocks to essentially make them canonical, should they be valid and timely, etc. And so the attesting rule is essentially saying if a valid block shows up, then vote on it immediately as soon as it's heard, or 4 seconds into the slot, whichever comes first. The aggregation part we can sort of skim over. It's a very Ethereum-specific artifact of just stuffing these attestations on chain. But the point here is that we now have the building blocks to kind of have an intuition for what these timing games can look like. So as a block proposer, essentially the proof-of-stake protocol assigns you this role to propose a block in a given time slot. And for the duration of that time slot, you have the proposer is given a temporary monopoly on that proposer is the only consensus participant that is able to propose a valid block in that time frame. And so here we see that proposer N is proposing the block slightly late, not exactly at the beginning of the slot, but just slightly late. But it is before the attestation deadline, before the committee basically commits to attesting to whatever they see as the head of the chain. And so what will happen is that this block is proposed slightly late, but early enough for the attesters to see it. And so eventually they will all vote for that block, assuming, of course, the block is valid, etc. And so then eventually block n+1 is built on top of block n, extending the chain, and everything moves on. Now, on the other hand, a block proposer here, a block proposer n+1 here shows up too late. So essentially, the block is proposed after the attestation deadline, meaning that the committee votes at the attestation deadline for block n because they haven't seen any block that they could otherwise vote for. And so block n+2 then comes along, skimming over some of the fork choice details that are protocol specific, but will then essentially build on top of block n, as opposed to extending the chain. And so here, we begin to see these dynamics of the timing game. Proposers have essentially their reward increasing linearly with time in our model relative to the most recent canonical block, so long as their block eventually becomes canonical. The intuition is simple, that the time difference between the latest canonical block and that proposer's block represents the amount of time that they can capture MEV, and so that is valuable to them, and so their utility function is increasing as linearly in time. And so in terms of dynamics, what this essentially implies is that as a proposer, you want to propose your block as late as possible while still being early enough to become canonical. Attesters, on the other hand, care about different things. They care about being correct, and they care about being fresh. Correctness here essentially means attesters essentially participate in some sort of beauty contest, meaning they want to vote correctly, so they want to vote alongside the majority of the remaining committee. And at the same time, they want to be fresh, meaning that these votes need to be released early enough for the next proposer to see. And the intuition here is that these votes, the information value of these votes degrades over time. And so freshness is of relevance here. And what we see here is this tension between wanting to wait as long as possible to either extract more MEV or have more information. More information here for the attesters. And at the same time, the tension to the other side being wanting to make sure to receive these rewards, because there's also a too late notion. And so in this static model that we define in our paper, we essentially have time that is partitioned into slots with a block proposer and a committee of attesters each round. And then proposers essentially choose to extend the chain or not. And they also choose when to release the block. Attesters, on the other hand, they choose when to release the vote for a block, or else they can also vote emptiness. So if a block doesn't show up, you would vote for emptiness. And importantly here, the strategies are static, meaning that all players commit to a schedule of actions at the beginning of the game. And so, yeah, this model is somewhat an idealized description of blockchain consensus mechanisms, especially proposed vote style type of proof-of-stake protocols. And in our paper, we then formally prove and show a multiplicity of equilibria. in fact, there's an infinite amount of equilibria within that time slot. And essentially, the intuition here is that testers can coordinate to implement proposers acting at any particular time within the time slot. And essentially, the testers, by choosing a attestation deadline, can force proposers to adhere to that deadline in order to ensure, as the proposer, to still become canonical. But given any attestation deadline, the proposer will release their block as late as possible, given that deadline. And so essentially, any kind of attestation deadline can be in equilibrium within that slot. And the nice takeaway here is that maybe like the equilibrium takeaway here is that, yeah, testers have the power to force proposers into accepting their attestation deadline. But at the same time, given any deadline, a rational proposer will maximize the delay that they can do while getting away with it, essentially. And so, to kind of recap what I walked through until now is that consensus participants are exposed to incentives outside of just the consensus rewards, namely MEV. So you have these exogenous rewards on top of the usual consensus rewards that influence their decision-making process. And so, importantly, time is valuable to consensus participants. And what this means is that block proposers then find themselves incentivized to use their temporary monopoly power by engaging in these strategic timing games. And these timing games, however, as just mentioned, can be contained but not fully stopped by the committee of attesters. And we care about this because ensuring economic fairness among consensus participants is critical to preserving the decentralization of the validator set. And we then argue in the paper that rational consensus participation provides a more accurate portrayal of behavior in economically incentivized systems such as blockchain protocols. This now kind of concludes the first part of the paper, which is this model. Obviously, you will find a lot more detail and the proofs in the paper, so please do read the paper. But now I'm going to shift to the empirical analysis. And essentially, we looked at some data on the Ethereum network to establish whether these timing games are being played by consensus participants and to what extent, if they are being played. To get there, I want to briefly take a step back and talk about this concept of proposer-builder separation, of which MEV Boost can be seen as an instantiation. Essentially, the MEV market structure in Ethereum has dramatically evolved over the last couple of years, and we find that now there's a set of specialized actors in producing blocks, and the high-level idea is that finding these MEV opportunities is a complex task. And a proposer may not be able to find these MEV opportunities. And so the proposer-builder separation refers to this idea of the proposer auctioning off the right to build the block to a builder. And now I want to quickly walk through these different sets of actors that participate in this network. So there's still the usual user transactions that are submitted to the public mempool. Then there's these actors that are referred to as searchers that look for these MEV opportunities. So, for example, arbitrages, and submit bundles of transactions alongside bids to express their order preference to block builders. Block builders, in turn, specialize in packing maximally profitable blocks using these searcher bundles and other available user transactions from the public mempool as input. and they submit these blocks with bits to relays. Relays, on the other hand, sort of act as a trust facilitator between block builders and block proposers. And what they do is they validate these blocks received by block builders and forward only valid headers to the block proposers. And this ensures that block proposers cannot steal the content of these block builders block, but they can still commit to proposing this block by signing the respective block header. And so essentially, the problem is the following. A block builder may not trust a block proposer, because if they would just send the block content to a proposer, then the proposer could just sort of steal the MEV opportunities. And so these relays act as a kind of broker between these two actors. And then essentially at the end of the day, the proposer can choose to either participate in this block auction or locally build a block just like always, essentially. And maybe an interesting note here is that over 90% of all Ethereum validators run this MEV Boost software, which is essentially participating in this proposer-builder separation paradigm. And so what we did is we looked at some data using data points from the ultrasound relay, which is one of these relays, and essentially they recorded these block builder bits, and so we collected over 150 million bits over just over a month earlier this year, and had data for over roughly 185,000 slots, and of those were 85,000 winning slots. And for each bit, there's several timestamps that the relay records that we can use to understand the dynamics of these timing games. And so what we see here is a logical representation of the block production process for slot n. So the builder bits begin streaming in during slot n-1, after which the proposer and the relay interact through like requests and responses to finally then release a block. And this kind of competitive process between block builders determines the right to construct the block for slot n and secures sort of potential MEV-derived profits. And so for each bit, the relay records some timestamps at which the bit was received, so the received at, when it's eligible, so once the block has been, the bit and the block has been verified, and then eventually the proposer goes to the relay and requests a header, and if that header, meaning if the bit is the highest that they have seen from all the different relays that a proposer may connect to, they will sign that header and return it to the relay with the get payload call, and then eventually, once that signed header is returned, the relay releases the block and sends it to the P2P layer as well as the proposer. And so the natural question we asked is like, what is the value of time? And so the marginal value of time that we find here is that we basically looked at all the bits submitted to the relay over time, and here we plotted the bits over time against the median bit value of these builders. And importantly, we observe a linear relationship here, meaning that a rational actor is incentivized to participate in these timing games. We ran a regression and we found a value of 0.0065 ETH per second, which roughly translates to $10 a second for the median proposer. So if you delay your block by some amount of time, you can essentially earn more due to these MEV dynamics. And so yeah, then this shows that there exists a positive marginal value of time indicating that a rational block proposer would participate in timing games. And so then we kind of tried to understand whether these timing games are played now that they're rational to participate in. And to do that, we looked at some different timestamps of winning bids now. Not all bids, but only winning bids. So bids that eventually were signed by a proposer and are essentially the block that a proposer released. And so what we see here is that the received time of winning bids is very close to the actual proposer schedule, so 0 seconds into the slot. Shortly after, they're eligible, and with a bit of a delay, they are then eventually signed. And what this indicates is, although the block is released relatively late, not as late as it possibly could, but still roughly like 780 milliseconds into the slot, a lot of this is actually due to signing delays, meaning that the block proposer, while releasing their block with a delay of roughly 800 milliseconds, most of it is not actually, they're not able to capture the MEV of 800 milliseconds more listening time, but it's a time differential only between the received timestamp and the signed timestamp. So we did a bit more empirical analysis than in the paper to show that this is due to signing procedures of certain proposer types, namely actually centralized exchanges, funnily enough. And now quickly to speak about some of the conclusions and implications. The high-level takeaway is timing games are rational to engage in, and they do occur, but they are not yet stretched to their fullest possible extent. And so on the model side, what's good is that testers can enforce an equilibrium strategy containing these timing games, but on the other hand, proposers are still able to maximally delay their blocks any given attestation deadline. And proposers can also delay their blocks better through sophisticated latency optimizations. Speaking to your comment regarding the high-frequency trading centralized version. And so this is important because economic fairness among consensus participants is of great utmost importance in real-world blockchain protocols in order to preserve decentralization. And to further recap the entirety of this talk, maybe the takeaway here should maybe be that time is valuable to consensus participants, and block proposers are, in fact, incentivized to abuse their monopoly power by engaging in these strategic timing games. And then they can be contained by attesters, as mentioned, and this is important because of the goal of preserving decentralization, and so modeling rational consensus participation arguably provides a more accurate portrayal of behavior in these economically incentivized systems. Obviously, a whole lot more detail in the paper, proofs, more analysis on the empirical side, and as a side note, this paper is forthcoming in the AFT conference later this year. And yeah, the QR code is a link to the paper. Thank you so much. Do we have time for questions?
Yeah, so we have time for questions. Please queue up behind the mics so that people online can hear. I'm going to use my latency advantage and ask a quick question. What is the main source that you find for the delay advantage? Is it that fees increase? Is it the time I have to process and get the best, to search and get the best built block? What is the advantage of delay? What is the source of delaying, of the benefit of delaying? Is it that fees keep increasing or more orders are increasing?
I mean, generally, the more time a proposer has, the more transactions will be in the public mempool, and so the more options to sort the transactions in a particular way to extract these MEV opportunities are found.
So it's not the processing time of the existing pool, it's the growth of the mempool?
It's the growth of the mempool, yeah.
And is it the fees? The more time, the more desperate I am to get my transaction, so I will bid higher fees? Or is it
I
more
mean,
market
there
makers?
it's to some extent, towards the end of the slot, you might have better ways to arbitrage between centralized exchanges and decentralized exchanges with a decrease in risk. But at the same time, so there's like several factors going on. But I would say the main source is just having more choice, more transactions to optimize from.
All right, we have a bunch of questions.
Thank you so much for the talk. Quick question. From this research, what do you think is the takeaway for Proposer Boost? And what do you think the 40% number could be changed up or down based on the research you have here?
So what exactly is the question? So Proposer Boost, yes. I mean, that's like very specific Ethereum fork choice quirks that are there to kind of make the protocol more secure, to prevent reorgs and balancing attacks. I think Joachim, the next speaker, will hint at that. But yeah, so what
what do you think the additional learnings are from this paper around Proposer Boost?
I mean, Proposer Boost essentially helps. So in Ethereum, Proposer Boost is essentially what it says is it gives fork choice weight to a block proposal if it shows up on time, and the boost is 40% of the committee weight. So if a proposal shows up on time, the attesters will assign that block 40% weight. And so if a block proposer in, say, slot n+1, they can basically use the boost to try and reorg block n if they don't manage to accumulate 40% of the votes. So it's essentially, it helps the next block proposer to reorg late blocks that don't show up early enough to accumulate enough attestations. So it's essentially a late block reorging mechanism, if you will. If that makes, I mean, it's very specific Ethereum fork choice stuff, but I'm not sure if that answers your question.
No, but it's okay, thank you.
All right, why don't we take the remainder of the questions offline?
Okay.
And thanks, Casper. Thank you.
Thank you so much.
And next up is Joachim, and arguably the second most important thing we've all have been waiting for this year. The first one is the merge, and the second one is to have actually a safe and live algorithm for Ethereum 2.0, and Joachim will present Goldfish.
Thank
Take
you.
it away.
All right, let's see. This works. This works. And this works. Okay, welcome everyone. Thank you so much for the kind introduction. And let's get started. Yeah, I'm going to present to you Goldfish. The paper is now titled No More Attacks on Proof-of-Stake Ethereum. There used to be a question mark in the title. You'll see why. Anyway, this is a joint work with our collaborator Francesco from the Ethereum Foundation, with my colleague Nusret, and with our advisor David Che, who's here. And let's get started. So, you know, the elephant in the room, or what Dalia just mentioned, you know, the big event that happened about a year ago in September 2022, nobody could ignore it, the merge, finally. Ethereum switches to proof of stake. And there's a very natural question related to this. Okay, we're switching from proof of work, Nakamoto-style consensus to a brand new proof of stake consensus protocol. Is this protocol secure? So we asked ourselves this question in 2020, about 2.5 years earlier, when this paper appeared on arXiv called Combining Ghost and Casper. Short, we refer to this protocol as Gasper. And that's really, in some sense, the foundation of the proof-of-stake Ethereum protocol as we see it today. And so the question is this protocol secured? That's how we started this. And here's the subtle hint that Casper was already announcing. Shortly thereafter, we found some issues with the protocol. Basically, there was a balancing attack on this protocol. Other people have been doing analysis of the protocol, found some other kind of nasty behavior that the protocol shows. The earlier versions of this attack were in a model that had adversarial network delay, but it turns out you can have the same balancing type attacks even in networks where the adversary doesn't control anything about the network. And the result of these attacks is that the protocol doesn't have liveness, the protocol doesn't have safety, even if the adversary controls relatively little stake. And in addition, you can use the techniques of these attacks in order to get reorgs. And if you want to read more, you can check out this paper called 3 Attacks on Proof-of-Stake Ethereum. And then there was the infamous proposer boost applied or put into the protocol in response to this. Unfortunately, this was also a little bit hinted to. The proposer boost makes certain types of selfish mining and reorgs easier. And it turns out that it was also not enough to make these balancing attacks go away because there were other vectors in the protocol that could bring them back, basically. There's a paper titled 2 More Attacks on Proof-of-Stake Ethereum, which you can check out. And then there was a change to the protocol again in order to make these attack vectors go away. And then we merged. So this is the protocol we have. Unfortunately, this process, whack-a-mole of between security researchers and security designers is not a process that we're very happy with. And so Goldfish is kind of in this line of work, the idea of can we have a protocol where we can be sure that there will be no more attacks on proof-of-stake Ethereum, and can we give a security proof, meaning can we give a description of the exact circumstances that would have to be satisfied for this protocol to be a secure protocol? So this is kind of the setting that this work is to be understood in. And now many of you probably know, hey, wait, we have proof-of-stake protocols for which we have a security proof. Think of Nakamoto-style, Ouroboros, for example, or PBFT-style protocols like Hotstuff. Why don't we just use those? And the answer is, well, for Ethereum, we're shooting after a very ambitious wish list of properties that none of these earlier protocols really satisfies. And I'm going to go through a couple of them. The first one we call dynamic participation. What we mean by this is the protocol should tolerate a large number of unexpected temporary crash faults. The idea being, for example, if for some reason some proposers or some validators decide to not vote for certain blocks because they don't like the content, or if there's a bug in some of the clients and some of the clients basically go offline, as has happened earlier in the year, then we still want the protocol to make some sort of progress. So that's dynamic participation. A second property we can call accountability, which means that we want to be able to slash malicious validators. In particular, whenever there's a safety violation, an inconsistency in the protocol, we want to be able to hold a sizable fraction of them accountable and take away their stake. The next property is a little bit, relatively straightforward, right? We want this protocol to be communication efficient, of course, so that we can support 1 million validators. We would like this protocol to be reorg resilient. By that, we mean that if there's an honest validator, playing no shenanigans, everything good, makes a proposal, an honest proposal, there should not be an adversarial strategy to prevent that proposal from entering the chain, together with kind of the prefix that is basically built on. And then finally, I think this one is also a relatively intuitive one. We want fast confirmation, right? We want to confirm transactions as quickly as possible, really. And by the end of the talk, you'll see a protocol that actually has all of these properties. But going back to the protocols that I just talked about, right, the ones that we had a security proof previously, longest chain style protocols, they get dynamic participation and they have low communication complexity, but they do not get accountability. They're not reorg resilient, and they do not have fast confirmation. They're notorious for their slow confirmation, in fact. And PBFT style protocols, you know, they have accountability, they can be made reorg resilient, they have relatively fast confirmation, but they don't work under dynamic participation, and they're not really communication efficient. So somehow, you know, we're trying to square the circle here. And in fact, you know, for these two properties alone, dynamic participation and accountability, you can show based on the CAP theorem that there cannot be one single log, one single ledger that has both of these properties at all times. So the question is, okay, if we cannot have one ledger that has these properties, can we at least, you know, some users might prefer one property, some users might prefer the other. Can we at least have a protocol where we leave the choice to the user? And I'll explain a little more what that means. So here's kind of the, you know, Ethereum consensus protocol in one block diagram, really. So Ethereum consensus is this box here, right? Transactions enter. And really, the box is composed of two protocols, of two sub-protocols. The first one is called LMD Ghost. It produces a ledger or a log, this orange log here. And that's what you see in your clients as the chain tip. And then, based on the chain tip, there's this second stage protocol, which many of you have probably heard of. It's called Casper FFG, and it checkpoints this chain tip in order to produce finalizations. And then these finalizations are fed back into LMD Ghost in order to make sure that, you know, these two protocols kind of don't diverge too far. Now, how is this useful? Right now we have a protocol that takes in transactions, but it gives us two output logs. What does that mean? We have a chain tip, we have finalizations. How should we deal with those? What should we follow? And the idea here is the following. We'll have the chain tip be a full log that has this dynamic participation availability property. Right? So the full log is secure even if there are many temporary crash faults, and as long as among the nodes that aren't crashed, a majority of them is honest. And then the Casper FFG gadget will finalize a certain prefix of that chain tip. So there will be a certain prefix, a certain portion of the output log that will be made accountable. And that means the prefix log is accountably secure, meaning that, you know, it's live as long as fewer than a third of the validators are malicious. And if there was ever an inconsistency with the finalizations, we can point to a third of the validators who must have provably violated the protocol. And then these two are also consistent. This is what is referred to as the ebb and flow property. And how is this useful? Well, you know, now we're giving this control back to the client, right? If the client is selling boba and is not really concerned that somebody would, you know, mount a double spend or a safety attack, then, you know, but on the other hand, you know, you want to be in business, you want to make sure you can always transact, then you would probably consider a transaction confirmed once it enters, you know, the chain, essentially the orange part of the log. And if you're selling something very expensive, or maybe you're a centralized exchange and you have like a big deposit, and you want to make sure that, you know, the payment is absolutely not reverted, for example, you're selling a car, then you would wait for the transaction to be finalized. So great, users can now decide again, right? So there's a paper also for ebb and flow protocols if you want to learn more about this. Now with this construction, you know, the issues that have been there in the past, they basically fall into two categories. One is related to kind of this feedback loop, the interaction between the two protocols. That's not the primary topic of this talk. The topic of this talk is issues with this first stage protocol, with this LMD Ghost protocol. And you can see why does this matter? Well, you could take the stance and say, well, why do I care about LMD Ghost? I'm only following these finalizations. You know, if LMD Ghost doesn't work, why do I care? But the point here is, you know, you see everything in this diagram is downstream from LMD Ghost. If LMD Ghost doesn't do what you expect it to do, you get basically almost no properties, right? You get accountability, you get accountable safety, but your finalizations might just never finalize anything, really, if the first stage protocol doesn't work. That's why it's so important, excuse me, that we make the first stage protocol work. Okay, so, then previous works have suggested a fairly similar construction where they just replace the LMD Ghost protocol with a longest chain protocol. And then if we look at the wish list of properties that we want, this construction manages to kind of combine these two main properties that we had to work around the impossibility of combining them. This construction also gets you a fairly communication efficient protocol because longest chain is communication efficient, and the votes in Caspar FFG can still be drawn out across like a whole epoch. But longest chain is not reorg resilient, and longest chain is slow in confirming, and so you do not get these two properties. Now, what we would like to do is we would like to design a drop-in replacement for this LMD, for LMD Ghost, or for the longest chain in this construction, where we have, the drop-in replacement gives us dynamic participation. It is communication efficient. But it also needs to have the reorg resilience and the fast confirmation. It's clear if you want to have fast confirmation, Caspar is definitely slow, so finalizations are going to be slow. The only hope you can have for fast confirmation is if it happens in the tip. That's why this first stage protocol needs to have this property. And similarly for reorgs, right? The proposals that are or are not reorged are the proposals of this protocol. The checkpointing mechanism, just adds a little safety on top. It just checkpoints this. Okay, so this gives us, the desiderata that we want for a drop-in replacement for LMD Ghost, which is safety and liveness under dynamic participation. For those of you who are a little more familiar with the literature, we mean the sleepy model, reorg resilience, fast confirmation, and low communication. And then in order for this to have, utility as a drop-in replacement and a realistic path to adoption, we want this to be composable with Caspar FFG, and we want it to be similar to the protocol we already have, LMD Ghost. Okay, and now the second half of the talk is about, how do we design this protocol? So let's look at LMD Ghost and kind of what's wrong with it. And in LMD Ghost, time is divided in slots, right? And I'm going to say for simplicity that every slot is 2 delta, where delta is the upper bound that we know on the message delay. Okay, so we're assuming that we're in a synchronous setting here because any sort of asynchrony, network partitions, etc., we've already delegated over to Caspar FFG. We can afford now, we want this to work only in the synchronous setting. And the protocol is fairly simple, actually. For every slot, we assume there's some sort of proof-of-stake lottery process that gives us a block proposer and a bunch of voters. Okay? And what do? At the beginning of the slot, the proposer runs this thing called fork choice and proposes a block. What's this thing called fork choice? It's every validator has in their head a block tree and a bunch of votes. And then they run this ghost rule. And ghost works as follows. You start at the genesis block, and then for every child block, you look at the number of votes in the respective subtree. So in this case, for example, on the left-hand side, this is 4 votes. On the right-hand side, it's 3 votes. And so you recurse into the subtree that has the most votes. And you keep doing that until you reach a leaf. And then the proposer makes a proposal and sends it out to everybody. And then delta time later, this proposal has propagated to all the voters. And the voters, again, run the fork choice rule. If everything goes well, they arrive. They determine as the chain tip the newly proposed block, and then they cast a vote on that newly proposed block. Now, what's the issue with this? The issue with this is, we could call it swaying voters. The issue is as follows. Suppose the proposal has been made, but just before the voters are about to vote, the adversary releases a few votes from like a previous slot on some kind of orphan blocks in order to confuse honest validators about what's the leading chain, what's the chain tip that they should be voting for. And then some of them might consider the proposal the leading chain, and some of them might consider another block the leading chain. And then they will vote inconsistently. Some of them will vote on, in this case, on the left-hand side, and some of them will vote on the right-hand side. And it can happen that then the proposal doesn't get enough votes, even though it's an honest proposal, and it gets reorged out. So this gives you reorgs, and then you can bootstrap from there to these balancing attacks. So this is what we want to solve. And that's what Goldfish essentially does. And I'm going to give you, it's going to be a little bit more technical. We have 9 minutes left, so that shall suffice for that. But I hope you at least get kind of the intuition from it. So in Goldfish, again, we have time slots, just like in LMD Ghost. We're adding one phase. So instead of having 2 phases, we now have 3 phases, all of them delta apart. In Ethereum, that would mean the delta there is 4 seconds. So instead of going from 12 seconds, we would go to 16 seconds. And then for every slot, again, we assume that there's a proposer and that there's a voter committee, and those are given to us from proof of stake. And then every validator maintains 2 data structures. One is a buffer, BI, and one is a block vote tree, TI. And whenever a validator receives a message throughout the protocol, they first just put it into BI. But whenever they run Ghost fork choice, they apply it to TI. And much of the magic has to do with how do messages go from BI to TI in this protocol. Okay, so keep an eye out for this. In particular, there are 2 mechanisms. One we call vote buffering or view merge, and the other one we call vote expiry. And the mechanisms work as follows. So at the beginning of the slot, there's again the proposer. And the proposer does the following. The proposer of the slot does the following. It takes its buffer and adds whatever it has in its buffer to its tree. And then it runs this ghost rule that we have just seen, but only using the votes from the most recent slot. So only using the votes from slot T-1. That is the vote expiry. The first aspect is this vote buffering thingy going on. And then the proposer adds a new block, right, at the ghost tip and proposes its block vote tree. So it just sends out its entire view of the protocol. There's a way to make this efficient so that the actual message that happens on the network is not as big and it's not as horrible as it sounds here in the pseudocode. You can check out the details in the paper. And then delta time later, right, this has propagated to everybody. And the voters, they take this proposed block vote tree and they merge it into their local tree. And then again, they run this ghost rule, and they using the slot T-1 votes, and they cast the vote themselves, which they broadcast to everybody. And then in the third phase, at the beginning of the third phase, every validator takes their buffer and adds it to their tree. Now this protocol has 2 interesting properties that immediately basically give you the security and the reorg resilience of it. The first one is that okay, we want to show reorg resilience, right? So we can assume that suppose the leader of a certain slot is honest, we want to show that all the slot T honest voters will vote for this proposal. Okay, so this is basically the property that is violated in these swaying attacks, right? There was an honest proposal, but not all the honest voters voted for it. So how does this property come about? So, this is kind of the view of the protocol from the perspective of a bunch of validators, right? And let's suppose there is this swaying attack. So there is one validator here on the left that has seen these votes that the adversary has released. The other ones haven't seen those. And we're now at this point in time where this arrow is, okay? So suppose by this point in time, this node here has seen these sway votes. Well, they now see this as the leading chain. The other guys see another leading chain. But the point is that according to the protocol description, there's no update from TI in this window for this validator, unless it's the proposer, but let's not assume that for now. So they must have received these sway votes before this deadline. And so come this proposal, the beginning of the proposal phase, the proposer, everybody else now has these sway votes in their buffer, not in their tree yet, but in their buffer. In particular, the proposer has it in their buffer. Now what the proposer does, suppose this guy is the proposer adds the buffer to their tree, right? Happens here, and then they make a new proposal. And then they send out this proposal. But now notice you have the property that the tree that the proposer has and that the proposer sends out is a superset of all the other honest validators' tree. And then what happens once that proposal propagates to everybody and all the honest voters merge that proposal into their tree is that now everybody has the same tree. And now if everybody runs the ghost rule, they all agree on what they should be voting for. So that is the property that vote buffering gives us, is if the leader in a particular slot is honest, then all slot T honest voters will vote for the proposal of that leader. Now we need to make sure that, it has happened once, it needs to happen, forever, right? So we want the second property, which is that if in slot T, or in T-1, honest voters vote into a certain subtree rooted at B, that they then also do that in the next slot. Why is that? So let's assume this, right? Let's assume that in slot T-1, all honest voters have voted for some block that is a descendant of a block B. But let's suppose for contradiction that there is one honest voter that is not voting into that subtree B in the next time slot. Why is that not possible? Well, because of vote expiry, right? The only votes that matter in the ghost rule are the votes from the most recent time slot. In the most recent time slot, all the honest guys have voted into B. That means into this blue tree, this competing tree, only the adversary can have cast votes. But by assumption, the honest guys are more than the adversary. So definitely B will win out in the ghost rule, and the honest node will cast their vote into B. OK, and now we just have to tie it all up, right? We need a confirmation rule for this protocol, which is that we output a block once its prefix, a block and its prefix once it is tconf time old, and still on the ghost tip according to the most recent non-expired votes. And then we get reorg resilience, right? Honest proposals enter the confirmed output log with the same prefix as determined at the time of proposal. Why is that? Well, the proposer was honest. We saw that in the time slot of the proposal, all honest guys have voted for it. In all the subsequent time slots, also all honest voters will vote for this proposal. So the proposal will forever stay in the ghost chain, and it'll be eventually output according to this confirmation rule. And then it's easy to get security from this, to get safety and liveness from this. Namely, we just have to tune this confirmation parameter such that we can make sure that within every tconf interval, there was at least one honest proposer throughout the execution. And then we trust the fact that honest proposals stabilize the prefix, they introduce new transactions, and so that gives us safety and liveness. Good. That's basically the protocol. Here are the theorems. Since then, there has been some follow-up work. So one of the challenges that comes with this protocol is that vote expiry means the protocol becomes more brittle if there was a temporary network partition or a temporary spike in network latency. Vote expiry gives us also a bunch of good properties, but this is a bad property. And so an idea in follow-up work is that what about instead of expiring votes after one slot, we expire them after k slots. Then what you get is a little bit of a trade-off between dynamic participation and asynchrony resilience, right? If you want to tolerate longer violations of the delay bound, you have to give up a little bit on the level of dynamic participation that you can tolerate. But the result of this is this protocol called RLMD Ghost of Luca and Francesco, which will be presented tomorrow. So you should make it to the 10 a.m. slot and check that out. And with that, I conclude. You have seen Goldfish. You have seen these three properties, safety and liveness under dynamic participation, reorg resilience, and hopefully you're convinced that it's quite similar to LMD Ghost. Properties that I haven't shown you, but that you can find in the paper, is that this protocol is also composable with FFG. It has fast confirmations, assuming the optimistic case that participation is high. And it can be made to have low communication because we can subsample the voting committees within Goldfish. And we have a kind of a proof of concept simulation / toy implementation and a bunch of experiments, which you can also check out in the paper. And yeah, if we plug Goldfish into this checkpointing construction here, then what you will get is a protocol that ticks all of these boxes. Thank you.
All right, we have time for maybe one quick question.
So one quick question then. So first, I'm happy to see that you also like fish names for your papers. But so this protocol is synchronous, but then you put it into the big box there, and there is a claim for partial synchrony, right? Is that correct? So is it also responsive? Namely, do your validators need to wait for a delta before advancing to the next protocol step?
Yes.
Okay.
So this protocol, the Goldfish itself is not responsive.
Cool.
And then as a result of that, the checkpointing is not responsive.
Cool. And could you use the Shoal trick to make it responsive by saying, I just advance at network speed, whatever, and if I realize that I do lose liveness, in that case, I start waiting for the deltas?
I guess you could try. We haven't thought about that, yeah.
Cool.
Would
Thanks.
be worth thinking about.
All right, so maybe one more quick question, if there is one. All right, I'll ask, when is Ethereum going to roll this?
Well, we'll see. So I think there's like an ongoing process kind of towards doing more and more work on the consensus protocol. So this RLMD Ghost is kind of fixing some of the kind of asynchrony resilience. And then there's a proposal for single slot finality, which is my understanding is basically built on RLMD Ghost. So there the idea is to basically run this finality gadget in faster. So we're probably not going to see Goldfish as it's like specified in the paper deployed, but it seems that the ideas continue to live and continue to evolve, and we'll see. Yeah.
Fair enough. All right.
Thank you.
Well, thank you, Joachim, again. Okay, and the next speaker, Oysin, who comes from OBOL. And we've already addressed MEV, we already addressed consensus in this session. What remains is the staking. And all this work to decentralize and scale proof of stake consensus aims to increase the security by having many, 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 many stakers. But of course, what we have is node operators organizing and coordinating all the stakers into essentially somewhat centralized control entity. And I guess Oysin will tell us about how to decentralize the validators back again. Take it away.
Sweet. Is this thing on? Okay. Thank you very much. Hello, everybody. My name is Oshin, and today I'm going to be talking to you about building a secure and decentralized proof-of-stake consensus for Ethereum. So if I give a quick overview of what I'm going to talk about, this talk is going to be focused on distributed validators and distributed validator protocol. Going to do a bit of an introduction to them and what they're for. And then I'm going to go into the DV protocol and different decisions we can take to make it secure and decentralized. So I'm going to look at some of the engineering and software architecture sides. Then we're going to look at like the data and subjectivity challenges of proving DVs. Then we're going to look at some of the open research items. And then lastly, going to talk about some of the like coordination and public coordination side. Before I get into it too quickly, I wanted to briefly kind of give you guys a mental model as to where DVs fit in scaling Ethereum. So Ethereum and most blockchains have kind of three things that you want to try and scale: execution, data, and consensus. To scale execution, the most common way to do so is with optimistic and ZK rollups. To scale the data side of a blockchain, things like data availability sampling is used. Common ones are EigenDA, Polygon Avail, Celestia, Danksharding, and so on. And to scale consensus, we think distributed validator technology is the next way to take like an order of magnitude improvement in scaling consensus. So I've mentioned this thing, distributed validators. What are they? A distributed validator is an Ethereum validator with software-based fault tolerance. You can think of it like a multi-sig, but for an Ethereum validator, one where you need kind of more than 2/3 of people online and honest. So what's interesting about them as well is because they are Byzantine fault tolerant, you can have multiple independent parties work together to run one single validator. Why would you want to do something like this? Who's this useful for? One of the first and foremost things is if you have fault tolerance, you can have a highly available validator, meaning one that runs on multiple machines, and if any one machine dies, no big deal. Validator stays online. Having multiple independent entities running your validator is something important for lots of like liquid staking protocols and people that want to delegate their stake to somewhere else. They want to make sure that it's actually run by independent people and not one person like kind of messing up can get you kind of slashed. For the home staker and the solo staker, the ability to run in teams and to do like squad staking is something that's enabled by distributed validators. And generally having multiple client implementations in a single validator, having multiple geographies in a single validator, things like this increase Ethereum's resilience, as we alluded to like in the previous talk about if there's a client failure, a DV that's made up of like many different clients isn't going to go offline. So if that's what a distributed validator is, just to briefly give you an idea as to their like progression at the moment, distributed validators have been a topic of research since about 2019. As of the end of 2022, we've put the first one on mainnet. At the moment, Opal is in alpha phase, and we have about 40 operators running validators on mainnet and as part of alpha. We're working with projects like Lido to run DVs on mainnet. We have solo stakers running DVs on mainnet with EtherFi. We've been doing like scaling and performance tests with Mega Labs, where we ran up to 3K validators on 4 bare metal machines. We've done a security assessment with Sigma Prime, and we're currently working on audit for some Solidity. So if that's what a distributed validator is, what is a distributed validator protocol? A distributed validator protocol is just, at its most simple, a spec that many different client teams have implemented that allows them all to interoperate and work together. A protocol like this is one that should focus on being secure whenever there's a trade-off. It should focus on verifiability, so we can figure out, who's taking part in a DV. And generally, it's the kind of base layer for proving participation in a DV, and then subsequently, like rewarding and penalizing people if they're participating honestly or if they're, not participating enough. So that's a quick run through on what DVs are and what a distributed validator protocol is. Now I want to talk about some of the challenges faced. And most of this talk will have more questions than it will answers. But the reason I wanted to start with the engineering side is I wanted to talk about private keys and networking. So proof-of-stake validators have private keys. That is, the kind of crown jewels, the most important thing in them. And when you look at a distributed validator, the first question to ask is, what's up with the private keys? So because BLS, the signature scheme, is homomorphically additive, that's a fancy way of saying you can add together signatures from 2 different pub keys so long as they're signing the same piece of data. This is very important for distributed validators because it means you can build a distributed validator that only has to do 2 things. It has to come to consensus on what every validator signs, and then once it receives a signature back, it has to aggregate them together into an aggregate signature that it can send upwards to the wider consensus layer network and look like a normal signature. What's interesting is it does not need to have runtime access to the private keys. It does not need to be able to sign messages. And what's important about this is you can separate the concern of controlling the private keys, not slashing any messages. That can stay with the validator. And then the distributed validator can mostly focus on coming to consensus on what should be signed and aggregating what comes back. And to put this in clarity as to what this mitigates for, if distributed validator software was compromised, like Lazarus Group was in charge, they're showing slashable messages to the downstream validators. The downstream validator says, I've already signed something for this slot height. I'm just not going to produce another signature. So even if you've total control, you don't get slashed, you go offline. And these liveness risks we'll talk about later on. One of the other things that's important about the private keys is you can do a distributed key generation rather than centrally creating the private keys. This is where all of the different operators in a distributed validator take part in the key creation process, and no one entity has the full private key. If you're then trying to slash this validator, you probably have to compromise 2/3 of the operators to get a full private key so you can sign something slashable. So that's the kind of private key side of a distributed validator and how you can build such a protocol without runtime access to the keys. The other thing that I wanted to talk about is the networking side. So in blockchains, we regularly favor these like gossip-based networks, which, you know, gossip messages to many parties, all like kind of in a one-to-many situation. This is not the route we've gone with for networking for distributed validators for a few reasons. Firstly, a multi-hop gossip network slows you down. If you have to kind of hop along from computer to computer, that, you know, wastes precious time when you're trying to, you know, run a validator and not be slower than a normal one. And it's also going to a lot of parties that don't exactly need that, like, you know, partial signature. Regularly with gossip networks, you need people to run like message brokers that are accessible to all and will like kind of rebroadcast your messages. If you don't, you kind of have issues where messages don't get to their intended recipients. And generally, if you have this big gossip network that everybody shares, you have to make sure that it's kind of homogeneous. You don't like break it with a new version that changes how like messages are formatted. That can cause a partition, or worse, it can cause like messages to halt entirely. And as a result, your kind of protocol becomes very like homogeneous, and it all has to like upgrade at the same time. And if you're making a protocol and you want to design something that's very like non-correlated, you don't want this big network that everyone speaks, that like all serializes the same way. That's kind of something that'll succeed together or fail together, which is not really what you want when you're building a DV protocol. Instead, we've gone with independent networks for each cluster, so each kind of set of nodes that are running with one another. You know your counterparties because they have the other pieces of your private key, so the messages you're sending are like only to the intended recipients. We've built on libp2p, which uses like a circuit relay, which is more or less a man in the middle that helps you find your counterparties and helps you do NAT hole punching, which is a way for you to speak directly to your counterparty with a key exchange, so you're like doing end-to-end encrypted comms. So if you're an adversary like in control of the network trying to like filter out this like communication, it can be very hard to do because it just looks like any other encrypted communication between peers. I would say that networking is by no means like a finished or a solved problem. Some of the things we also look at are using something like QUIC instead of TCP, and also doing decentralized discovery rather than having these relays that help you find one another. That's something that I'm keen to hear about more at CADemiliaCon later in the week. But yeah, on the engineering front, the two main takeaways I'd like you to kind of think about is you can build a distributed validator that doesn't have access to the private keys. It's only aggregating signatures from something else that, you know, guards the kind of crown jewels. And networking, if you have all of these clusters with independent networks, you can upgrade one in its own time, see if it goes like successfully or not, then upgrade all of the other clusters. You're not in this kind of one big like homogeneous network that either like succeeds or fails all at the same time. So next, on the data front, data is quite a large part of distributed validators, and I want to go back to actually where they were first kind of introduced to the Ethereum space in a talk at DevCon by Doncrod Feist and Carl Beek around trustless validators, the trustless staking pools in ETH2. So in 2019, this was around the time that the ETH2 spec picked up the BLS signature scheme, and they had this new homomorphic additivity to play with. And this is where they realized you could do these like distributed validators. However, the problem that they kind of foresaw and spent most of the time in the talk talking about is how do you penalize the lazy validator? The one that's offline, or the one that's running on underpowered resources, the one that's kind of not running any EL or CL at all and is just pretending to agree with what everyone else says. This is what we call the like lazy validator problem. And the short answer is there's no magic bullet for kind of knowing, is this person honest and far away, or are they nearby and running on like an under-resourced node or something? There's been lots of research in the space, including the like proof of custody work that the original ETH2 spec considered, and we're doing some interesting work with verifiable delay functions and delay towers at the moment, trying to use VDFs as a way to prove access to the fresh beacon state, being like, yep, I definitely had beacon state at the right time because I have like all of these VDFs to prove that I couldn't have kind of, you know, caught up in time. On this front, trying to come up with some objective measure of who's online and who's offline is an interesting game, one that there's no kind of like perfect answer for, but if you can get with something relatively objective, you can use that as the base layer for like rewarding and penalizing people on top of it, which is kind of what I'm getting to in the next slide, which is if you have this, you know, proof of participation, how do you then get this to L1 where the like validator rewards are being streamed to? If you were, for example, to publish this data once a month, that's a known drag on rewards. It's kind of like a pretty fixed cost. You'll end up being, making less rewards than a normal validator, which is not something we want to do. If you do the same thing but on an L2, you still have to pay the call data costs of kind of getting your call data published, still have kind of an overhead. If you do something purely like fraud-based, where you only kind of report and hit the chain when somebody's offline for like a minimum floor, that's not bad. It becomes cheaper, but it still sets a minimum bound on when you can be offline, and like no one can like report you, because reporting you costs more money than you might be slashed or penalized. But some of the ones that we're also looking at that I find frankly interesting are state channels. You have long-lived counterparties here running a well-known protocol. So there is a decent argument to be said that you can do all of this opening and closing of a state channel like in the happy path, all off-chain, never hitting it. But some of the other things we are looking at is, when you do show up on-chain to claim it back, are you closing a state channel? Are you giving a BLS signature? Are you giving a ZK proof? None of these are all like super cheap, so there's always going to be trade-offs involved, but figuring out a protocol that's succinctly provable or like in an affordable manner provable on-chain is kind of a decent part of this like distributed validator protocol work. So that's some of the engineering and then the data sides of things, but there's still quite a lot of like academic research on the DV protocol itself and different things that can be like influenced and need to be taken into account. The first set of things I want to talk about are consensus-related research problems. So in our first version, what we've built today, it uses a synchronous and leader-based proof of consensus mechanism called QBFT. QBFT is pretty well understood. It's kind of a variant of IBFT that loses liveness. But one of the main downsides of it is because it's leader-based, if you have a slow person in there, or worse, an offline node, they keep getting a turn like once every 4 duties, and you have to wait for them to time out. And that's unfortunate because you're wasting precious time. Whereas if you had an asynchronous protocol or a responsive protocol where you can kind of make progress as fast as possible, adding in a slow validator or like a slow node operator doesn't hinder you the same way that it does in like a synchronous leader-based one or a partially synchronous leader-based one. So if we're looking for like, the DV protocol of the future, you probably want something that's more responsive and, sees no negative impact if you add somebody in like New Zealand really far away. You're like, cool, either you work or you don't. It doesn't kind of negatively hinder me. Another aspect, and I think Joaquim kind of covered it a little, is attributability is a very important kind of feature that people would like in consensus. If in this instance with the distributed validator, you had more than the safety threshold of like dishonest nodes, you come to consensus on more than one thing, maybe more than one thing gets signed, you really want to figure out who is involved or give some kind of guarantee that at least 1/3 of the nodes are getting slashed, for example. Adding attributability to a consensus game is one of the kind of key features for the like unhappy path of kind of figuring out what happens in the worst case scenario. We've come to consensus on like dual things. So within this space, I think Eigenlayer have done interesting work on forensics of BFT is what they called it, but it was this figure like trade-off of can you identify everybody that kind of committed the fault? Can you identify up to a certain amount of them? This is the kind of things that we're looking at within the consensus realm. And another one that we talked about even in the previous talk by Casper was the idea of MEV and whether that will impact consensus. And I really enjoy that I had the time to do quite a lot of time talking about honest assumptions or rational assumptions, because everyone assumes kind of honesty assumptions, but the rational assumption is kind of more likely. And what I'm getting at was to where MEV impacts consensus in a distributed validator context. If you're the leader, you're proposing a block, why wouldn't you just kind of like slide a bit of the MEV to some like third EOA that nobody knows about? And can you figure out if like you can get away with that before people know it? And the marginal defector is the one that kind of like earns this reward and stuff. And whether there's like a fix to this is kind of where the like enshrined PBS debate comes in. And can you separate the idea of like proposing rights and building the block and the actual proposing rights? This is something that I think is kind of needed for all validators and something that's been actively worked on the L1 more generally. So there's some of the consensus side improvements, but there's still quite a lot of other research aspects that we're looking at. Some of them being like danksharding. What is the most effective way for a distributed validator to you know, agree on what is available and what's not. You don't want one bad actor to kind of pretend things are available that aren't actually, but you don't want to like recheck everybody's work and be completely inefficient about it. Is there kind of some middle ground where we can kind of all check the same things and have pretty good guarantees about availability without doing kind of unnecessary work? Another aspect that we spend quite a lot of time on is the key generation. So I didn't go into the two types of distributed key generations, but one is where you need to be part of the DKG to know it was honest, and the other is a publicly verifiable secret share. This is where anybody can check the proof to be like, yep, all of these people did the DKG honestly, so long as they're not like Sybil resistant, like Sybil attacking and all the same person. This is probably independent people with the keys. This idea of a PVSS DKG is kind of the gold standard for DKGs, and figuring out can we adopt one that is also provable at L1 in some way, shape, or form is kind of like what a lot of the liquid staking protocols would like to see for like really reducing the trust in, you know, people running a distributed validator. We also spent a decent amount of time trying to figure out, can this pattern make sense for sequencers at the L2 side? This is something that's a hot debate at the moment, and a lot of people are quite involved in. And on the other side, one of the things we look at is key refresh scheme. A key refresh scheme is the idea that if you keep the same public key for your distributed validator, but once a day, for example, everybody picks a new share, and so long as you follow this protocol, we all end up on the right, you know, new polynomial every day. And what's new, you know, super powerful about that is then if you try and compromise private keys, you have to compromise 2/3 of the nodes all in 24 hours before they've done a resharing, and now they're all on a new set of keys, and you know, you have to start the process of compromising them again. This can also go further, and it can be used for like operator rotation, where you can kind of rotate to a new set of private keys and leave behind someone that you didn't want involved because they weren't, you know, performing well enough, for example. And even on the kind of more quantum end of it, I know Justin Drake is very keen on like single shot signatures, and whether you can do something like that for a validator, that would again make it much, much harder to compromise the private keys for a validator. So we've talked about now engineering challenges and how we design something that's kind of, you know, not too risky from a networking and privacy perspective. We've looked at some of the subjectivity and objectivity of data about DVs and whether we can kind of prove this to a smart contract cheaply. We then looked at some of the research challenges involved and like how we can improve consensus, you know, adjust for dank sharding. Didn't mention secret leader election, but coming onto the more like human side of it, there's, you know, lots of coordination involved in distributed validators. And this is where I kind of want to circle back to moving safety risks to liveness risks and kind of mitigating liveness risks with multiple implementations. So if you have a well-working distributed validator solution, you now have, you know, private keys in many different locations. Even if it's compromised, it's not getting slashed. Like, this really reduces the safety risks of kind of causing a good double signing. But if you have one piece of software in every single stack, you still have a liveness risk where, you know, that software can go offline and you're not going to get slashed, but you don't want to go offline, particularly if you're like a large amount of the network. And this is where, you know, having a credibly neutral spec and multiple like well-tested implementations of it goes that bit further and says, yes, we've mitigated safety risks. Now we're kind of in the liveness space. We now have lots of different implementations. That's further reducing the liveness risks. We now have like really, really secure and like decentralized proof of stake. This effort is something that we've been kind of working on for quite a long time, but it's something that we've recently kind of kicked up a notch with the Nethermind team, where we began work on a distributed validator protocol. And this is at first a research and specification effort, and generally, you know, an effort to build multiple implementations. But the goal here is to take in some of the things that I've talked about today, which is, you know, good ways to design it from an architecture perspective, things we can do from like attributable consensus, trying to figure out if we can make something succinctly verifiable so we can prove it on chain, and generally make something that's, yeah, credibly neutral and that, you know, can be the high availability software for all validators on Ethereum going forward. And that's kind of where we're working towards at the moment. I'll show you in a minute. We're making some of these posts available on our research forum this week, if not like in the next kind of couple hours. But to talk a little bit about, you know, making such a protocol, one of the things that I think is very synonymous with distributed validators is the idea of proof of work mining pools. Back in Bitcoin's kind of heyday, Bitcoin started in the start of 2009. before the end of 2010, there were like CPU miners that were like, hey, there is no chance of me producing a block on my own with just a CPU. I need to like team up with other people, and together we'll be able to share the chance to like produce blocks in proof of work. Proof of stake we see is kind of going down a very similar avenue. You know, for the first 2 years, anyone could get involved, and at this point it's getting like, you know, extremely prohibitive on a cost perspective to kind of, you know, produce blocks on your own. And people are starting to look at like, you know, what is the fix here? Do we all go to DPoS and like kind of like delegate to somebody else? Preferably not. The goal is to have people involved in the proof of stake protocol, like no matter how small. And we see distributed validators as being that kind of analog to like mining pools. And mining pools haven't gone anywhere. They've been, you know, in operation for like 13 years. They, you know, extract revenue, and they're like generally seen as a resource. But if you're, you know, early in Ethereum's proof of stake consensus kind of formation, and you're figuring out how do we want this equivalent to like mature, we want probably a spec, we want something incredibly neutral, we want something that probably funds public goods and like funds the client teams that develop this software, because that's how it'll be like sustainable. We take a lot of inspiration from the likes of people like Optimism, and particularly this EIP 1890 that some of you might remember. Back in 2019, there was a proposal introduced to have proof of work mining rewards given to like a public goods Gitcoin like kind of matching pool. There was a lot of debate back and forward about whether this would be a good idea or not. And generally the kind of conclusion was that this would be too risky to put in the base layer because it might get kind of compromised. We see distributed validator protocols as kind of a sensible layer to be like, oh yeah, maybe this is where we do a bit of like funding of public goods. And as people go to use the software to like take part in proof of stake, maybe this can be somewhere that can, yeah, fund client development into the future and make Ethereum kind of more robust and decentralized. I'm kind of coming to the conclusion, and just before I do, I wanted to kind of give you an idea as to, you know, as I said, there's no answers here. Most of this is kind of like research problems, questions, ways to get involved. So I would say if anything I've said today kind of interests you, I would say kind of consider joining our Discord community. You can test out these DVs on Girly or Mainnet if you're brave. You can kind of get in touch with us. The QR code beside it is a link tree, which is all of our kind of info. And kind of most importantly, we're hiring. We're hiring kind of researchers, Go devs, mathematicians, Solidity devs, product owners. So like we've quite a lot out there that I would recommend. But just lastly, before I kind of go on to a Q&A, in terms of kind of the order of operations around making distributed validators, some people maybe favor kind of making some spec first and then making implementation. My background is maybe more on the eng side than the researcher side. It felt more sensible to me to make a V1, like make an implementation, prove that it works, prove that it's real. And when it starts to get adoption and find product market fit, and people start to say, hey, we now need to kind of address these liveness issues, this is when you can start to kind of make this more forever protocol, and you can pick some of the more like kind of long-term changes and, you know, pick a more out there consensus mechanism, a more out there DKG. And we see it a lot like how Ethereum was developed. They had this like plan for proof of stake from the beginning, but they were like, look, let's, you know, fork Bitcoin and add the EVM. Let's start with kind of the MVP, and we can work our way towards a spec and a protocol and proof of stake. This is something that we're trying to follow at OBOL, which is kind of make an implementation, show that it's real, get people interested, get people like believing that DVs make a load of sense, and as it starts to kind of take off and find product market fit, work on this protocol, work on making it incredibly neutral, work on getting like many independent specs and like implementations on, work on getting kind of like a feedback loop that will kind of keep this resilient and funded. And yeah, that's generally our goal, is to make a distributed validator protocol. Thank you very much. I'll take a question now if you want.
Questions?
Hi, I really enjoyed your talk. So validators run consensus, and distributed validator participants run consensus for each step in consensus. Do you foresee the need ever for distributed validator participants?
Need is a strong word. I've seen it done already in terms of people already have like high availability for their remote signers, which is like kind of the private keys behind it. So yeah, it's not the end of the world for there to be consensus on consensus on consensus. I wouldn't say there's, you know, a need per se, but this is the idea of how we get like an next order of magnitude scaling for consensus. You know, the core layer has gone to like, you know, 1 million participants. That's super impressive. But if you want to keep going like further, it's, you have 12 seconds, play a smaller game between it. And that's kind of how we see you go from like 1 million to 10 million participants in consensus. But would I say need for like a third layer? Not necessarily. Would I say it's done? Yeah, I think it will be done and has been done.
Thanks.
Yes, I wanted to also come back on this. You're changing the trust assumption underlying, right? You have one of the 128 validators that's now suddenly distributed.
Yes.
And why are not the distributed, say, among 10? Why these 10 are not participating in the main as one of each one, a separate one in the 128 set?
Because they generally can't afford to.
Sorry?
They generally can't afford to be part of like the main set. Like each of these 32 Ether is quite prohibitive. So it's
from
like,
the mining pool.
yes,
Okay.
exactly.
Okay.
A few more?
Yeah, if say someone today takes just a Cosmos SDK, what is still missing? Like, can you just claim that's kind of a poor man's distributed validator before everything else from Obo is ready?
You can have, I would argue there's already that equivalent of like distributed validators on Tendermint in the form of like Horcrux.
Right.
However, Cosmos is slightly different in that because it's ED 25519, you can't just aggregate signatures. You have to have like quite an involved like MPC signing process. So distributed validators in the current Cosmos set have access to the private keys, which is a little scary if your like, client is compromised and they can sign whatever they want and get you jailed. If they were using something like homomorphically additive like BLS, you could have the kind of current design where it's much lower risk of like, if it is compromised, you're not like risking safety in the same manner. But yes, you could do this in like Cosmos as well.
Okay, good, thanks.
Last question.
Last one I go.
Cool, thank you. Great talk. My question is related to the topic of lazy validators.
Yes.
So let's assume we have one highly trusted, highly available data source with all the chain data, and all the other validators just kind of, they're lazy, so they proxy everything to that one highly trusted, highly available data source. You mentioned that you've heard people looking into VDFs and other approaches to try and solve this problem. And even though I don't expect there to be a solution, I'm curious what else you've seen, what other ideas you've seen floating around to try and solve it, maybe aside from just VDFs.
Nice, yeah. So you hit on one of the important ones, which is data availability. So in the happy path, when like 4 nodes are online, they can all kind of vote who's online and offline. And when you have consensus, that all works. If 2 out of the 4 nodes go offline, you no longer have consensus. They can't agree as to who is online and who is offline. So normally you need some sort of like data availability layer where you can be pushing these like partial signatures for cheap, and then some like external party can come on and say, well, I see all of these partials, and then eventually they go missing. That must be where it went wrong. And that's kind of one of the ways of having an external observer is like solving this data availability problem, having this trusted external place where you can like push all the partials. And then the other side, as I mentioned, is the VDF one, which is, people were online because they have VDFs to prove it. Don't want to waste too much time, but basically the idea is if you put the beacon state root, so like the tip of the chain, as a pre-image to your VDF, you could not have started the VDF until that was available. So if you're trying to backtrack and you're trying to like make up a 2-hour delay, you might be able to do so if you have slightly faster like hardware, but you can't get out in front because you don't have the beacon state root. So that kind of slows you down. So that's one of the ones that we can say, you can show up to the L1 with the VDF and someone can check that VDF and be like, cool, they definitely were online. They have like proofs of it. And that's, different to the data availability, like pushing things into data availability layer. But I'd argue they're the 2 main ones. So something like with the VDF and like a validity proof, or having like some DA layer and doing it like in a fraud-based way, getting a third party in to like check, and either like agree with the fraud claim or like not with the fraud claim. They're probably like the 2 main ones.
Okay, I'll follow up with some more questions later.
Absolutely.
Thank you.
Yeah, let's continue offline, and thank Øystein again.
Thank you very much. See you guys.
And we are adjourned, and come back at 3:30 for the next session.
Hi, Dan. We're not starting yet. Okay, we're going to start again in 2 minutes. So if everybody can grab their seats. Not yet. We'll wait 2 more minutes. Okay, 2 more minutes. All right, so let's get started. Last session of the day. This session is, we're going to have a treat. This session is on zero-knowledge proofs. We're going to start with 2 talks on folding, and we're going to end with an invited talk by Eli Ben-Sasson on Starks and Starknets and where that's going. Okay, so the first lecture in the session is on Hypernova, recursive arguments for customizable constraint systems, by Abraham and Srinath is going to give a talk. Looking forward to your talk.
Thanks, Dan. So this talk is about Hypernova, which is a new recursive argument for customizable constraint systems. Given that this session is titled Snarks from Folding Schemes, I thought I'll start by recalling what a snark is. A snark is a non-interactive protocol where the prover proves that it knows some witness to some statement. For example, it could prove that it knows a value x such that SHA-256 applied to x results in a public value y. In general, the snark prover proves that it knows a value w such that the circuit applied to w along with some public input x makes the circuit output 1. A trivial proof system is one in which the prover just sends its witness and the verifier checks if the circuit is satisfying under that witness. A snark achieves better properties. First, the size of a proof is smaller, for example, sublinear or polylogarithmic in the size of the statement proven. The cost to verify a proof is also smaller than the cost to check the witness. Given that snarks have many applications, there has been tons of work over the past decade or so. Unfortunately, the prover time remains a key bottleneck in snarks because they require many MSMs or FFTs or both. In general, the proving algorithm is also harder to parallelize or distribute. These are exactly the problems addressed by folding scheme-based snarks. In particular, they provide the fastest prover when proving semi-structured circuits. These new snarks also have a prover that's far easier to parallelize and distribute. More recently, there has been this notion of lookup singularity. One way to think about this work is that they are a more efficient way to represent computation. In particular, they actually need folding scheme-based snarks to be able to scale to large computations. So now let me introduce what a folding scheme is. At a high level, it takes as input some statements that we want to prove. For example, 2 circuit satisfiability instances defined with respect to the same circuit. Then it just outputs a folded statement. There are some key properties here. First, the size of the output statement is the same as the size of one of the input statements. So it provides some sort of compression. Second, if the input statements are true, then the output statement is also true. So it can be proven. If any input statement is false, then the folded statement is guaranteed to be false. So if the prover knows a satisfying witness for the folded statement, then it also must know satisfying witnesses for the input statements. So proving the folded statement is equivalent to proving the original input statements. So here is a sketch of how we would build a snark from a folding scheme. Suppose we have n statements. These n statements could be all independent. For example, a batch of signature verifications, or they could all be steps of a single computation. For example, verifying some roll-up transactions that all share some global state. We can apply the folding scheme on a pair of input statements to get a folded statement. We can keep doing this recursively until we just have one folded statement. By the properties of the folding scheme, proving this one folded statement is equivalent to proving all the original n statements. So this folded statement can be proven just by providing the witness. The size of this proof is linear in the size of one step. In particular, it's independent of the number of statements that were folded. So with a folding scheme, a proof is roughly the witness of one step, so which can be megabytes in size depending on the number of gates in the step. In contrast, snarks provide tiny proofs, for example, kilobytes. They're also very efficient for the verifier. They can also prove unstructured computations. Whereas folding schemes are prover efficient. They get this efficiency because they focus on the semi-structured computations. So the best approach is to actually combine both. In particular, we use the folding scheme as a prover efficient pre-processing to fold n steps of a computation into one, and then use snarks as the verifier efficient post-processing to prove that one folded step. The result of this combination is a prover efficient snark. Given this promise, there has been an explosion of works on folding schemes over the last few years. NOVA and BCLMS papers were released around the beginning of 2021. NOVA was actually inspired by a large line of work, most notably the inner product arguments or bulletproofs. So these protocols fold two inner product instances into one. NOVA can then be seen as a generalization of this pattern to arbitrary circuits. Last summer, we finished a full implementation of NOVA. This was developed as an open source project. It was actually shaped by requirements for a NOVA-based verifiable delay function, which is a collaborative effort among EF, Filecoin, Supranational, and Microsoft Research. The NOVA code depends crucially on libraries built by many of these partners. In 2023, there was a lot of proposals to improve folding schemes. I think these were catalyzed by several things. First, there was a ZK whiteboard session by Justin Drake. Then Nico from Geometry released a white paper that extends NOVA to Plonkish arithmetization. Finally, there was an excellent lecture on folding schemes by Dan. Finally, this summer, there were a bunch of works, and I'm going to talk about one of these works in this talk. Later in the summer, there was also a bug in the original implementation of NOVA on a 2-cycle of curves. We later released an approach that sort of overcomes some of these difficulties with instantiating folding scheme-based snarks on a cycle of curves. Just this morning, there was a paper that sort of shows how to extend Hypernova to proving distributed computations. It might be difficult to keep track of all of these works, so there is an awesome folding page that has a list of all the resources related to folding. So now that I've given an overview, let me start with Hypernova in a nutshell. So it's a snark for semi-structured computation, and it's based on folding schemes. So it can prove sequential computations. It can also prove distributed and concurrent computations, for example, MapReduce. One of the key improvements over general snarks like Plonk or Marlin is that the proving speed is approximately the speed to commit to the witness with an MSM. This can be significant. For example, it could be orders of magnitude lower than those general purpose snarks, depending on the circuit. There are some exciting subsequent works like Protostar. As I'll show you later, there are some advantages to Hypernova. So in the rest of this talk, I'll first provide a simplified problem statement. Then I'll describe prior approaches to recursion. Then I'll provide some information about NOVA, and then I'll switch to Hypernova. Finally, I'll provide a high-level comparison with Protostar. So at a high level, our goal is to prove some structured computation was executed correctly. As an example, we want to prove that some non-deterministic computation C applied to some initial input Z0 results in an output of Zn. By non-deterministic, we mean that this circuit at each step can take some witness from the prover. For the purpose of this talk, I'm going to ignore several things. For example, we might want each step to apply one of the circuits rather than just a single circuit. We might also want parallel proof generation, meaning the steps of a computation are executed at once and then folded in a binary tree fashion. Or we might also want proofs of distributed or concurrent computations. But the good news is this machinery can support all of these, but for this talk, I'm going to ignore that. So this sequential model of computation is already very powerful. For example, we can already build a VDF where C could be one or more invocations of some delay function like minroot that takes non-trivial sequential time to compute. In a ZKVM, this C is a step of a VM, for example, EVM or LLVM, or a CPU like RISC-V. In case of ZK Bridge, this C validates state rules according to the consensus rules of a blockchain. In case of ZKML, C applies one or more layers of the model. In case of photo proof, C could apply a particular transformation to a photo or a video or an audio file. In case of public key transparency, this C checks if the public key directory is append-only in each epoch. So how do we prove such incremental computation? The high-level idea is to not prove that a step was executed correctly. Instead, we would prove an augmented circuit. In particular, the prover proves that it has executed not only C, but it also proves that it has executed a verifier expressed as a circuit. And this verifier as a circuit verifies the correct execution of the prior step. So the invariant here is that a proof at any step proves the correct execution of all prior steps in the sequential computation. So there are broadly 3 approaches to achieve this. The first one is full recursion. The second one is accumulation, and the third one is folding. So in the first one, the pi is a snark. And this verifier circuit fully verifies that snark. And it's implemented in many schemes, like Fractal, Plonky2. In the second approach, pi is a snark, but the verifier circuit partially verifies that snark. This was implemented in the Halo paper. A major downside of this is that a verifier circuit is actually pretty large, so it has very large recursion overheads. They also do not provide a faster prover than the base snark that was used. So in contrast, in the case of folding, this pi is a commitment to some witness plus some auxiliary information. V simply computes a random linear combination of these commitments. So this can be quite small. For example, the verifier circuit in case of NOVA is just 10,000 R1CS gates. This approach was implemented in NOVA. Turns out folding provides a much faster prover than general snarks. For example, compared to ECC-based proof systems like Plonk or Marlin, just does far fewer MSMs. For example, just 2 MSMs compared to Plonk's 11 or Marlin's 22. NOVA also has free addition gates. For example, for circuits that have a lot of additions, think of circuits that have Poseidon, speedups are even more significant. So NOVA is also faster than Fry-based proof systems like Plonky2 and Starkey. For the SHA-256 benchmark from Cellar, NOVA is 50 times faster than Plonky2 and more than 2 times faster than Starkey. This might actually be quite surprising because Starkey and Plonky2 use 64-bit fields, and NOVA uses a 256-bit field. So for SHA-256, it turns out all the witness elements are quite small. So NOVA's MSMs are fast. This is also one of the things that was leveraged by Lasso. So one of the key takeaways here is that when comparing MSM to Fry performance, it's crucial to consider the bit width of all the scalars in the MSM. They're not always going to be 256 bits. So given that we already get very good performance from Nova, are we done? Why do we actually need Hypernova? So the short answer is Nova uses R1CS, but Plonkish, which is another arithmetization, is preferred in practice. Fortunately, Sangria shows that Nova extends easily to degree D Plonkish constraints. But a major downside of this work is that the prover must perform D MSMs of size proportional to the circuit size. So one of those MSMs is to commit to the witness, and D-1 MSMs is for committing to the cross terms. To see why this is a downside, let's consider an iteration of min root. So in case of R1CS, it takes 3 constraints to represent an iteration of min root. So Nova would do 6 exponentiations per iteration, plus some cost to compute 1 cross term, which are all field operations. There is a degree 5 constraint for expressing an iteration of min root, and we just need 1 constraint. Sangria's cost would be 5 exponentiations per iteration, plus the cost to compute 4 cross terms. So Hypernova, in contrast, can do 1 exponentiation per iteration, plus approximately the cost to compute 4 cross terms. So what this means is that Hypernova can be 5 times faster than Nova or Sangria for this particular application. So to design Hypernova, we could have built a folding scheme for Plonkish. Instead, we provide one for CCS, which stands for Customizable Constraint Systems. CCS, the motivation to introduce CCS is that Plonkish and Air are overly tailored to the particular characteristics of the proof systems they are built for. In contrast, CCS is separated from the proving system used to prove CCS. So to give a quick example, Plonk internally uses a permutation argument. So Plonkish only supports a restricted form of linear constraints, which are called copy constraints. In particular, the Plonkish constraints can only enforce equality between 2 different variables in the constraint system. Whereas with R1CS and CCS, constraints are inlined, or these linear constraints are inlined, which means they are free when used with multiplication gates. So in more detail, a CCS circuit is specified with multiple sparse matrices and multi-sets. There's also a public input X. A witness W is satisfying for some Z, which is a concatenation of W, X, and 1, if this equation holds. So this may look complicated, but let's consider the case of R1CS, which CCS generalizes. In case of R1CS, Q is 2, and these matrices are the familiar ABC matrices. So M1 is A, M2 is B, and M3 is minus C. If we expand that equation, we get, the multisets are given by this 1 and 2, and the second multiset contains 3. And if we expand this, the original equation, we get this AZ times BZ minus CZ equals 0. So a key takeaway here is that these multisets and matrices can be programmed to represent arbitrary polynomial constraints. So now that I've introduced CCS, I'll provide an overview of Nova's folding scheme, which provides a folding scheme for folding these CCS instances. At a high level, our goal is to fold these committed CCS instances, where the verifier holds a commitment to the purported witness. A challenge, of course, is to avoid those order D cross terms that I mentioned earlier. As a starting point, we break this problem into 2 subproblems. First, we reduce a CCS instance into a restricted form of CCS called a linearized CCS. Suppose we call that a fresh instance. Second, we fold that fresh instance with some running instance, which is also a linearized CCS instance, to get an updated running instance. So what is this linearized CCS instance? It's a restricted form of committed CCS. Just like CCS, it has these matrices, multisets, a commitment to the witness, and some public input. In addition, it also has a scalar U, some challenge R, and a set of scalars where the number of scalars is equal to the number of matrices. A witness vector is satisfying if for the concatenation of W, X, and U, this linear relation holds. And we can think of this as an inner product relation because this equation involving the matrix M, I, R, comma, Y can be thought of as taking a weighted combination of all the rows of the matrix and then taking an inner product with the vector Z. And as before, we also want the C to be a commitment of the witness. So it turns out that linearized CCS is not NP complete because it can only encode linear constraints, but this is acceptable in our setting. So now let's see how to fold these linearized CCS instances. As a starting point, I'm going to focus on the simpler goal where we're going to fold 2 linearized CCS instances with the same challenge R. The protocol is actually quite simple. The verifier just simply sends a challenge gamma, and the verifier takes a weighted sum of all the elements in the instance except for R. The prover similarly takes a weighted sum of the witnesses, and they both, the prover outputs a witness, the verifier outputs this instance, and it just copies over the value R into the output instance. We can actually see completeness holds by linearity. For example, if we take the output value Vi, it's the weighted sum of the input values, and we can expand, because the input instances are satisfying, we can expand that into a product between the matrix and some vector. And because the matrices are the same, we can collect the value inside. And this is exactly the satisfiability check for the output instance. So if the input instances are satisfying, the output is also satisfying. So we solved one problem, which is a folding scheme for this linearized CCS instance. But it turns out we actually introduced another subproblem. In particular, the folding scheme that I described requires the 2 linearized instances to have the same random challenge R. So we need a new black box that can actually re-randomize the running instance to have the same challenge as this fresh instance that will be output by the first box. It turns out it can actually solve both problems in one shot with a linearizing reduction. The verifier takes as input a linearized CCS instance with some randomness R1 and a CCS instance. The prover takes as input witnesses to both of these instances. And then they have the same common structure, meaning they have the same matrices and multisets. We then run a protocol where we output 2 linearized CCS instances that have the same randomness R, and the prover just copies the witness. And the core idea in this construction is to use the sum check protocol. It reduces CCS into linearized CCS over some challenge R, and it also re-randomizes the input linearized CCS instance to the exact same challenge R. So in summary, the folding scheme has 2 components. The first component invokes the sum check protocol. It only involves finite field operations. There are no cross terms that need to be committed. And the second box just takes a random linear combination of those instances. A key takeaway here is that this folding scheme is a drop-in replacement for Nova's folding scheme. It performs 2 MSMs instead of it performs 1 MSM instead of Nova's 2 MSMs. So it's even better than Nova's folding scheme for degree 2 constraints. Then, more crucially, the number of MSMs is 1 regardless of the degree of the constraints. Only the finite field operations grow with the degree. Next, I'll present some high-level comparison with Protostar, which is the topic of next talk. There's some perception that one can actually do better without the sum check protocol. So I'm going to use 3 axes: prover time, the verifier circuit size, and support for multi-folding. By multi-folding, I mean the ability to fold more than 2 instances at once. It turns out that this ability is required for binary tree parallel proving and also to prove distributed computations. So on the prover time, here's a table that compares Hypernova's prover on 2 axes, size of an MSM and the field operations that are performed. The key takeaway here is both have the same prover time because SumCheck is actually super fast. So on the verifier circuit, Protostar performs 3 scalar multiplications, and it performs fewer hashes compared to Hypernova. However, Hypernova's verifier circuit can be concretely low because of 2 things. One is by using cycle fold, we can actually reduce the size of the circuit on the second curve in the curve cycle. And by using snark-friendly hashes, we can keep the concrete cost of this hashing quite small. Finally, Hypernova supports efficient multi-folding. By efficient, I mean that these log m hashes are actually amortized across all the k different instances that we want to fold. Whereas Protostar does not support multi-folding, there is a recent proposal called ProtoGalaxy that does support multi-folding, but it requires logarithmic number of hashes that grow with the number of instances to be folded. So key takeaway here is that Hypernova retains some advantages in some contexts. Another misconception that I want to clear is that folding special sound protocols is more expressive than folding CCS circuits. In these interactive protocols, each round the prover sends a vector, the verifier sends some challenge, and these interactions proceed in k rounds. The verifier then runs a set of degree D checks on the concatenation of these vectors. This type of protocol is useful for realizing lookup arguments because these lookup arguments require at least one round of interaction. It turns out that there is a standard technique to perform such randomized checks inside circuits. For example, it's described in this book. And I'm going to just quickly go through that recipe. So we just first make the protocol non-interactive using Fiat-Shamir. Then we take the CCS witness to have k components, one for each of the vectors that were sent in the interactive protocol. Then we take Z to be the concatenation of all those vectors along with some X augmented, where X augmented is a concatenation of X and the challenges. And we also require these challenges to have been obtained through Fiat-Shamir transformation. And then we could use CCS to enforce arbitrary constraints on those concatenated vectors. A key takeaway here is that once we have a folding scheme for CCS, it can be used as a folding scheme for any non-interactive special sound protocols. So to summarize, folding schemes unlock prover-efficient ZK snarks. Hypernova is a new prover-efficient ZK snark. Hypernova is surprisingly more powerful than it appears. For example, it has the same prover efficiency as Protostar. It supports efficient multi-folding. It can fold arbitrary public coin interactive protocols like lookups. It can also support multiple circuit types, for example, non-uniform IVC via Supernova. I didn't discuss this, but it can be done. With that, I'm happy to take questions.
Great. Are there any questions? Actually, let me start by maybe asking you about the implementation status of Hypernova. Yes. So how can you, I think you said something about the implementation, but can you say a bit more about how complete is the implementation? Is it commercial strength? Is it available, and so on?
So Nova implementation is public, so it's been out from a year. But the Hypernova, I think there are some implementations by others. We haven't released an implementation yet.
I see. Okay. So hopefully that's coming. Or? Yes. At some point. Okay, good. Are there any other? Yeah, please. There's a mic up there.
What does the developer experience of writing circuits in Nova or Hypernova look like, and how should we be prepared for that?
Yeah, so there are currently, I think, a couple of different ways to use Nova. One of them is you could use Bellperson, I think, which was recently upgraded to Bell Pepper. So you could write a circuit in Rust and Pru. There is another one where you can use another tool called Nova Scotia, where you can write your circuits in Circom and then feed it to Nova using Nova Scotia. And I think there is one more, Lurk. You can express your programs in a Lisp-like language and then prove it using Nova. But I think there are maybe more that I'm missing.
Yeah, please.
Hey, thanks for the talk. Can you go to the last slide again, please?
The previous one?
Oh, we need to go to the slides?
No,
you guys
after
go back
this.
To the slides? Yeah.
Oh, before this?
No, after the last one.
Sorry, is this the one?
Take it away.
After this is the summary.
Yes. So I'm curious about actually that point, that you can fold arbitrary public coin interactive protocols. Can you expand on that, please?
Yeah, so it's exactly this one. So we take an interactive protocol, we make it non-interactive, we could then express the knowledge, we can express that protocol as a circuit. meaning that if the protocol is knowledge sound, it's equivalent to the circuit being satisfying.
Okay, so like expressing it as a circuit and doing CCS and Hypernova on that.
Yeah, so the verifier like takes, so in these protocols, the verifier takes concatenation of all the vectors, performs degree D checks. We could write a circuit that takes those vectors in the witness and performs the same checks.
So you haven't like the lookup that you have in the paper in Hypernova, have you tried to like integrate it into the CCS constraint system?
So, that particular lookup argument can also be done this way. So it's described as a separate folding scheme, but you could integrate that or any other lookup argument, including lasso or log derivatives into this.
Okay. Okay, thank you.
Thanks.
Maybe we'll take one more question.
Yeah. So first, thanks for the nice talk. And it's cool that in the d=2 case, you got the number of MSMs down by 1 relative to NOVA. I guess my question is whether NOVA retains any advantages if you're dealing with R1CS. Like
yeah.
other costs beyond the MSM in
Yeah, I
which it's
think
better?
there may be some advantages in terms of the verifier circuit. For example, NOVA, as it exists, it just performs a constant number of field operations, hashes, and scalar multiplications. Here, we would do logarithmic number of hashes. Yeah, that might be one trade-off.
Thanks.
Great. Yeah, thanks, Trinas. This was a really, really fantastic talk. Thank you so much. Okay, our next speaker is Bin Yi, who's going to talk about Protostar, and this is joint work with Benedikt Bunz. So, Bin Yi, the floor is yours.
Hello. Okay, yeah, thanks for the introduction. My name is Bin Yi, and today I'm going to present Protostar, which is a new generic and efficient IVC scheme. And this is joint work with Benedikt Bunz from Espresso Systems. So in the blockchain world, we think there are many objects following an iterative pattern of computation. For example, a delay function is defined as a step function executing t times, where t is some dynamic hardness parameter. Also, blockchain, you can understand it as something like state transition machine, where the ledger state is repetitively updated by executing transactions block by block. Another example is a Ethereum virtual machine, or EVM, which is basically the computational model used by Ethereum for smart contract execution, where at each step you are executing one of the many supported OP codes. So in this talk, our goal is to enable efficient verification of this type of computations, which leads to powerful applications like a verifiable delay function, succinct blockchain like Mina, and also zkEVM, which allows you to prove correct execution of smart contract without letting the validators to receive this execution trace and re-execute the program. So more generally, we want to solve this problem, give some initial input and some final output, this iterative computation, where at each step you ask some step function given some online witness. The prover wants to convince the verifier that this execution was done correctly, but without sending all this intermediate witness and let the verifier to re-execute everything. So key here is to want to really have the succinct proof and make the verifier really efficient. Interestingly, this primitive for solving this problem has actually been introduced back to 2008 by Paul Willems, even before Bitcoin was invented. So this is called IVC scheme, or incrementally verifiable computation scheme. So here, instead of sending the entire intermediate witness for the execution, the prover can generate a really tiny IVC proof and incrementally update it as time goes by. And the correct verification of this proof implies correct computation of this entire execution. So we want completeness, meaning that the prover should be able to generate an update to the next IVC proof, given the previous IVC proof and the online witness for the last execution step. Also, we want knowledge soundness, meaning that the prover, if he can pass the verification check, he should actually know the right witness for this computation. It was actually well known that IVC can be constructed from snarks, which is another powerful primitive for proving NP relation statements with some fixed size. The idea is simple. Well, the IVC prover will we'll just generate a snark proof for the statement that first, the last execution step of this step function was done correctly, and second, the previous IVC snark proof was correctly verified. And this implies that all the previous computation were done correctly. So this kind of a recursive snark idea is really neat, but however, it's not commonly used in practice. This is mainly because this recursive circuit for representing the snark verifier is really, really expensive. Therefore, people are asking whether we can construct IVCs from even weaker primitive without using snarks. And the answer is yes, and recently there are some really great works that construct IVC from another weaker primitive called a split accumulation scheme or folding scheme. Intuitively, this kind of scheme is basically allows you to fold multiple instances with pairs of some relation into a single one. So now instead of checking them one by one, you only need to check the last folded instance. So more specifically, there is an accumulation prover that tries to fold multiple instances with pair into a single one. And also, we need an accumulation verifier that takes some input instance and some folded instance and check they are consistent with the help of some helper information from the accumulation prover. And the key highlight here is that this accumulation verifier is really lightweight, meaning that it's much, much more efficient than snark verifier. And this is the key why we can have a much more efficient IVC construction. The reason is that in this recursive circuits, now we can embed this more lightweight accumulation verifier rather than this very expensive snark verifier inside the circuit. Finally, there's a decider check that the last fold instance is correct. And this primitive has similar notion of completeness and knowledge soundness. It was also shown that we have a really efficient IVC constructions given this split accumulation scheme or folding schemes. However, existing accumulation schemes have the following kind of limitations. First, there are many constructions of the folding, but they are usually having very different flavors of description and security proofs, and there's no unified and general framework for analyzing and deploying them in practice. So that's the first issue. And second, the most popular and most efficient scheme usually use the so-called R1CS-based constraint system, for example, NOVA. And this is basically a language that allows you to represent the relation statements in circuits. However, it's kind of less expressive compared to some recent advances that introduced the so-called high-degree custom gates and lookup gates, which is more expressive, meaning that with a single gate, you can express more functionalities. We do know there is some elegant work that support this kind of front ends. However, as accumulation scheme itself is less efficient compared to NOVA. Finally, we know that most of the schemes are having a relatively poor support for so-called circuit branching. What does it mean? It means that in some cases, at each folding step or each execution step, the step function might only trigger one of the branches in this big function. One typical example is actually EVM, where in the configuration you have hundreds of OP codes being supported. But at each step, you only execute one of the many possible OP codes. And in the traditional IVC, you still need to prove all this, every possible branch circuits, and that can make the scheme really, really expensive. Given this, we have the following contributions. First, we introduced a new general recipe for constructing the so-called folding scheme as well as IVC scheme, where the NOVA is just a special case in this framework. Along the way, we also construct some folding scheme that can support really expressive relation, for example, high-degree custom gates, large lookup table, and efficient circuit branching. In summary, in this resulting IVC, the dominant proving cost is only a one multiscalar multiplication of size of witness, and in this recursive circuit, is only dominated by 3 group exponentiations. Compared to a concurrent work, Hypernova, which is also a great paper, and it turns out that I think we have a cheaper lookup support, because in our setting, the lookup support is almost for free. And second, in this recursive circuits, we have a log factor number of hash and field operation, but with the trade-off 2 more group operations. Okay, so this is the background, and now let me start to get some meat, and I will start by explaining the general recipe for constructing folding scheme. Recall our goal is to fold multiple instances with pairs into a single one, and we use the following framework. First, we design some so-called special sum protocol for this MP relation. And then this is a really key step. We transform this protocol into another protocol, but for which the verify is much, much simpler. Basically, the verify only needs to check one single algebraic equation in this protocol. And after that, we use some standard trick to make it non-interactive, and we introduce a generic way which extend NOVA to obtain a folding scheme for the verifier check in this NUC proof. The highlight here is that number of group operation on both the accumulation prover and the verifier side now is independent of the degree of the check, which makes it particularly friendly to support high-degree gates. Before delving into details, let me quickly recap what it means by special sum protocol. Given some protocol for proving some relation, we say it is K special sum if K different accepting transcript allows you to extract a valid witness for the relation. For example, in this really naive, very naive example of proving element-wise product relation, what prover can do is directly just send these long vectors, and the verifier will just check the set of equations, which are kind of expensive. But however, this protocol is one special sum because every transcript is exactly a witness. And we care about three parameters in the class of special sum protocol. First is the number of interaction, the number of prover messages in this interact protocol. And second is the maximal degree of each equation checked by verifier. And last is the number of equations checked by the verifier. And in this example, you see that R equals 1 and D equals 2 because every equation is a multiplication check with a degree 2. And L equals M because there are n different equations being checked. So I'll add a note why we care about this strange special sum protocol. There are two reasons. First, compared to directly construct a folding scheme from scratch, it's much, much easier to analyze and design a special sum protocol because we have no succinct or non-interactive requirements. For example, you can see here that we can send a really, really long witness, and the verifier can do a really, really expensive verification. The second reason is that compared to directly folding a relation statement, as NOVA did, use special sum protocol enables us to represent some other really complex relation, like lookup, using a much simpler special sum protocol, which makes folding much easier. So now suppose we already get a special sum protocol for some target relation. It's straightforward to transform it in non-interactive proof using some very standard trick in cryptography, like commit open and Fisher-Shamir. It was also proven before that the transformation is knowledge sound as long as the original protocol is special sound. Now our goal has been reduced to build accumulator for this NUC proof, which is equivalent to build accumulator for the relation we care about, right? So in this NUC proof, we split it into two parts. The short part is called proof instance, which consists of some really short commitments and the verifier challenges in the original special sum protocol and some public inputs. And the larger part is the opening of these commitments, which are the possibly long prover message in the original special sum protocol. And we say this in the relation if the set of L equations checked by verifier are satisfied. And every equation is just an algebraic formula of degree D. And now we want to build an accumulator for it. So we exactly use the same kind of format. The only difference here in the accumulator is that we add one more arrow vector commitment, for which the arrow vector is put on the right-hand side of the set of equation being checked. This is some trick also used by NOVA, and you can understand this as a relaxed version of NUC verifier check, where each equation, it doesn't need to be equal to 0, but you can equal to some like arrow as long as this arrow is committed in the instance. Now the key problem now is that given some existing accumulator, how to fold some online NUC proof onto it to obtain a new accumulator so that a new accumulator is satisfiable if the existing accumulator and NUC proof are satisfiable. And this reduced to prove that two sets of equations here in the right, like upper right, that are satisfied. And we do this by doing an interpolation of these two sets of equations by combining the inputs, basically combining the messages and challenges using this linear polynomial, xm plus m and xr plus r prime here, and compose it with the set of equations we want to check. And there's a great property of this target polynomial is that the constant coefficient of this polynomial exactly matches the left-hand side accumulator checks, and the degree D coefficient of this polynomial exactly matches the left-hand side of this NUC proof check. And therefore, in order to prove that these two sets of check equations are satisfied, it's equivalent to prove that this polynomial is some polynomial for which the degree D coefficients are all 0, and the constant coefficient is just the error vector committed in the instance. To do this, it's very, like prover just send this polynomial, basically send the coefficients of this polynomial at degree 1 to D minus 1. And the verifier now will example and return a random challenge. And now, instead of proving this polynomial identity, we can reduce it to a random evaluation check. This is some standard trick used in cryptography. And now you see this random evaluation check is exactly with the same format of the cumulative check we had before. Basically, we are checking the same set of equations, except that this input has been changed. This input just becomes a random mini combination of the original accumulator and the NUC proof. So the folding now becomes really straightforward. Well, the prover and the verifier just fold this accumulator instance and witness and error commitments using random mini combination of alpha. And this is it. However, since it becomes more complicated and expensive when this set of equations being checked has high degree. For example, if degree is super high, then at the beginning of the protocol, the prover needs to perform D times L number group exponentiation to commit these cross error terms. Well, like you see, there's a D minus 1 cross error terms, and each of them have a length of vector L. And moreover, for verifier, it's also more expensive because it needs to pay like D group exponentiation to fold these error commitments. So to fix this, a key observation is that suppose we have some really good special sum protocol, which is super simple, with a number of checks, like number of equations being checked is really, really small. Then we don't need to pay anything for committing to this long vector because it's a short vector. Why not just directly use the identity function as a trivial commitment scheme, and we can remove all the possible group operation inside. So this gives us some hint. So basically, given any special sum protocol that might be expensive in terms of verification, we can transform them into another special sum protocol for the same relation, but the verifier is much cheaper in the sense that it only needs to check a single equation. More specifically, we add one more round on top of the original special sum protocol where the verifier will sample a random challenge, and the prover will send the power of this challenge. And then the key here is that the new verifier, instead of checking all the L equations separately, now he only needs to check a randomly combination of these L equations, which is basically a new combined equation. And here the random coefficients, Bj, is just one element sent by the prover. However, this scheme has two issues. The first issue is that, okay, yes, the degree only increased by 1. And the first issue is that the accumulation prover now needs to add one more message, send one more message, which is really long. And that means in the NUC proof generation, it needs to commit to it, which is also very expensive. And this turns out to actually easily fixable because instead of representing each coefficient as a single element sent by prover, you can represent as a product of k factors sent by the prover. For example, if we set k equals 2, now prover, instead of sending all the power of beta, only needs to send 2 square root L elements as this. And now each power of beta can be represented as a product of 2 elements sent by the prover. But now the prover is sending much shorter message, which is much cheaper and it can be negligible compared to the message already sent in the original protocol. So this solves the first issue. However, the second issue is that the verifier also needs to check, add more equation checks. So we see we already had a combination that successfully makes all these L equations into a single one, but now the verifier needs to add more checks in order to make sure the prover is exactly sending the correct message, exactly sending the power of beta rather than some malicious message. Fortunately, these checks are all very simple. It's low degree and not too many, and we can use another Peterson commitment to handle it. So that's why we add one more group operation here, but I think that's independent of degree D, so it's not a very big deal. So in summary, after all these optimizations, the number of group operations in both accumulation prover and the verifier are now both independent of degree D, and we can obtain a really concretely efficient accumulation scheme. Okay, so I actually have missed one more point, because now after these tricks, we make this really simple, the verifier only to check a single equation, we still need to figure out how to exactly compute these cross error terms quickly for the prover, right? We haven't specified that yet. But this is actually easy, where you just evaluate this polynomial at d different points, and you get an evaluation form of this polynomial, and do some interpolation like inverse FFTs to recover the coefficient form of this polynomial. That's exactly what you want. But what I want to highlight here is that in certain cases, which is like very common in practice, we can do even much better. So for example, what if the set of equations are heterogeneous? That means what if among the set of n equations, only 10% of these equation checks are with high degree, but the rest of them are really with low degree. In this case, we obtain an algorithm that has a complexity similar to the pure low degree case. This is useful because sometimes you only want to use high degree case for only a few number of constraints. But in this case, our performance won't degrade, and it will be similar to the case where the degree are all low. The second case is when we have some, like this kind of called branch case, which means that each equation being checked is of the form of sum of multiple branch equations. And that means, and only one of them will be active and be non-zero at each execution step. This is something that will happen, for example, in the VM execution simulation scenario. In this case, we use some so-called caching technique to accelerate computation of error terms so that complexity is now independent only on this branch circuit size rather than the entire step function circuit size. So it turns out to be really useful for supporting circuit branching and non-uniform computation and VM simulation in IVCs. Finally, there's another case when the snark proof is really, really sparse, meaning that like most of the entries are just zero, the number of non-zero entries is much smaller. In this case, we can exploit so-called commitment homomorphism and the caching techniques to make the complexity to be independent to this NUC proof size. And the complexity is only proportional to the number of non-zero entries. And this turns out to be really useful in accumulating the so-called lookup relation, which I explain later. Okay, so now that's the whole story about constructing accumulation scheme given some special sum protocol to some interesting relation. But now, in order to get an IVC, we still need to figure out how to build this special sum protocol for some NP complete relation that's expressive enough, right? It turns out to actually be an easy task. We obtain many one-move special sum protocol for interesting relations, and those schemes are almost trivial. What the prover just directly sends the long witness, the verifier direct check the set of equations which can be expensive that represent these relations. But turns out this special sum protocol scenario is even more powerful than that, because like enables us to accumulate also some really complex and non-algebraic relation that's not so straightforward to fold into some really simple special sum protocol that can be easy to fold. One typical example is that the lookup relation I mentioned, which the goal is to prove that some secret witness are inside some preprocessed lookup table that, for example, you want to prove some elements is inside the range of 0 to the 64. In this case, we design some really simple special sum protocol such that it exactly has some really sparse witness and low degree checks. And this turns out to be really helpful. So after combining with the general recipe, we obtain the first transparent lookup accumulation scheme for the lookup relation for which the prover time is independent of the lookup table size, which might be of independent interest. So after composing all this interesting special sum protocol for interesting relation, we can obtain the special sum protocol for NP complete relation we care about, which support a lot of expressive gates like high degree gates and lookup gates. So in summary, we've introduced a new generic and efficient way to build to construct folding scheme, and that supports support really advanced front end, which can be really expressive. And after combining the general recipe and efficient IVC compilers, we obtain an IVC called Protostar, which is highly practical, that can efficiently support high degree custom gates, really large lookup tables, and efficient circuit branching. At last, I want to mention one of the many interesting open questions. There are more, but for time reason, I won't talk all of that. But one such intriguing question to me is that to construct an accumulation scheme for the so-called online memory lookup relation, for which we have a prover time that's independent on the memory size. And what does it mean? It's basically the same problem with lookup relation. The only difference here is that the lookup table is no longer fixed or preprocessed. It can be some online memory that can be dynamically updated. And this can be the solution to this can be really useful to simulate some large memory read and write, for example, in zk-EVM application. So I do think it's a really meaningful question and encourage everyone to think about it and improve it. Okay, so for time reason, I'll stop here, and thanks everyone for listening, and I'm happy to take more questions.
Yeah, great. We have time for a few questions. Actually, let me ask you, like, I just want to make sure that this kind of your opinion here is expressed. Like, if you wanted to compare, let's say, some large, long ZK EVM computation, you can do it using a monolithic snark like Plonk or Marlin or any of the others, or you can do it using these folding schemes. So I guess kind of to summarize the two talks, in your opinion, which one do you think is the better way to go now?
It's a hard question. I think depends on the scenarios. I think if you can split this large computation into a lot of small parts, and if you can use IVC or PCD, that can have a really good parallelism. I think PCD is a really good choice. And also another advantage of using PCD or IVC is because you don't need to fix the size of the circuits or fix the configuration of the circuits. It can be, the key difference is this is dynamic. So I think it might be better to easier to maintain or something. But I guess the main argument is still the parallelization is generic parallelization way to do it. While for snark, you really need to have a really parallel friendly snark to achieve similar results. But I agree that there's also some overhead in IVC because in the recursive circuits, you need to add more logic. So that's some kind of trade-off. I don't have a full answer to this, but it's just encourage everyone to discuss this. Yeah.
Yeah. So the answer is it depends, and maybe probably requires a bit more research.
Yeah. Exactly.
Although, would you agree too, Sridhar? Yeah. So same. Okay.
Yeah.
There's agreement between the two of you.
Yeah.
Terrific. Great. We have time for a few more questions. If anybody has any more questions, please. Yeah. Mike's over there.
Okay, yeah, so you give us a general compiler from a NARC scheme to an accumulation scheme for these verifiers, right? Is it possible to do this compiler if the NARC is in some idealized communication model, like an IOP or a random oracle model? Is it possible to build accumulation schemes for those verifiers?
With those verifier or without those verifier? Can you?
Sorry, what did you say?
What's the exact question? Sorry. Oh.
Maybe you can repeat the question?
Yeah. So is it possible to build accumulation schemes or folding schemes for verifiers in idealized models, such as IOPs or in the random oracle model, without having to instantiate completely?
Oh, that's a good question. You mean don't need to use Vierchamier heuristic? I'm not so sure. Yeah, you mean doesn't use any heuristic assumption, you are saying? Yeah, that's a really hard question, I think. Yeah. So I don't have a full answer. The main question is how can we prove the IVC directly in the kind of random oracle model without using any heuristic assumption? Currently, we have some heuristic assumption. We will always embed some hash inside these recursive circuits. There's some work recently by Alessandro Chiesa that tried to partially solve this, but it's a really active area of research. I don't have full answer to that, though. Yeah.
Thank you.
Yeah, thank you.
Yeah.
There's optimization that you're talking about the betas, and the question is, why stop at square root of the length and not go full logarithmic?
That's a good question. So yeah, in general, you can increase k whenever you want. There's a trade-off here. That's when k is large, the number of elements you send is smaller and shorter, but there is a trade-off in the degree will increase as well. It become d plus k. And also, we choose k equals 2 because it's kind of a sweet spot, because usually for all the relation we care about, the prover already needs to send a lot of messages in this original special sum protocol. And when you choose k equals 2, square root L is usually already much smaller than the message we already have. So that's the reason we choose k equals 2 usually, but definitely you can easily generalize to k larger than 2.
And what is the practical kind of length of so L what's the practical
L you can understand as number of gates of a circuit, for example.
Yeah, but what are the practical sizes of for L?
Oh, I see. So I guess it depends on the recursive circuits, right? Usually for IVC, the recursive circuit won't be too large. I guess like 2 to the 16, like around that. Yeah. So square root L will be like less than 1,000, right? To the less than 1,000 is negligible from my perspective.
Thank you.
Yeah.
Great. I guess we have time for one
Yeah.
last question. Yeah.
It seemed like there was some disagreement about the generalization between CCS and special sound protocols. You made the point that you can represent algebraic or non-algebraic arguments like lookup arguments using special sound protocols. And I think the counterclaim was made earlier that CCS is able to generalize any special sound protocol. Could you comment further on that?
So for lookup, I'm not so sure if we can represent CCS easily. But I do want to mention that like there's no conflict in these two scenarios. For example, in our framework, I mentioned here, we can also easily extendable to support CCS in this setting. And CCS is also very good as a constraint system because like it generalizes R1CS to higher gates, but also save a lot of additions. So it depends on the setting you want. And also even if you want to use CCS, you can use this framework of special sound protocol framework. Yeah. Hope that answers your question.
Okay, great. Excellent. Thank you, Bini.
Thank you.
Yeah, excellent talk. Okay, and now for the last talk of the day, it's a real treat. So Eli Ben Sasson is going to tell us about Starks and Starkware and the future of Starkware. Eli is the founder of Starkware, and it's a really wonderful. This is an invited talk. It's a really wonderful, wonderful way to end the first day.
I'll use that. Let me just connect the power. Just in case.
Oh, you want to mic him up? Yeah.
I want. No problem.
Great. I should have prepared some embarrassing story about Eli while he's getting mic'd up, but I can't think of one right off the top of my head. Okay, great. The floor is yours, Eli.
This work? Okay, can you hear me? So thanks to Dan and the organizing committee for inviting me to give this talk and for organizing the marvelous SBC conference, which is undeniably the very best conference on research in blockchain. So thanks. So I want to tell you about three things. The current state of Stark research and implementations, a few recent highlights on research, and then some thoughts about future directions. And if there's one meta message I want to put out there is that if you're a developer or also a research student looking into stuff to do, so definitely consider both for research, there are a lot of questions at the end I'll mention that are very interesting to be resolved about Starks, both theoretical and theory and practice. And if you're a developer looking to build your stack, so definitely consider Starks because they're, I'm going to argue, very efficient, probably the most efficient, most safe, most future-proof, and also battle-tested. So what do we mean when we talk about a Stark? So there are two important letters. Let's forget about the ARC, though it's very important. S stands for scalability, which means the two things happen simultaneously. Proving time scales quasi-linearly or nearly linearly with the amount of computation being proved, and verification simultaneously is polylogarithmic. T stands for transparency, which means public coin protocols, no trusted setup. Notice that if you have a setup, it has to be succinct or polylogarithmic in the amount of computation. So if you have a proof system that satisfies these two properties, whether you call it by that name or not, it satisfies the definition of a Stark. Now, most Starks today happen to use Fry, not all of them, but most of them happen to use Fry, and also some form of succinct arithmetization, which has two components. Usually, there's some crafting of polynomial constraints, and then some way to succinctly talk about their enforcement domains. And then there are many different forms of arithmetization. Most Starks used today, not all of them, are post-quantum secure, and I think pretty much all of them are deployed non-interactively using the Fiat-Shamir transformation, and hence are also snarks, and sometimes they're referred to as Fry-based snarks, though I prefer the shorter and starker version. I gave a talk 3 or 4 years ago that was titled The Cambrian Explosion of Cryptographic Proofs, and I surveyed some of the proofs that were back then, and since then, of course, there's this enormous explosion in the amount of proof systems and stuff out there. But if we look at things deployed or soon to be deployed over blockchains, you could categorize them, and there are many, many different ways to parse the world. But one way is to talk about the associated commitment scheme and some of the white papers that are mentioned by projects when they deploy them. So you have the family to which Stark belongs, which are Fry-based. You have inner product arguments, such as things like Halo and bulletproofs and projects implementing over them. And you have the KZG pairing elliptic curve-based stuff, which I guess Groth 16 is like a very famous example of that. And so I last gave this talk half a year ago, February 23, and this was the status. And today, what has happened, if you just look at the difference, you'll see that there are a bunch more that have joined. Well, again, this is a very non-scientific sort of gut feeling, Twitter-based, asking my feed, what are they using or what do they hail to, and this is the set of answers I got to. I must confess that ever since Elon Musk took over Twitter, then at least my personal feed is not as effective, and folks are, I don't know who's reading it anymore, so maybe it's completely biased. But anyways, I digress. So it seems, from my skewed view, that you have a bunch of projects that are joining in the KZG pairing and in Fry. So these two branches seem to be, for now, like the most prevalent. So later on, I'm going to focus on both of them. And basically, so we have two major contenders for your commitment scheme today to choose from in terms of projects choosing what to build their proving systems on. And again, those interested in more why is this the characterization and so on, Google, a Cambrian explosion of cryptographic proofs in my name, and you may find more stuff on this. Now, one thing I want to mention is that both the StarkEx and StarkNet systems use actually the same prover, and we have just announced last week that we are open sourcing it, and the open source ceremony and event and the engineering session is going to be held this coming Thursday at the StarkNet Summit in San Francisco. So there's a QR code somewhere here. Please feel free to use it or reach out to any of the StarkNet folks if you want to join this exciting event and get a first-hand and first impression view of the stone prover that has been used at least by us, and probably will be used by a lot of other teams. So let me just say a few words about the stone prover. So stone stands for Stark 1. I think the second version is going to be called Stew, or at least that's going to be my suggestion for it. I don't know about the third version, but and then what is it? So this is the prover that we've been using for proving the computational integrity and correct execution of generic Cairo executions. And the statements proved are all of the same flavor. They basically have two parameters, a program, or rather a hash of a program, and an input or a hash of an input. When I say input, it actually mixes input and output, and it basically says, the statement says, program P run on this input executed correctly. But what is Cairo? So Cairo is a Turing-complete von Neumann architecture. It's the first Turing-complete Stark system to be run in production. It's been running in production since June 2020. And it comes with an ergonomic, Rust-inspired, safe linear typing system. And it is what we've been using for everything we've been doing since, over the past 3 years. And it's all going to be open sourced in 3 days. So please come and start using it. Kick its tires and everything, improve it. It's been used for generating StarkNet TPS of over 100, the most performant TPS by its capacity. And we've used it for StarkX for trading more than, for letting our customers trade more than $1 trillion, and a bunch of other impressive stuff, saving customers more than $1 billion. So it's very battle tested, it's very robust. Please check it out. It's, the Stark One Prover, stone hard. Another thing I want to point out is, and this is, a confession of, theory to practice distance. Some of you may know I started my career as a mathematician and theoretical computer scientist, but over the past at least 5 years, I've been solely or mostly dealing with entrepreneurship and StarkNet, Starkware. So the sad reality is that it took us 2.5 years from the white paper that had an academic implementation until we reached our first product, and in between probably a total of dozens of engineering years. I was also a co-author of the Zero Cache paper that also had an academic implementation, and a co-founder of the Zcash project. Again, a 2-year span and dozens of engineering years between white paper with academic code and implementation. There are a lot of details that need to go into something till it reaches maturity. And another fact is that, at least among our resources, if you look at the pie of engineering, probably 5% or maybe even less of the time being spent is or was spent on the core proving, and then 95% is on everything else, which includes tooling, the Cairo programming language, compiler, infrastructure such as full nodes and sequencers, customization for customers in various use cases, integration with wallets and API services. So there's all this to say that there is somewhat of a distance from between what is theory and practice. So now I want to tell you a few of the recent highlights from research regarding Starks and why you should care about them, especially if you care about practical implementations. So let's talk about the state of research 2 years ago and then compare it with what we know today. And later on, I'll give some open questions. We don't know everything that we want to know. There are a lot of very cool research questions out there. So 2 years ago, we knew how to build Starks efficiently only for certain nice fields, and today we know to do it over all fields. 2 years ago, we lacked concrete parameters for analysis of the security of Starks in the random oracle model, which is a very important model. And today we have very, very good estimates and also very good numbers and very good understanding of the safety in the random oracle model. 2 years ago, we didn't have any concrete security analysis for the use of recursive Starks and how security degrades with the depth of recursion. And today I have very good analysis with very good numbers for recursive Starks. And lastly, the amount of provable soundness per query of the Fry protocol was much lower by a factor roughly of 2 than what we know today. There's still a factor, one last factor 2 that is an open problem that I'll mention towards the end. So let's go, now I'm going to go over these 4 results just a little bit, what we didn't know and what we know today and why you should care about this. So 2 years ago, we knew to build Starks over fields that had subgroups, either multiplicative or additive, but that are smooth, that you can, the size 2 to the k, let's say. And you needed these groups both for efficiency of FFTs and low-degree extensions, but you also needed them for the Fry protocol. And today, we know how to get basically Starks and all the components needed for them on any field. And this is very important, for instance, if you want one day to port over a whole bunch of, let's say, Apple-based signatures, which use a very particular curve that is not, in any case, defined over anything that is, a nice field. And the way this is done is basically using the group structure of an elliptic curve, and there's an abundance of elliptic curve groups of various sizes and shapes. Well, not that many shapes. They come in mostly one shape, but sizes at least. There's abundance of sizes you can choose from. And theoretically, it should be pretty much the same performance, but this sort of asterisk is very important. The fine print is, so to best of my knowledge, no one has implemented them yet really for like a product, and whether it's exactly 1x the same running time for a similar size, FFT-friendly field, or 2x worse or 10x worse, we don't know yet. But they should behave similarly, and this is like really terrific news, especially for the future. So right now, any proving system is usually built on one fixed field, but we envision in the future where you're going to actually move across different fields very seamlessly and use them for whatever you want. And this is something you can do, especially with small fields, only using things that are, well, not only using Starks, but we know how to do it over Starks, and we don't know how to do it as efficiently over other kinds of commitment schemes, in particular KZG. So the next thing I want to mention is that 2 years ago, if you asked about the analysis or the security in the random oracle model, what is called T epsilon security, concrete parameters for Starks. So we knew some, theoretical estimates of how to get it. There are like three major components in building a Stark. There's the IOP, which is a very nice, elegant model, but analyzing it is somewhat hard. Analyzing it is algebraic, but it's just you can't use an IOP model for building your Stark. You need to add to it things like Merkle commitments and Fiat-Shamir. And for that, there was a missing piece in the analysis, which is round by round soundness. So what we know today is that there is very good random oracle analysis for the Starks as they are deployed, whether interactively or non-interactively. And this is very nice work of Bloch, Gareta, Katz, Thaler, Tiwari, Zachatz. I hope I'm pronouncing this name right. Very recent, like from 2 months ago. We also have the same sort of results in the ETH Stark documentation. And basically, the bottom line is that all of the deployed Starks are as sound in the random oracle model as they are in the IOP model. And in particular, if you know how to analyze the security in the IOP model, and you get k bits of security, so if you take a Merkle tree commitment and you use 2k bits, then you have k bits of security, which is what everyone has been using anyways. And so that seems to be fine. By the way, a very good open question is whether you actually you need 2k bits, or you can use less than 2k bits and get the same security. It's an open problem to which we don't know the answer. And it's, you could have something like a factor 2 in proof length by resolving this. The third result I want to mention is that if you looked at recursive Starks, so everyone, most of the projects deploying Starks in practice are already making use of recursion, both StarkX, StarkNet, but also the Polygon teams, RISC-0, and so on. And if you looked at the theoretical analysis for what happens to security, we didn't have any good estimates for that. And today, or rather I should say very soon, so this paper, to the best of my knowledge, has not yet been published. It's by Chiesa, Guan, Samocha, and Yogev. So it's not out there just yet, but I did get their authorization to mention this result. And it basically says that if you're looking at the model the relevant model for analyzing security, which is a Q-bounded random oracle model adversary. Basically, the security of a recursive Stark, no matter what is the depth of the recursion, is the same as a one-shot Stark, like with no recursion, with the assumption that you externalize all of your Merkle tree and Fiat-Shamir queries, which from a theoretical point of view is something you want to do, but maybe practically, you know, it's a little bit like the Fiat-Shamir. You can just assume that it's all fine. But anyways, we do have much better handles on what is the use of recursion, and it's pretty safe to use, which is good because everyone's been using it. So it's good to know that we have the science behind it. The last thing I want to mention is that, well, now I go back 3 years. We knew that every invocation of the Fry protocol, which is the commitment scheme used for soundness of most of these Starks, you could have 1/4 of the logarithm of the rate, many bits of provable soundness. So it means that if you use the blow-up factor of 16 or a rate of 1/16, you could provably get roughly 1 bit of soundness, and it was based on a combinatorial analysis that sort of deteriorated with the number of columns. And what we know today is that actually you get twice as many bits, and there's still a residual question of is this factor 2 reduction really needed or not? And then I don't want to go into the math of this. The biggest change, if we look back 3 years in Starks that should matter to developers, is that 3 years ago was very hard to build circuits and do computations with them. You had to do it by hand, which is very hard, and you know, safety becomes a big problem. And today, of course, we have many you know, Turing-complete programming languages to choose from. Of course, there's Starkware's Cairo, but there's also Maiden. There are a lot of compilers from EVM and other systems, or standard VMs like the RISC-0 team. So today, if you're a developer, it's much easier to write code and just have it deployed. Now I want to talk about future directions. And a big question is, you know, to fry or not to fry. So at least for us at Starkware, we started with this route like five years ago. There's a lot of exciting research all the time. We just heard about folding schemes and other stuff. So, you know, is it still something that you want to use? Maybe it's outdated. And I want to answer that. I think the answer is yes, that it's still going to be much more efficient by a factor of, I don't know, between 10 and 100x more efficient than KZG-based stuff. And I want to explain why. So this is a very rough back-of-the-envelope calculation that we are using inside at Starkware. Of course, you need to measure things end-to-end and do your own research. But if you look at just the commitment part of, let's say, a word, a 32-bit word, in a stream of 2 to the 20 words. So you can compare a Fry to KZG. So KZG, let's say, over a 256-bit field, which is the standard used today in most teams. So you're going to use Pippinger, which gives you a cost of 2 times log of the number of bits divided by the stream size, that many group operations. And then, you know, asking around a little bit, it seems that around 40 clock cycles is what takes 1 modular multiplication for a 256 size bit. And then you need roughly 12 mod mols per group operation. And if you sum all of this up, you get around 1,700 clock cycles. So the Stone Prover, which again, we're releasing, this is something that we've been working on for the past 4 or 5 years. So it's sort of oldish. The major cost there, or the cost there to commit to the same thing, is roughly the FFT cost and then the Merkle commitment cost. And if you use a blow-up factor of B, we use in the code that will be open source the factor of 16, you can tweak it. You have the same mod mol cost of roughly 40 cycles per mod mol, modular multiplication. And we're using Blake as the hash, which is very efficient. It's roughly 12 cycles for a 32-bit word. And then you get a total of around 700 or so clock cycles. Now things get even better if you move to smaller fields. So here's an example of 63-bit field. The main difference is that the field size, the clock cycles per operation have gone down by roughly 10x, thanks to what modern CPUs can do. And even if you use something like the Poseidon hash, which is not 12 cycles, but around 300 cycles, if you go with a small blow-up factor, you get a total of around 400 or 4x better. And of course, if you use something like a very small field, like a 32-bit field, and you use the Blake hash, then you get to something like 35 to 40 clock cycles for per element in this hashing. Now, again, this is rough back-of-the-envelope computation. There are many other components to both of these systems in whichever way you do it. But at least to us, this indicates that it's a good, it's a safe bet to say that Fry-based systems will, over small fields at least, will continue to be most efficient in terms of proving time. Now, what about in practice? So in practice, there are many, many benchmarks. I'll mention that 3 years ago, at the request of the Ethereum Foundation, we proved 100,000 rescue hashes in under 10 seconds on a quad core with 16 gigabytes RAM. And back then, it was 20x faster than the best KZG best or Groth 16 implementation, which is roughly in line with the numbers that you see here. And I don't know what is the best KZG best implementation for, let's say, 100,000 invocation of the KZG-friendly hash. It's a good question on similar hardware, but I think it's a good question to benchmark and see where the numbers come out. Now, in addition to being the fastest commitment scheme, it's also agile, works over all fields. It's also the safest in terms of no trusted setup, post-quantum security. The security assumptions only assume a collision-resistant hash. Of course, KZG-based systems have a lot of advantages, such as much, much shorter proofs, around 200 bytes. And they have additivity, or they're homomorphically additive, so you can do cool things like folding. And I basically just want to end with future research focus. So because the two main components, or one of the main components in Starks is the speed of the hash. And right now we're in this sort of sad situation where you either pick a Stark-friendly hash, but then it's very slow on CPU, or you use a very modern CPU-friendly hash, but then it's very hard to argue about it in your next recursive invocation. So what we really want is faster Stark-friendly hashes. You also want to do better arithmetization, and there's a lot of exciting recent work here that at least excites me. So use of logarithmic derivatives, I think they're, this thing that Ulrich Habok from the Polygon Zero team started, I think is really, really interesting. There are lookups of various forms, Planck, Lasso, and just like yesterday, so Ulrich Habok and Shachar Papini, who's somewhere around here, posted a very nice sort of update to the Lasso and log derivatives paper that I urge you to look and also talk to Shachar. And a lot of work on how do you write your errors. Finally, my favorite math questions. The biggest one is, what is the soundness beyond the Johnson bound? So is the factor 2 loss in soundness necessary or not? It's a really terrific open problem in math. What about EC Starks over high genus curves, not elliptic curves? What happens with them? We know that there are amazing error correcting codes over such worlds. And then can we replace the Merkle trees with better commitment schemes? I'll just mention that there are a bunch of activities, my time is up, that we'll be doing. Come here, Noam Nissan, talk about fees and tokenomics. I'll be speaking tomorrow at Berkeley. If you want to hear the more theoretical side of things, if this wasn't theoretical enough for you, there's going to be more theory tomorrow at Berkeley. And then, of course, join us for the StarkNet Summit. So thank you very much.
Awesome. Thank you, Eli. What a wonderful way to end the day. So again, we have time for questions. If anybody has any questions. Yeah, I see. Please go ahead.
Thanks for the very nice talk. Just want to ask you compare with the Fry-based Stark with KZG-based Snark. how do you consider to compare like Fry-based Stark with the snarks that not using KZG, for example, using like Hydriac, like Orin, because there are new kind of snarks, like for example, Hyperplunk and Spartan, these kind of like snark systems are actually not using KZG. Would that make snark looks better in this comparison chart?
I don't know. I don't know. But like, yeah, one has to do these measurements.
Okay, thanks. Yeah, question, please.
This might be a better question for like an extended conversation, but I am curious about the factor 2 blow up. So I was curious if you could say a little bit more about that.
Well, I can say a lot more about
Okay.
that. Well, there's this thing in error correcting codes called the Johnson bound or the list decoding bound. And right now, the provable soundness that we get matches exactly that bound and even uses in a very non-trivial way the Guruswamy-Sudan algorithm for decoding, for list decoding. And now the question is, what happens above that? And it's a very mysterious regime, also in general for like list decoding. It's an area of a lot of active results, active research. Like what happens between, 1 minus square root the rate and 1 minus rate in that regime? And we don't know. So we know that you cannot get more than a factor 2 of soundness from Fry because there's a trivial attack at that like 1 minus the rate. And then there's this big open problem for Fry. I should mention that for Deep Fry, which is very similar to Fry, we actually know to connect the two open problems. So we know that the soundness of Deep Fry is directly related to the list decoding problem. But we don't even know if this connection exists for pure Fry.
Thank you.
This is probably, if you had to guess in the next 10 years, is this problem going to get resolved, or is this one of these millennial problems?
Yeah, it's going to be resolved,
It's
yes.
going to be resolved.
Because there's a lot of exciting, well, there's a lot of research on just list decoding. Yeah. So I think it will be sort of at least tied to it a bit more.
I see. Great. All right.
I don't know.
Oh yeah, Bramco, one last question,
Yes.
please. Go ahead.
So it's incredible that we now can do Fries over any arbitrary field. But another algebraic object that is very popular is the ring of 64-bit unsigned integers. Is there any chance we can do Fry directly over rings?
That sounds like a research question.
Yeah, it's a good research question. I would guess that probably the answer should be, it should be somewhat doable, but I don't know, like, yeah, no, it's not, I don't know the answer to that. There's hope.
I mean, polynomials over rings behave
Yeah,
a little weird.
I know, polynomial,
So
well, weird
it's
things
not clear
happen.
that this
Weird
is-
things happen over rings, but it's not like doomed.
You sure? Because you have cubic polynomials can have lots of solutions.
No, I'm not sure. Of course I'm not sure.
Yeah.
Okay.
That's a hard,
How can I be
tough
sure?
question. Okay, this is a wonderful way to end the day with a hard question to think about. So thank you so much, Eli.
Thanks.
This is great. But our activities for today are not over. So now we are going to transition to a reception. So the reception is going to be outside. Reception is going to run until 7. It's a wonderful time to talk to folks and meet everybody here. The only request is that apparently they're asking not to bring the wine into the building. So it's okay to drink the wine, but outside. And so enjoy the reception, and we'll see everybody here at 9 a.m. tomorrow.
Thank you so much. Thank you so much. Appreciate you.